Hello. Hopefully my mic is turned on. Welcome to the last part of the Weather and Climate Livestream. We have 9 hours to go until we hit 100 hours, which is absolutely incredible. I know that was our goal this entire time, but part of me was like, can we actually do that? I don't know. This is one of the most incredible things I've ever been part of, and I can't wait to see how the last few hours go. I'm not going to take up too much time since we're a little bit behind, but I just want to remind everyone, this is the Weather and Climate Livestream. We've had 91 hours of amazing talks from meteorologists and climate scientists from across the country, and a few international guests stepping in to just tell us how important all of the science is to our daily lives here in the US, the ramifications it has abroad, and why it's so important to keep funding this science. All the amazing benefits that it provides to folks in the US and around the world. So if you want to head to wclivestream.com/act, we've made a script for you. It's super easy. You can call your representatives, leave a message, talk to a staffer. All of that matters. All of that counts. Thank you so much for taking the time. And with that, I would love to bring on our next speaker, Jessica Labe. Apologies if I mispronounced your name, who is an oceanographer. And I don't have the schedule up yet, so I don't know the title of your talk. Plankton, Biological Pump, and Earth System Models. Amazing. Take it away.
All right, thank you so much. I'm so thrilled to be part of this live stream. My name is Jessica Labe. I am a marine ecologist and ocean biogeochemical modeler, and I study plankton. You can just see from this slide here, just the wonderful diversity of plankton that exists in the ocean, from the small microscopic phytoplankton all the way to what we would consider still zooplankton, these jellies, these gelatinous zooplankton at the top of this figure. So plankton are really important because they form the basis of the marine food web. See in this figure here, the plankton includes these phytoplankton, which are kind of the plants of the ocean, and zooplankton of lots of different types, or the animals of the ocean. And then these zooplankton, phytoplankton, zooplankton, then are food for fish. Fish, from forage fish to tunas, sharks, top predators, seals, seabirds, etc. They really, if we didn't have plankton, we wouldn't have the rest of the marine food web. They also produce about 50 to 80% of the oxygen that we breathe. It's estimated that plankton productivity in the ocean is about equal to that of land, about 50 petagrams of carbon per year. And they also sequester carbon dioxide from the surface ocean to depth. And this process is called the biological pump. And I'll talk a little bit more about that in a little bit. So how do we study plankton? We study plankton using a variety of different ways, from experimental laboratories, seen here in the example from Norwegian Institute of Marine Research, to field-based or ship sampling. Here, this is actually just some work from my dissertation off the Florida coast. And then also with satellites. And these three methods are mostly called observational methods. And then on top of that, we have models. These models are mathematical equations that relate the amount of incoming light, for example, to available nutrients and temperature, to then growth rates of phytoplankton. And then that serves as a basis for the consumption and growth of zooplankton, then fuels the formation of detritus. The most simple of these models are called nutrient, phytoplankton, zooplankton, detritus models, or MPZD models. They were developed about 35 years ago and are still being used today. There's many degrees of complexity in these marine ecosystem models or ocean biogeochemical models. I will kind of use them a bit interchangeably, from the most simple MPZD models I just described to some of these more lower complexity models that maybe just model one nutrient, such as phosphate, to now these in the middle, intermediate complexity models. We're modeling many different nutrients, iron, nitrate, phosphate, and modeling many different types of phytoplankton and zooplankton too. Then the last would be this really extremely high complexity models that are interested in more the diversity of plankton. these intermediate complexity models are really important because they serve as the basis for Earth system models. Earth system models, you've probably heard through this live stream, are a collection of different models coupled to each other. And there's Earth system models and climate models. They're very similar, but here Earth system models include more of the biogeochemistry and the land processes, the ocean processes, the chemistries of the ocean, and that we call them chemistries of the Earth system, and we call these Earth system models. These component models are process-driven, so they're starting from the ground up, from the physical processes all the way to the chemical and biological processes. And when we develop these models, and I am an ocean biogeochemical model developer, we must balance the computational cost with complexity. And here in the US, the major Earth system model development is funded by the National Science Foundation, by NOAA, by DOE, and NASA. So these Earth system models show us what could happen in the future under various different scenarios of climate change. So here we're interested in the ocean, so we're looking at some of these plots from this paper in 2013, Bopp et al., showing the change in global ocean oxygen content under a range of different scenarios. So this is now not using just a single model, but an ensemble of different models, and showing how oxygen may change under extremely high emission scenario, RCP 8.5, compared to a lower emission scenario. And similarly, on the right, you can see how net primary productivity will change under various different scenarios. And there's much more variability here between the models and between the scenarios. And as we've progressed in time, we can start looking a little bit more on newer models, which will then show us not only how MPP will change, but how phytoplankton and then zooplankton biomass will change under different scenarios. So this is now a 2019 paper, a few years later. This is from the AR6. And these phytoplankton and zooplankton biomass anomalies, the first two plots on the left and center, are just showing percent changes relative to the historical period. And then these models then serve as a basis for additional models that we will use to look at impacts. So for example, fish models, here's a range of different fish models on the right that are forced by these ocean biogeochemical models, and that will show just a huge range of impacts to fish, from very little change in one model to about 40% decline in biomass under a high emission scenario. But also, what's really important about these models is it shows what impact can be avoided with collective action. So here, I love this paper from Krumher et al. 2017, just showing how MPP changes relative to a historical baseline, 1920, in two scenarios: in an RCP 4.5, kind of a middle emissions, and a high emission scenario, RCP 8.5. And you can just really see, just if you look in the Atlantic, some of the areas that are really, we can avoid them being really dark blue, and these big changes in MPP with this lower emissions. And one of the things that is really important to note for this live stream is we're no longer on this extremely high emission scenario trajectory. We're no longer on a RCP 8.5, but we're actually on a pathway that's closer to RCP 4.5. So it's really important that we can use these models not only to look at the worst impacts, but also what can be avoided if we all decide to band together to make changes. All right. So I'm really interested in the ocean biological pump. This is one of the really key elements of the marine system that we simulate with ocean biogeochemical models. The ocean biological pump is a collection of processes that together remove carbon from the surface oceans to depth. And this estimated flux of detritus from the surface oceans about 5 to 10 petagrams of carbon per year. And this is about equivalent to the total global emissions, anthropogenic emissions. But I'd like to note that this is a natural process. So this has been occurring without climate change, and it still continues to occur now. And this process is really important for setting the vertical gradient of carbon and nutrients in the ocean. So in Earth system models, a lot of these processes kind of on the right-hand side of this figure, involving mesozooplankton, fish, jellies, as well as some of the bacteria processes are typically omitted or highly parameterized, or rather what this means is we set these models to fit data rather than kind of representing every single little pathway that's going on in nature. And we might be interested in representing some of these more pathways because we need to better understand these feedbacks between the biological pump and climate. So now, I'm sorry, this is a little bit small. I was trying to fit all of this into one slide. But if you just take a look at the top right, the positive feedbacks, I'll just run you through one example here. So with the increase in atmospheric CO2, this will increase the ocean vertical temperature gradient, which increases stratification. With the increase in stratification, this will decrease the amount of surface nutrients in the ocean, which then drives phytoplankton to be smaller. The smaller phytoplankton take up nutrients more effectively, so they outcompete some of the larger phytoplankton. With the shift in phytoplankton size, this actually then results in a decrease in particle size overall, which then decreases particle sinking speed. Smaller things tend to sink slower than larger things, which then decreases POC flux and then results in a positive feedback with atmospheric CO2. So that's just one example from the positive feedbacks loop. On the negative feedbacks loops, if you look at the inner loop, so atmospheric CO2 will increase, here the loop says atmospheric CO2 to decrease oxygen. I already showed you that in a few slides back. I'll kind of just walk you through a little bit of the processes. So atmospheric CO2 will increase ocean temperatures. Warmer ocean temperatures can hold less oxygen. The oceans will also be more stratified, which leads to decreased oxygen in the upper oceans. So then this will then slow remineralization, so slow the breakdown of this detritus in the water column, which will then overall slow POC flux. And this will overall slow remineralization. It results in an increase of POC flux to depth, which actually then decreases atmospheric CO2. So this is now a negative feedback where something in the ocean then results in a decrease in the atmospheric CO2 over time. But disentangling these feedbacks between positive and negative, and then also some of these mixed feedbacks is really important and why we need better models of the marine ecosystem. So some of my work, I'll just show you some of this in the last few minutes, focuses on the higher trophic levels in the ocean. So one of the missing gaps in these models is these fast sinking detritus from fish and pelagic tunicates. So here on the right, you can see some of these, this fish ball is really cool, as well as this salp chain. So these pelagic tunicates are these really cool marine animals that filter feed. They kind of pump water through their barrel-shaped body. They are able to eat these extremely small phytoplankton, and these pelagic tunicates end up shunting carbon away from the microbial loop and towards export. Another thing that's really important is that the detritus from fish and tunicates sink much, much faster than other bulk detritus in the ocean. So this fish detritus is fish poop, and the tunicate detritus is tunicate poop, but also they're sinking carcasses. They have these big boom and bust cycles where populations will increase in a big jellyfish bloom and then all die very quickly. And the sinking carcasses, as well as their poop, sinks very quickly up to 1,500 meters per day. So a particle at the surface will make it to depth in just 4 days or so. This is a non-negligible part of the biological pump, but is rarely included in models. So one of the things that I've been doing is modeling these pelagic tunicates and the fast-sinking detritus in the NOAA GFDL Cobalt ocean biogeochemical model. So Cobalt ocean biogeochemical model was used by GFDL in their last contribution to CMIP. So CMIP 6 is an extremely well-performing model and is also one of the more complex ones. And so one of the things that I've done in the past couple years is add a little bit more to that complexity, kind of surgically selected to study this element of the biological pump. So I added these tunicates in two sizes, kind of a small and a large. And I'll just show you very quickly some of the results with this fast-sinking tunicate and fish detritus. So at the first row, I'll orient you to these plots. The top row is showing the export out of the surface ocean, so 100 meters. And on the left is our model with all the bells and whistles, with our multiple tunicates, with the fast-sinking POC or detritus. And the center here is our control without the fast-sinking POC. And what you can see is what happens in the surface oceans is this fast-sinking detritus removes carbon and also nutrients from the surface oceans and then sends it to depth. So the bottom panel is the export at 1,000 meters, or what we would call a sequestration depth. So about 11% decrease at the surface, now 37% increase at depth. So we were interested in what happens once you're sending so much carbon, nutrients, detritus to depth. And one of the things that was really cool for us is what happens to these oxygen minimum zones in the ocean. So I'll just back up a little bit, kind of pause here at this slide and back up a little bit and tell you that there are a number of biases in our ocean biogeochemical models. One of the largest biases that has historically been in our models is we tend to overrepresent these hypoxic zones, these oxygen minimum zones. This was historically thought to mostly be due to the physical resolution of the models. It's really hard to get both a combination of these extremely fast jets in the equatorial regions, as well as the subsurface circulation, and our models have historically been, about 100 kilometers in horizontal resolution. So pretty coarse. And with these coarse models, the hypoxic zones end up being much bigger than observations. So here, what I'm showing is just an example from that I've pulled out that actually shows there may be a biological addition to these models that may reduce the amount of hypoxic expansion here. So the total hypoxic volume is on the top as is oxygen less than or equal to 60 millimoles per meter cubed. So organisms are generally able to be in these waters, but maybe they will not. Maybe the largest animals will not be surviving very well. And then the bottom here, the total suboxic volume, or the oxygen at or below 5 millimoles per meter cubed. So this is extremely low oxygen. There will be very little animals here, and here what I'm showing is that with the addition of these fast-sinking detritus, we are actually able to reduce that total suboxic volume, if you look at the blue line compared to the red line, by about 40%. And this is just in a kind of an ocean-only model, and we are right now in the middle of developing our next Earth system models, and we will be incorporating some of these processes. So kind of going back to understanding these climate ecosystem feedbacks in marine ecosystems. So for example, this is the positive feedback that I highlighted earlier. One of the things that I've shown through a couple of my studies with pelagic tunicates is that we'll have a little nuance on this positive feedback. So with increasing atmospheric CO2, we still have ocean warming and increased stratification and decrease in surface nutrients and decrease in phytoplankton size. But what may happen with pelagic tunicates is that because these tunicates are feeding on this really small size phytoplankton, that their fraction of the ecosystem may actually increase with climate change because phytoplankton size overall has decreased. And because we'll have these really fast sinking detritus from tunicates, this will result in increased POC, particulate organic carbon sequestration at depth. So this may be a kind of a shift from a positive to negative feedback loop that I think is transient in nature, but we really won't know until we do a little bit more with incorporating these processes into climate models. All right. This is it for me. In summary, we study plankton using models. This is really fun. And these plankton models, coupled with in-earth system models, can reveal the effects of climate change on marine ecosystems. There's a lot of ongoing research on the biological pump that reveals in combination of models and observations, just the importance, the huge importance of jellies and fish in sequestering carbon and nutrients to depth. I just showed you a little snippet of some of my work, but you can use this QR code to look at this recent paper of mine that was published in Geophysical Research Letters. And more work and more funding to support this work is urgently needed to disentangle complex climate feedback loops to help us better understand how these systems may shift in the future, what the impacts may be to fish, to marine mammals, and other things that we really care about in the ocean. All right, thank you. This is it for me. Any questions and comments?
Amazing. Great job. You have tons of questions and we only have 4 minutes to get through them. So I'm going to start pulling them up and see what you have to say. So let's see, what's the first one we should start with? This one was very popular. Has the rate of sequestration by the ocean biopump changed with human-made carbon spike?
This is a really good question. We actually do not know. Scientists do not know if the rate of export and sequestration by the ocean biological pump has changed. This is because observations of the ocean biological pump is really difficult to make. They use a combination of these sediment traps that are kind of deployed at depth and measure the amount of detritus that hits the trap over a certain amount of time. They use these thorium kind of isotope methods, and also now increasingly are using Argo floats. You kind of heard a little bit about that in the previous talk, to look at the flux of material down to depth. But we do not know if carbon export has changed, and that is really why we need more support, more funding to do a combination of these observational studies and these modeling studies to look at this process.
Okay, and so I'm guessing, is this kind of related? So how do you test the model of species abundance and location and where all the detritus is coming from against the observations? Is that a thing that's currently very much in?
Yeah, this is also a really important point, and this is actually, what I think about a lot in my day job, is how do we test these models? So unlike on land, ocean is kind of difficult to observe. The ocean, we go out with these nets and sensors to get data of phytoplankton, zooplankton. And then we also use fish catch data for fish models, and they end up being aggregated over time because these observations are scarce. Because it takes time to collect them, we tend to end up aggregating maybe a decade, multiple decades of observations all together for a global picture. So this is kind of why it becomes really hard to disentangle these, if there's been climate effects, these questions of, has there been any recent changes to the ocean biological pump, to these fish and zooplankton, observations over time. So for these fish models, just really quickly, they use this big data set called the Sea Around Us data set for fish catch globally in the large marine ecosystems to validate these fish models. So they are validated against observations.
Amazing. Good to know. And then kind of going to a different type of observation, Kim M wants to know if you've used the PACE satellite in your research on Plankton.
I have not yet used the PACE satellite observations because it's just come up. The PACE satellite is really exciting, and I'm extremely excited about what the PACE satellite will show us with these hyperspectral observations. I think we can start looking at really cool dynamics of phytoplankton size, of particle size that will give us a little bit more information than what we had before.
Perfect. Yeah. And that's a great plug kind of to the whole reason we're here is we got to make sure that the funding for these sort of impressive satellite projects keeps going forward for as long as possible.
Yeah.
Yeah. All right. Thank you so much, Jessica. That was great.
Thank you.
All right. So we are halfway through our 91st hour, which means that we have 8.5 hours of this whole thing left until we hit 100 hours. In theory, the math should be getting easier, but I've been awake for longer and longer. So, it is what it is. But welcome if you're just joining us at the beautiful hour of 7:30 a.m. on the East Coast or whatever time it is where you are. This is the Weather and Climate Livestream. We have been going for 91.5 hours now, talking about weather and climate science with meteorologists and scientists. I haven't even been talking that much and I'm losing my voice. Oh well, we've seen a lot of great talks, and the next person coming up is no exception. But before I bring him on stage, I'm just going to go through the host spiel. I heard this, Virginia was saying this in the section before, but this is a great time to mute me. You've heard this probably dozens of times already. Take this time to pull up the wclivestream.com/act on your phone or your computer and call your representatives, because part of why we're here showcasing the science is to inform you, the viewer, what we're doing and why it's so important. Especially in the US, where we have for a very long time been kind of considered world leaders in weather and climate predictions. A lot of that is at risk now due to funding cuts that have already happened and funding cuts that are proposed. Fortunately, many of those are not set in stone yet. So calling your representatives now is a great way to, keep funding going, telling them why it's so important, maybe telling them a fact, why you love Argo floats so much, why it's so important that the US continues funding 50% of the Argo fleet. So take this time, pull up your representatives' numbers on your phone. I promise it's not as scary as you think. I believe in you. I'm a millennial, we hate phones, and I still do this basically every day. I believe in you. All right, so with all that said, I think it's time to bring up Tristan Abbott, who is going to talk about understanding thunderstorms in climate models. I am so excited because I have no idea how you do this.
Okay, great. Good morning, everybody. Or I guess afternoon if we have some people joining from Europe or somewhere else in the world. So I'm Tristan Abbott. I'm a climate scientist. I work right now for a nonprofit that relies mostly on philanthropic funding, but was until very recently, so about a year ago, a postdoc at a NOAA modeling center in Princeton. So the same one the same place where Jessica works. And the work I'm going to talk about is largely based on what I was thinking about while I was there. So the thing that I was thinking about while I was a postdoc at NOAA was simulating thunderstorms and climate models. Most people here, I'm guessing, probably have some picture in their mind when they hear the word thunderstorm, but just for the sake of making sure we're all on the same page, I want to start by sort of giving a working definition and explaining some terminology that I'll use during this talk. So when I talk about thunderstorms, what I'm really talking about are troposphere-deep convective cloud systems. I'll use this picture to unpack what each of the components of this phrase means. When I talk about convective clouds, I'm talking about clouds that form because warm, buoyant air that from near the surface of the Earth gets lifted high into the atmosphere. When I say troposphere deep, I'm talking about convective clouds that form in parts of the world where the surface is warm enough that air lifted from the surface has enough buoyancy to make it all the way up to the tropopause. So that's the transition between the sort of weather layer of the atmosphere and the next layer higher up, where the ozone layer lives. And when I say cloud systems, what I really mean is that thunderstorms are not individual clouds. They're typically clusters of many different troposphere deep convective clouds that collectively produce the rain and the lightning and the thunder that you're used to seeing from thunderstorms. So the climate scientists' word for a thunderstorm is just convection. I'll probably use that term a lot throughout the rest of this talk. Just know that when I say convection, what I really mean are clouds that you probably know as thunderstorms and clouds that look like this one. So thunderstorms of convection are, you find them all over Earth. They're particularly common throughout Earth's tropics. So this is a satellite image from a geostationary satellite that NASA and NOAA operate. The image is centered on Central America and the tropical Eastern Pacific and Western Atlantic. This cluster of clouds here, you're seeing the anvils on top of a group of convective clouds. Northern South America, all of these clouds are convective. Over Central America, you can see some, they're pretty young convective clouds. So these circles are the tops of convective towers hitting the tropopause and starting to spread out to produce anvils. These clouds over here are all convective clouds too. So they're a very common feature of Earth's atmosphere. You could pull up the latest image from NASA and NOAA's satellite images and see convection, especially in the tropics, basically whenever you want to. So there are a lot of reasons to care about convection if you care about climate. But I think one of the most sort of striking and fundamental ones is that the tropics are, in a very real sense, habitable thanks to convection. So this plot is an image. It's based on NASA satellite data showing average rain rates. So the yellow and orange parts of this plot are parts of the world that are very hot and humid, very rainy. These are parts of the world where you tend, on average, to get a lot of convection. Darker blacks and blues are parts of the world, these are mostly in the subtropics, where the atmosphere is very dry, where there's very little rain, very little clouds. One of the sort of remarkable things I think about Earth's tropics is that the very deep tropics, so these are the hot and humid regions that show up as yellow here, receive so much sunlight or so much heat from the sun that if they were isolated from the rest of the world and had no way to export heat to other parts of the planet, they would fall into a runaway greenhouse. So a runaway greenhouse, what I mean is a climate state like the one you find on Venus that happens when a planet receives so much sunlight that it has no way of losing the same amount of heat back out to space through radiation and just gets hotter and hotter and hotter and hotter until you eventually boil off all of the water on the planet's surface. That water escapes to space. You lose water, the greenhouse effect that water provides, and the planet's finally able to stabilize, but at a very, very warm temperature. So the surface temperature of Venus is hot enough to melt lead. The surface temperature in Earth's tropics obviously is warm, but not Venus warm, and that's largely thanks to convection. So convection does two important things. The first is that it lifts a lot of air up in the deep tropics. That air has to come down somewhere. It does that in the extratropics and creates these dry regions. It also takes a lot of the heat that gets absorbed by the Earth in the tropics and transports it to these dry regions where that heat can be very easily released back out to space. People often describe this as convection creating Earth's radiator fins that help keep the climate of Earth, especially in the tropics, sort of, in a relative sense at least, comfortable and habitable. So if you are, care about Earth's habitability and are happy that people live in the tropics, you should care about convection, because there's a very real sense in which the tropics probably wouldn't be habitable if convection didn't exist. Oh, sorry, I have some pictures of radiator fins that I forgot to pull up. At the same time, and so this is probably not a surprise to you if you live in a part of the world where there's a lot of convection, intense convection can be responsible for an extraordinary amount of damage. So we know, thanks to reporting work by NOAA, that in 2024 in the US, there were 27 different billion-dollar weather and climate disasters. So these are events that caused at least $1 billion in damage. 17 of those were caused by severe thunderstorms. So those are hazards like wind, hail, tornadoes. 5 more were caused by landfalling hurricanes, and hurricanes are weather systems that don't look like an ordinary thunderstorm by the time they make landfall as a mature hurricane, but actually form out of just sort of convective systems that happen to organize in a certain way. So I guess I mentioned this probably isn't a surprise if you live in a part of the country where there's frequent intense convection. This is a video that I took when I was in Madison in Wisconsin visiting my partner's family a couple of weeks ago. I took this video, it was probably like 5 minutes after I was sitting outside on her parents' deck editing a paper. I knew, thanks to the National Weather Service, that there was a chance of thunderstorms that might produce hail that day. I noticed the sky starting to look a bit stormy, so I packed up my laptop, went inside, stuck my car in a garage, and about 5 minutes later, we stood by the front door and watched quarter-sized hail start falling from the sky. So despite this sort of obvious importance for climate and obvious importance for weather, though, convection tends to be a bit of an Achilles heel for climate models. I think the most straightforward way to illustrate why that is to take a satellite image. So this is from a Japanese satellite. But again, you can see a lot of convective clouds throughout Earth's tropics. You can also see an enormous amount of sort of very fine, small-scale detail, and compare that to what a cloud field in a climate model looks like. So climate models work effectively by taking the entire Earth, dividing the Earth up into a bunch of pixels, and running simulations that tell you how the properties of those pixels evolve over time. In order to run long climate model simulations that capture all of the different processes that matter for climate, people generally have had to limit computational expense by creating a relatively small number of relatively large pixels. And so that means that the cloud fields that you see in most climate models look something like this. So this is meant to represent what you would see in sort of maybe now slightly outdated, but relatively typical climate model resolution. You don't see anything like the fine detail that you see in satellite images. You see very pixelated clouds, which sort of, that look like this because the resolution of global climate models historically has been quite low, just so that they're models that you can run at reasonable computational expense. One of the results of the limited resolution is that climate models historically have been reliant on what are called parametrizations to represent the large-scale climate impacts of convective clouds that they can't themselves resolve. That approach, in some ways has been wildly successful, right? The climate models are the best tool that we have for understanding how decisions that we make in the future will affect the climate of the future. But at the same time, the process of developing parametrizations, coming up with highly simplified representations of very complicated clouds, sort of inevitably introduces uncertainty into climate models. So one of the areas where that uncertainty is a particular problem is in attempts to use climate models to make statements about how future warming will affect extreme weather. One of the most striking examples of this are projections of the response of precipitation extremes to warming. So this is, rather than trying to answer the question of how much warmer Earth will get in the future, it's trying to answer the question of how much more extreme the heaviest rainfall rates will get given some amount of warming. So the way to read this plot is to focus just on these dotted lines. This shows the range among a bunch of different climate models in the response of precipitation extremes to warming, so measured as a % increase in the intensity of the heaviest rain rates per Kelvin of warming. So 1 Kelvin is the same as 1 degree Celsius, is a bit less than 2 degrees Fahrenheit. In the mid-latitudes where I live, where a lot of heavy rain is produced by relatively large-scale weather systems, climate models agree reasonably well. In the tropics, where most rain is produced by convection, and so represented in climate models by parametrizations, the spread is huge. It's hard to use this information by itself, at least, to say anything very robust about how most extreme rain events might change in a warmer climate. One thing I've been excited about, though, is work over the last decade on the initial development of climate models that do simulate convection. So there's not really any secret sauce behind these climate models. Other than that, we're just at the point now where we have computers that are powerful enough that we can run climate models globally over reasonably long periods of time, so years now, hopefully decades in the relatively near future, at a resolution that allows us to simulate thunderstorms, using the equations of fluid dynamics rather than using some, sort of a human-designed cartoon representation baked into a parametrization. So this animation is model output from a convection resolving climate model developed at GFDL, so the modeling center in Princeton, where I did a postdoc. This is a simulation that I ran, but not an animation that I made, so I should give credit to Julius Busecke for designing the animation. The thing that I want you to take away is just that this is output from a model that's run on a global domain, but you can pick parts of the world, so the western coast of Africa, Central Africa, zoom in and see convective systems, so thunderstorms, forming and evolving in sort of exquisite detail. So these models, they're often called global storm resolving models by the people who work with them and develop them. They're sort of being developed with the promise that they might, for example, enhance our ability to model how clouds influence climate and climate change. So, in doing so, help us produce more robust projections of the rate of future warming. But maybe more importantly, might help enhance what right now is sort of fairly limited understanding of how climate change affects extreme weather, largely by virtue of being able to simulate extreme weather events with little level of fidelity that most climate models can't, and so improve our ability to plan for warming's worst impacts. The reality, right, is that these are relatively new models. It's not yet clear to anybody who works on them what their strengths are. One thing that is clear, though, is that U.S. federal funding is going to be crucial for understanding and realizing their benefits. So I've plotted on this map, put marks in locations where there are modeling centers with with mature global storm resolving models. The sort of working definition for mature that I'm using are just models that are mature enough to have contributed simulations to an intercomparison project that was run relatively recently. There are, I think, 12 of them scattered throughout the Northern Hemisphere. Fully 5 of them are in the US. So there's Lawrence Livermore National Lab in California, which gets funding from the DOE, NCAR in Boulder, which gets funding from the NSF, Stony Brook University on Long Island, which is a university and receives a lot of federal funding, the Goddard Space Flight Center in Maryland, which is funded by NASA, and GFDL in Princeton, where I'm based, which is funded by NOAA. So, to me, it seems just sort of self-evident from looking at this map that if you care about climate modeling and if you're excited about a new generation of climate models that do a better job of capturing some of the worst impacts of climate change and extreme weather events, that you should want to continue to fund these US modeling centers. I think I'll try to wrap up in about the next 5 minutes, but want to give you sort of a flavor of the work that happens at these modeling centers by talking a bit about work that I did on GFDL's global storm resolving model while I was based there as a postdoc over the last couple of years. So the motivation for this work, as seems to often be the case in climate science, was based on observations collected by a satellite mission funded by the US government. In our case, the observation that got us excited were observations of land-ocean differences in lightning flash rates collected by NASA's Tropical Rainfall Measuring Mission. So this mission was a satellite that flew from 1998 to 2013, was launched by NASA, had a sensor on it that could detect lightning. One sort of remarkable thing that you find when you look at data from that satellite is that if you make a plot of long-term average lightning flash rates, so that's what I'm showing here, areas in orange and yellow are places with very high lightning flash rates. Places in black are areas with low flash or low lightning flash rates. You see there's a sort of very clear contrast between continents. So these sort of glow in this image, and ocean, where evidently there's very little lightning. The way to interpret this image is basically just that lightning is an observable proxy for very intense convection. So you tend to get a lot of lightning in very intense thunderstorms. And so this, again, is probably intuitive to people who live in parts of the world where thunderstorms form. And so this observation suggests that there's something about land that means that convection over land is sort of systematically and significantly more intense than convection that forms over oceans. The question that we became interested in was, pretty straightforward. It's just whether XGIELD, so this is GFDL's global storm resolving model, could reproduce these observations. The reason for this is also pretty simple. GFDL or XGIELD is an example of a class of model that's pitched as a way to improve our understanding of the future of severe weather. If you want to use a model for that purpose, you'd better hope that it does a good job of capturing the processes that control the intensity of convective storms in the present day, and so testing whether or not the model produces a clear difference between the intensity of convection over land and ocean, motivated by observations like these, seems like a very straightforward but potentially very insightful test to throw at the model. What we found, so I guess in hindsight, maybe naively came into this project assuming that, well, great, these models have all the resolution you could ever want to simulate deep convection. They're run with a reasonably realistic representation of the land surface and the ocean. Like, sure, surely they must kind of automatically produce an image that looks like this. What we found when we began working with the model was something a bit more nuanced, which was that XGIELD, while it is capable of reproducing the land-ocean contrast and convective intensity that shows up in observations, it doesn't do it automatically. So I'll show simulated proxies for lightning flash rates from simulations we ran with two different versions of XGIELD. Version 1, so this is an experimental version that we ended up sort of cooking up with a lot of input from experts at convection resolving modeling at GFDL after probably about a year of work, produces a realistic land-ocean contrast. So the simulated proxy for lightning is confined mostly to continents and doesn't appear as strongly over oceans. There's no, it turns out, guarantee that global storm resolving models do something like this automatically. So you can come up with a different version of XGIELD that, to most people seems equally reasonable, that does a much poorer job of producing clear differences between the intensity of convection over land and ocean. So the sort of what we ended up feeling like we got out of this was maybe not what we were expecting to see initially, which was some just kind of nice illustration of the strength of this specific convection resolving model. But rather something that emphasized the importance of, in our view at least, of using this specific observation, so observations from satellites of land-ocean differences in convective intensity as a constraint on global storm resolving model development. So I want to just wrap up quickly now by talking a little bit about sort of how I see this result fitting into the sort of broader landscape of support for model development, climate model development in the U.S. So it's, important always to be clear-eyed about the strengths and weaknesses of every model. And it's clear from the work that I've just showed you and work that other people have done looking at the first generation of global storm resolving models that they're not perfect models yet. This is, maybe shouldn't be surprising, right? They're very high fidelity simulations of a very complex system. And it's, all of the expertise that exists at US modeling centers aside, probably a lot to expect for these models to get everything right, on the first try. One of the things that I think is sort of remarkable about, at least historically, support for science from the US federal government, though, is that they're willing to fund science based on future promise and not just based on concrete, present day benefits. And developing convection permitting climate models, there are some clear signs of promise from the first generation of models, and there are also enormous potential benefits to science and society. So it's hard for me to put these two things together and come to any conclusion. Other than that, there's a clear need to retain and support the people with the expertise, or that have the expertise to realize this potential, and to make sure that future generations of climate models, provide as much value as past ones have. So I'll stop there. I'm happy to take questions if there are a few minutes left.
Amazing. What a great talk. Thank you so much. We got a couple questions, and hopefully folks in the chat will keep sending them in as we're chatting here. But I do want to highlight this because we've had a lot of folks coming in talking about convective systems, and they're referred to as anvils often, but this person pointed out that they also kind of look like the Star Destroyer, which I'm kind of ashamed I've never thought of before, but they're definitely correct. And now an actual question from this person, and perhaps this is kind of like picking a favorite child, but when you think about these modeling centers, either in the US or abroad, maybe talk about like the pros and cons of the different models that are out there rather than trying to define a most powerful.
Yeah. So I guess it's, this is going to sound like a cop-out initially. It's really not, though. I don't think that there's really a meaningful sense in which you can rank the relative power of different modeling centers, just because model development efforts involve so much exchange of knowledge between different modeling centers. And so it's, it's not even talking about different OAR, NOAA labs collaborating. The work that I just talked about, so this is work on X-Shield, was motivated largely by observations about lightning flash rates. So those were observations collected by a NASA satellite. It's based on a model that right now is being developed primarily at GFDL, but that runs on a dynamical core. So this is sort of the, the fluid dynamical framework for simulating large-scale flows in the atmosphere, that was developed partly at GFDL and NOAA and partly at NASA. That dynamical core now is used in X-Shield. NASA has their own global storm resolving model that shares that dynamical core. The way that I think about modeling centers is not in terms of sort of individual power. It's more a network of tightly interconnected scientific expertise that makes every modeling center stronger.
I think that's a very diplomatic way of answering that question. Apologies if my internet connection's being strange, but yeah, that's okay to pick a favorite. And we have a couple questions about sort of the data size used, but I sort of had a question for that. Extremely high resolution cloud, high resolution cloud resolving models. For like a specific domain, what kind of runtime are you looking at? Like maybe, for example, like the one that showed West Africa all the way to South America.
Yeah. Well, so this, what was it? This one. Yeah.
Mm-hmm.
I guess one thing to clarify is that this is not output from a regional simulation. This is output from a global simulation. We just zoomed in on Western Africa and the Atlantic when we made it. Runtime. So it's, a sort of like from the perspective of a human who, working on these models, it's sort of remarkable. Like when I was a postdoc at GFDL, ran month-long simulations. So these are not super long simulations, but they're long enough to collect pretty robust statistics about the sort of aggregate properties of convective systems in the tropics. And those, I could set a simulation up at the end of one workday, click go, send it off to Princeton's supercomputer, and come back the next morning and have it like sitting there ready for me to analyze. This is possible not because these simulations are cheap, obviously, but because we have extremely powerful supercomputers to run them on. But the reason that people are starting to think about running very high resolution models for climate prediction, as opposed to just weather prediction, they've been used for a long time, is that the computers that we have available to run them on are so powerful that the computational cost, although it's immense, is actually at this point reasonably manageable. But it's worth emphasizing that this is not like manageable running on a laptop or some relatively small department workstation. This is running them on state-of-the-art supercomputers that are funded, again, largely by the U.S. government.
Good to know. Thank you so much. And I think that unfortunately we have a couple more, but that puts us at time. So thank you again for dropping by and telling us all about this incredible research. It was great.
Yeah, thanks for having me.
All right. So we are just about into the 90-second hour, I think, even though the TV hasn't quite changed yet. Now it's gone. Okay, now we're in the 90-second hour. It's official. Welcome to 8:01 a.m. Here in New York, where I live. Excited to see all of you here. We still have an absolute banger lineup of talks coming up, so don't leave your screens yet. Couches, TVs, wherever you're watching this, maybe on your phone while walking the dog, which is what I'm going to do once I'm done hosting. Don't go anywhere. Wow, great, cool. So let me really quickly, before we bring on the next amazing speaker, give you all a reminder of what we're even doing here. This is the Weather and Climate Livestream. We have been going for 92 hours now since Wednesday, May 28th, and we're going to end later this afternoon in 8 hours when we've completed 100 hours of just sharing science as broadly as we could possibly imagine on this open to everyone live stream here at wclivestream.com/watch. But part of the reason we're doing this, aside from just sharing how freaking awesome all of the scientists are, is to remind people that this science needs funding. Unfortunately, doing this work isn't free. This is a lot of people's jobs, and we are creating benefit for the U.S. public and abroad. The U.S. has for a very long time been world leaders in weather and climate prediction. We developed the first computerized weather forecast. We had the first models of climate impacts of carbon pollution, and we have this incredible network of weather stations and weather reporting apparatuses and infrastructure that are used across the country to protect us from natural hazards, warn us when things are turning into disasters, and that those resources are even used around the world. Unfortunately, we've already seen huge slashes to a lot of those budgets, and it looks like there might be more coming soon, which is why we are asking folks to take some time to go to wclivestream.com/act. We wrote a script for you, made it really easy. If you plug in your zip code, it'll give you the numbers and names of your representatives, and you can give them a call, share some of the science you've learned today or yesterday or the day before or even the day before, and tell them why it's so important to keep funding this work. And just as a quick reminder, all of the things that speakers say are their personal opinions. Unless otherwise stated, they're not representing anybody. They're just here to share the cool work that they're doing. Alrighty. So with that, I'm going to bring on Becca Jackson, who's going to talk about where glaciers meet the ocean. Take it away.
Great. Thanks so much, Miriam. Thank you so much to all the organizers of this amazing event. I'm really excited to be here in the 92nd hour, final home stretch. This is really an amazing, inspiring event. So I'm really grateful to be be part of this. So I'm an assistant professor at Tufts University, and I'm an oceanographer. And in particular, I study the polar oceans, where the ocean comes into contact with ice, particularly glaciers and icebergs, like what you're seeing in this photo. This is a glacier in Alaska that flows down into the ocean. And I study particularly underwater melting of glaciers like this with robotic and autonomous platforms to get measurements right near the ice, where you can't go with people, to study how the ocean impacts the ice and how the ice impacts the ocean. And before I kind of get into the details of what we're doing and why, I'm going to start with a little bit of sort of big picture motivation about ocean-glacier interactions. And I should mention this, all the work I'm going to be showing here today is funded by the National Science Foundation. I'll be talking about sort of two different projects, one in Alaska, one in Greenland. And apologies in advance if you can hear little kids screaming in the background. It's Sunday morning. Let's see if I can advance the slides. Here we go. So big picture motivation. This is a NASA visualization of the Greenland ice sheet, where you can see ice velocities in color. And the basic balance of the ice sheet is between snow accumulation in the interior that becomes ice, and then it flows and sort of discharges at the margins. And these pockets of fast ice velocity are glaciers. So where you kind of see the blues and purples, those are areas of the fastest ice velocity where the ice sheet is being drained by glaciers into the ocean. And specifically around Greenland, it's often draining into fjords, which are these long, sort of narrow inlets that connect the open ocean to glaciers. And there's a variety of reasons we care about what's happening where glaciers meet the ocean. So for one, ice sheets and glaciers are shrinking, and when they shrink and dump additional fresh water into the ocean, that raises sea levels. So Greenland in particular, the Greenland ice sheet is currently contributing about a quarter of the current rate of sea level rise. And you can see this illustrated here on the left is a map. This is from satellite data from NASA showing the red regions are where the Greenland ice sheet has lost ice. As you can see, kind of all around the margins, losing substantial amounts of ice. And the plot on the right shows that sort of mass change over time. So about 269 gigatons per year. That's a little bit of an abstract number, but as I said before, it's contributing to about a quarter of the current rate of sea level rise that we see globally is coming from this mass loss in Greenland. And so we want to be able to project sea level rise in the future. We need to understand what's driving this mass loss from glaciers and ice sheets, and how can we understand the physics well enough to make projections in the future. And so this is one example of a plot showing sea level change over time. And the black line is the part of the plot where we have data showing sea level rise occurring over the past decades. And then the colored lines in the plot are projections of sea level rise based on different model scenarios. And the main set of projections here are kind of under different warming scenarios, different emission scenarios, how much sea level rise do we expect in the coming century? And you can see that depends a lot on how much we emit into the atmosphere. Greenhouse gases is going to affect how much sea level rises. But the dashed line here shows kind of a different modeling scenario, which actually it's kind of in the same dark red color, but you get a lot more sea level rise in our model projections if you include sort of some poorly understood ice sheet dynamics. And what this is illustrating is that understanding the kind of physics and processes that drive ice sheet change are sort of poorly understood, and that creates big uncertainties in our projections of sea level rise. And so if we want to be able to make good projections for the future and be able to plan around those, one piece of this puzzle, and this, I should say this is one of many pieces, but the piece that I focus on in particular is ocean-glacier interactions. So how glaciers in the ocean interact affects how ice is lost and how sea level is raised as a consequence. And so when we think about ocean-glacier interactions, we can sort of think of both directions. In the first direction, how glaciers impact the ocean. Well, for one, as I just mentioned, when glaciers and ice sheets lose mass, that raises sea level. But it's also an extra source of meltwater, fresh water that goes into the ocean and can alter ocean dynamics at a whole variety of scales. And so this map you're seeing here shows the Greenland ice sheet on top of a sort of schematic of the ocean currents that bring warm water, kind of shown in red and oranges and yellows, warm waters from the subtropical North Atlantic, the lower latitudes up around Greenland. And this is a really important region in the global ocean circulation. And so when you dump additional freshwater, meltwater into the ocean, there's potential to alter not only kind of the local ocean around the coast of Greenland, but potentially the global ocean circulation that transports heat and really regulates our climate system. So kind of the impact of glaciers and ice sheets on the ocean is important for both sea level rise and ocean dynamics. And then in the other direction, we also care about how the ocean is impacting glaciers, because there's growing evidence that as the ocean has warmed around Greenland, that has led to an increase in underwater melting, which has then triggered glacier acceleration and retreat. So that ice loss that raises sea level is also in part driven by the ocean, and in particular by ocean warming. This is something, though, of a hypothesis, a work in progress, because importantly, we have almost no direct measurements of this underwater melting, let alone how it's changing over the decades. And so our ability to kind of predict how glaciers will continue to accelerate and retreat and overall shrink in the future is really limited by a poor understanding of this underwater melting of glaciers and how ocean warming affects glaciers and ice sheets. And so if we zoom in to kind of what's happening, where glaciers meet the ocean, and I'm focusing here on systems that are kind of typical for Greenland, Alaska, Patagonia, what we call tidewater glacier systems that have a relatively vertical ice face where the glacier meets the ocean. And that's in contrast to around Antarctica. You often have big floating ice shelves, kind of floating tongues that come out into the ocean, extensions of the glaciers. But here I'm thinking about tidewater glaciers, shown first in the lower plot here is a satellite image of a glacier fjord system in Greenland, one of the ones I study, where you have glacier coming in from the right, the fjord, which is the long, narrow inlet that connects the glacier to the open ocean. And then the top here is a schematic of sort of the most important exchanges that are occurring where glaciers meet the ocean. And so you have two sources of fresh water coming into the ocean. You have where the glacier melts from above with the atmosphere. You have surface melt. It drains to the bed of the glacier and then enters the ocean as what we call subglacial discharge, sort of like a river, but coming in way below the ocean surface. And then we have submarine melt, which is where the ice is melting directly into the ocean. And in some ways, that's sort of like the holy grail here. If we want to understand how the glacier is impacted by ocean warming, we want to know for a given amount of warming in the ocean, how is that going to change the melt rate? And then how is that going to feed back on the glacier flow and glacier dynamics? So understanding these kind of systems really boils down to thinking about the exchange of heat and fresh water. So you have heat from the ocean going to drive melting of the ice. And then you have these two sources of fresh water coming into the ocean and potentially altering ocean dynamics. Okay, so one of my projects that I'm going to talk a little bit about here and give you a flavor for how we do this work is a question about what controls, how fast these glaciers are melting underwater, or we call this submarine melting. And our sort of some basic facts we need to know are, first of all, when the freshwater sources enter the ocean, they're buoyant compared to the salty ocean water, and so they rise and they form plumes. And that's sort of shown now schematically with that vertical arrow going upwards. That's the rising meltwater going along the ice face. And we know that melting, how fast the glacier melts, should depend on the near ice temperature, right? Warmer water should melt the ice faster, but also velocity. So the faster the ocean is moving along the ice face, the faster the ice will melt. That's sort of like if you have ice cubes in a cup of water, if you stir it, it's going to melt faster. If you can kind of get the meltwater away from the ice quicker, you can get more heat to the ice to drive melting. And so this melt really depends on sort of the small scale physics of the boundary layer where the ocean meets the ice. And if you kind of zoom in on that, the focus of one of the projects I'm going to show is really trying to understand the along ice velocities from plumes, but also from other kind of modes of circulation that drive velocity or kinetic energy along the ice face, and how that controls the transfer of heat across the kind of boundary layer between the ice and the ocean. But importantly, we have all these sort of theories, models, parameterizations for this melting and ocean glacier interactions, but we actually have very few observations to test these. And so a big focus of my work is getting observations right near glaciers in order to test our models and theory for melting, so that we can ultimately answer these questions of, as the ocean warms by a certain amount, how will that change the melting of the glaciers and ultimately the ice loss from glaciers and ice sheets. Okay, so to get at some of these questions of what's happening right near the ocean glacier interface, I have two sort of ongoing projects, one in West Greenland on the left here, and the other in Alaska, Southeast Alaska at LeConte Glacier. And so I'm going to focus first on a little kind of preview highlight of how we do fieldwork in Alaska, trying to get at these questions of what is controlling the melt rates and how can we better understand the physics near the ocean ice boundary. And in both cases, in both of these projects, both funded by the National Science Foundation, we use various autonomous platforms to collect measurements right near the glacier where you can't go with people, right? These glaciers are breaking off icebergs, making it hazardous to go kind of within about half a mile, quarter of a mile of the ice face. And so if we want to get these measurements right where all the action is occurring, we need to use autonomous or robotic platforms. In Greenland, this is what we call a hybrid ROV, remotely operated vehicle, that we kind of is tethered to the ship and drives half a kilometer up to the glacier face. In Alaska, which I'm going to start talking about, it's a whole fleet of different vessels, both at the surface. ASV stands for autonomous surface vessels, and then also subsurface ROVs, remotely operated vehicles, measuring. What I'm highlighting these schematics here are sort of the observations that I'm focused on, which are measurements of velocity from ADCPs, the blue and yellow kind of icons. So that's measuring ocean currents and velocities. And then the red icons represent measuring the temperature, salinity, and pressure, and sometimes turbidity or muddiness of the water. Okay, and so why we use all these robotic autonomous platforms is illustrated by video like this, where you have, this is actually a relatively small iceberg calving event, but gives you a sense for why we don't go up there with people and why we really rely on kind of really new approaches to use autonomous and robotic platforms to get measurements right where the ocean is meeting glaciers. And so our approach, this is Alaska with LeConte Glacier in the background. We go out in usually kind of a medium small boat, usually a local boat from Southeast Alaska. And we sort of use that almost as like a floating hotel to deploy our autonomous platforms from. And this is part of the team here. And one thing I'll emphasize is this is a big collaborative interdisciplinary project where I'm talking about sort of one component of this project that I'm focused on, which is kind of measuring the velocities and water properties along the ice face. But it's a big interdisciplinary team involving glaciologists, engineers, other ocean physicists, studying kind of all parts of the glacier ocean ice system at a variety of scales. From, if anyone was tuned in yesterday morning, Jonathan Nash was talking about sort of the small scale measurements we've collected from this project. So right at the boundary layer scale, drilling melt stakes into the ice face. What I'm talking about is slightly larger scale, kind of the currents that drive transfer across the boundary layer at a slightly larger scale, but all in the kind of very near glacier region. So we go out, a team of, and another thing I want to emphasize is that these teams span from students through seasoned oceanographers and glaciologists. So kind of all experience levels, and a really important part of our funding is not only to do the science, try to push the envelope on cutting edge research, but to train the next generation of scientists. And so on this project, we've had both undergraduate and PhD students heavily involved with, the development of instruments, the science itself. And that's, a really, really crucial part of this funding is not just doing projects, but training the next generation of scientists, and retaining that talent is super important in these difficult times. Okay, so we go out, we're on this boat, and you can see sort of on top of our larger boat are a bunch of smaller boats, a little bit hard to see, but in red and in gray are the two little red boats you might be able to see in the deck of the bigger boat are autonomous surface vessels. And then the gray boat there is another boat we kind of launched from the bigger boat to make measurements slightly further from the ice face. And so this is actually kind of showing two different generations of the autonomous surface vehicles. The kind of original version looked sort of like a kayak. The newer version is a RIB, or a rigid hull inflatable boat, with a whole bunch of instruments, particularly that measure ocean velocity and water properties. And we deploy it from the bigger boat. We stay a safe distance back with all the people, and then we send these right up to the ice face. And so what that looks like here, this is the kind of kayak version of the boat approaching the ice face. For scale, you can maybe make out some of the little black dots in the water. Those are seals. And what you're also seeing here is the turbulent plume boiling up to the surface. So that's all the meltwater that's draining at the bed of the glacier, rising up along the ice face, and kind of boiling up to the surface in these billows that you can see. Okay, and then this is actually now the newer version of our surface vehicles. And I should mention, I think this was on the slide before, but these are all developed at Oregon State, led by Jonathan Nash, this fleet of autonomous both surface vehicles and subsurface ROVs that we've been using in this project. And so what you'll see in this video is another illustration of why we don't go up here with people. The beginning of a calving event, an iceberg breaking off, and then you'll see we're following this all closely on the ship. We're probably freaking out right now, and you'll see the boat turning around and running away from these large waves generated by the iceberg calving. But amazingly, we've not lost any vehicles in all this near glacier surveying. And we've been able to kind of get an unprecedented view of what's happening, not just at the surface. Kind of what we've already known is, this sort of picture. You have these plumes boiling up to the surface. They're carrying a lot of sediment. You can sort of see that they're muddy. But what all this surveying has let us do is see what's going on beneath the surface. This is just a little sampling. I'm kind of going very, very light on data here. So this is the most complex plot I'll show you. It is pretty busy. But what it's showing is how we're able to collect measurements of the velocity right along the ice face. In this particular plot, I'm highlighting some data of kind of the energetic plume that rises along the ice face. On the left is sort of a map showing the high density of observations we've collected with the glacier in white. And then all those tracks are kind of where we've driven our various vehicles and where we've made water property profiles. But on the right, what I really want you to focus on is these 6 snapshots of velocity. And so basically each of these little panels is one time that the boat drove over the plume. And then what you're seeing here is beneath the surface, the structure of the velocity, the vertical velocity in particular, where red is upwards velocity. And so you're seeing a signal of that upwelling plume that rises along the ice face and is driving melt. And what we're finding is sort of energizing velocities across the whole terminus. So one approach we use is surveying, kind of what I just showed, where we drive the boat. We're out there for a week or so, and we drive the boat around again and again and kind of get what we call synoptic surveys. But we also want longer term measurements over weeks, ideally months, years longer, to capture the variability in time. And so one approach we've developed is autonomously deploying moorings. So these are instruments that you put out, kind of anchored to the seafloor over longer periods of time. And we've sort of developed these new methods to get these moorings right near the glacier where you kind of can't deploy them in standard ways. And so what you're going to see here is a video showing the autonomous boat towing a barge. And the barge is carrying basically an anchor and a set of instruments. And it drives off from the boat. And then it's going to drive up to the glacier. Which you'll see now in the second video. Since it's early in the morning, I'm going heavy on the videos here. I hope they're coming through okay on the live stream. But what you'll see here is the little autonomous boat towing this raft or barge that has basically a trapdoor in it. And so what you're going to see in a second is the trapdoor open and the instruments fall down to the seafloor and sit there for several weeks to measure sort of the variability in front of the glacier. And so the instruments are now in the water, and then the anchor is pulling them down, and you'll see them sort of disappear, maybe if it's big enough, down to the seafloor. And we actually are then able to recover the instruments using acoustic signals that sort of, when they tell themselves to release, and they float up to the surface. And so what we can get from this sort of picture of putting moorings out that stay there over weeks or ideally longer in future deployments is sort of the variability. And one big signal we saw that we hadn't observed before until we were able to do this was the signal of high frequency internal waves. So these are waves kind of within the ocean that are actually excited by the plumes that I mentioned, but then propagate across the whole ice face. And so what you're looking at here is a plot of depth versus time, again, vertical velocity. But what you're seeing is not just that steady rising plume, but an oscillation up and down of these internal waves as they propagate across the terminus. And this is some work led by a former postdoc of mine, Jesse Cusack, who's now a professor at Oregon State. And he compared the observations from that mooring with an LES model, type of really high resolution model, and showed kind of the origin of these waves being the plumes and how they importantly enhance melt across the whole terminus. It's sort of a process that we hadn't accounted for before that drives velocity, kinetic energy across the whole ice face that plays an important role in enhancing melt. And so this is just kind of like a few little snippets of what we're doing in this project, but it's an ongoing effort towards sort of a revised understanding and a revised model or parameterization of submarine melting. And what we're finding is that the melt rates are much higher than our standard theory or parameterizations predict. And so we're kind of investigating a whole bunch of different threads related to how can we build a better model or parameterization for melt to put in our larger scale understanding of ocean glacier interactions. But at least one of the pieces that I've kind of alluded to here is that we need to account for the velocities, not only of plumes, kind of as you can see in the middle of this schematic, but also waves and eddies and recirculations, kind of other modes of circulation and velocity across the whole terminus that energize the boundary layer and drive melting. And then I'll just end, if I can get to one last slide. Unfortunately, I don't have time to, I'm happy to show a little bit about Greenland. But I just want to end, putting this back in the bigger context that these small scale processes right at the ocean glacier interface are important for these bigger questions about what is the ocean's role in driving glacier retreat and sea level rise, and the impact of all this increased meltwater on ocean circulation. And so kind of getting these small scale processes right, testing them with observations is one step towards kind of improving our ability to model the evolution of both the ocean and the ice sheets in a warming climate. So I will stop there, and I'm happy to take questions.
That was incredible. The photos and videos you were showing, I don't know if you're looking at the chat at all, but people have been very much appreciating them. Here's like one comment that I saw a minute ago. And I also want to say, like, I don't do glacial stuff, but I've seen some of the things you were talking about in cartoons. I've never seen like video footage of them, like the subglacial melt turbulently coming up to the surface. That was incredible.
Yeah, it's beautiful. It's a very it's a fun, dynamic environment to work in, and yeah, I love showing the videos because it really gives you a different flavor on what's going on by actually seeing the footage.
Yeah, it makes it so much more real, literally. And I know this question was kind of answered for the people in chat, but maybe we can kind of memorialize it in the live stream. But a lot of people are asking, what happens to the land masses when all that ice melts off?
Sorry, say that again. What happens to the
land mass? Basically, they're asking about isostatic rebound.
Yeah.
That physical process.
Yeah, exactly. So when the ice melts and reduces its mass, the land does rise up and rebound. And so you actually often get a little bit of locally, and we get sort of two, so you can have you have very interesting spatial patterns of sea level rise, both because of the rebound and also because ice is a mass that exerts gravity on the water around it. And so when you shrink ice and it loses mass, not only does the land rebound a bit, but the gravity field from the ice is reduced. And so you can actually get dropping sea level locally around shrinking ice sheets and extra large amounts of sea level rise kind of on the opposite side of the planet. And so, yes, exactly. That's a really important process that other people study in great detail. And it's really important for kind of understanding the I'm talking mostly here about the ocean glacier interactions, but the solid earth interactions are really important and interesting as well.
Yeah, definitely. And there's a whole long conversation, people going on about, how it's affecting different sea level rise around the globe, as you just mentioned. So
yeah,
thank you for kind of explaining that processes. We have another kind of, basic physics processes question, which was what makes the ice so blue?
Oh, yeah. So yeah, I'm definitely not a glaciologist. So
sorry,
but let me see if I can get this right. Oh man, I'm gonna get this wrong, I think.
It's okay. We can also skip it if you prefer.
So definitely, let me see at 8 in the morning if I can get this right. So definitely the optic, like the color of the ice is very dependent on the bubble content. So glacial ice contains air bubbles, trapped air bubbles that forms at the surface. But actually so kind of typical glacier ice is more white when it has a lot of bubbles in it, I think. Oh my gosh, someone correct me if I'm getting this wrong. But you do get basal ice that often is has a different color because that ice is actually melted at the bottom of glaciers and ice sheets and lost kind of its bubble content. And so it has very different visual color. But for the most part, I'm not answering that question very well. We can get a glaciologist on here to give you a better answer.
Okay. Well, we'll have to ask the next glaciologist that pops on. I'm sure we'll get somebody. I think, let's see if we maybe have, you kind of skipped over some of your Greenland conversations, but we did have one person asking how many glaciers have you been to and if you have a favorite.
Oh, that is a great question. I think I've worked in 9 different glacier fjord systems. I have to say probably the first one I worked at has to be my favorite. So it's Helheim Glacier and Sermelik Fjord in Southeast Greenland. And I think just, it's the first glacier fjord system you go to is just like, it's such an experience. And I spent my whole PhD working on that sort of one system. And, since then I've branched out and I work across a bunch of different systems, but I think my first love is Helheim Glacier in Southeast Greenland. But they're all great.
Yeah, it's kind of like, the first time you get that, someone was saying that religious awe of seeing glaciers at first. It looks like our next presenter is having a little bit of trouble. So if you don't mind, I'm going to keep throwing all these questions because there's so many.
Yeah, we can even look at some Greenland videos if anyone wants to see.
Oh my gosh, that would be amazing. Maybe while you pull that up, we can this person's actually more kind of like the bigger picture climate change sort of situation, where we're at with emissions. Is our best case scenario kind of to try to stop retreat now, or is it possible that the glaciers can start to grow back?
I think definitely the priority now is slowing our emissions to reduce warming, to reduce the retreat. I think that's like by far kind of where the priority should be. It is it's the difficult path, but it's the straightforward path that if we reduce our emissions, we know we will reduce warming, both of the ocean and atmosphere, and that will reduce the retreat of glaciers. And I think what we're learning kind of through a lot of this research is how both the atmosphere and ocean play this important role. And they're really linked. Like one thing I didn't have time to kind of get into the details of is like the underwater melting is not just a function of the ocean temperature, but it's a function of all that fresh water draining at the bed of the glacier. And that is due to atmospheric warming or atmospheric temperature. So kind of the underwater melting of glaciers is really linked to the air temperatures as well as the ocean temperaters. And so it's all, this is sort of a common theme when you study any part of the climate system and you realize how tightly coupled the different components are. And so, yeah, definitely I think the best path forward here is reducing our emissions to reducing warming, which then will slow the retreat. And the part that I didn't actually get time to talk that much about really at all is the kind of role of sediment. And so thinking about processes that can slow the retreat and potentially help glaciers build back is actually the role of how glaciers transport. Actually, if I can, if we have time, I think
Let me jump
Whenever the
in.
next speaker comes on, feel free to cut me off. But while we're hanging out, the kind of part I didn't get to talk about, but actually is very relevant to this question, is the role of sediment. So the plumes that drive melting also transport sediment. So from at the bed, the glacier erodes the bedrock underneath it and generates sediment, and that is transported by all this fresh water into the ocean. And then when that sediment comes out into the ocean, it accumulates into what we call moraines, kind of underwater sills that you can sort of think of as like speed bumps to the glacier's flow. I mean, that's sort of an oversimplification, but moraines can play this important role in stabilizing glaciers or slowing their retreat. And so adding in the sediment dynamics to our understanding of what's happening at the ocean glacier interface is really important for kind of, again, being able to build these more accurate models of how glaciers and ice sheets will evolve in a warming climate.
Amazing. I'm glad you got to share that. That's so important. It looks like we have our next speaker is ready. So I'm going to say thank you so much for answering all these questions and your wonderful talk and those incredible videos. That's perfect for this medium of a live stream. I really appreciate you taking the time.
Oh, well, thank you so much. Thanks for having me. And, great to be here. And I'll check out the chat more too to see if any other questions I can answer.
Yeah, feel free to get in there and answer some of their questions.
Great. Thank you.
All right, so we're now it looks like everybody's ready to go. So real quick before I introduce the next speaker, as a reminder, my name is Miriam. I'm a PhD student. This is my dog, Darcy, and we're just here to remind you that we have set up a amazing way that you can support all this incredible science you've been hearing about. You can go to wclivestream.com/act, right around Darcy's nose, and call your representatives, tell them why what you're learning about is so important, how useful it is to our understanding of the climate system and our weather forecasts, and let them know that, when it comes time to vote for a budget, vote for one that supports science. All right, so with that, I'm going to have Dr. Amy Clement join us. Hello, hi, welcome.
How are you? Can you hear me?
Good, I can, yes, great. So hold on, I'm kind of inhibited, so I can't quite get to where it says what your talk is, but you're a professor at University of Miami, and you are going to talk to us about heat waves or heat research?
Well,
yes.
Yes, heat research, not waves.
Not waves, right, sorry. Amazing, thank you so much.
Yeah.
I'll let you go right ahead.
Okay, let's see. Can you see this?
Yes.
No? Okay, and it's in presentation mode?
Yes. Looks
okay.
Great.
I guess can't see my notes, but you all anticipated that was going to be an issue, right?
Yeah, sorry.
Okay. No worries. How does this look?
I can see your kind of PowerPoint window, not the presentation mode right now.
Okay, hold on. Let me just put it into full on mode there. There you go. How's that?
Perfect. Yeah.
Okay, so I know you said to do an external monitor, but I'm actually not at home. I'm in DC right now. I'm here for AGU's Days of Action. And I'll be meeting with representatives from the state of Florida later this week. And so I'll start to talk. I'm going to shift gears from the last speaker, which was it was amazing, fascinating to see such great science happening at 8:30 in the morning on a Sunday. Yay. And I'm going to shift gears to the other side of the temperature spectrum and look at heat. And I'm going to focus in particular on work that's being done by an interdisciplinary team that includes myself as an atmospheric scientist, along with a collection of social scientists who together we're looking at the heat hazard in Florida and advocating for a different perspective about heat, because Florida is a place where actually heat does not come in waves. And I'll try to make that argument to you today. So let's go. So this is a picture. It's a little bit dated. It's from the EPA from 2016, and it shows the estimated excess heat attributable deaths. So in a place where in the northern mid-latitude cities where heat during the summertime, it can be persistently warm, but there are extremes of temperature. We saw in places like Portland, extremes of temperature in like the triple digits, which were extremely unusual. I'll come back to some actual data on this. But it happens at a discrete time. And so using epidemiological methods, you can actually go ahead and look at the impacts in that period of time or shortly thereafter and get a sense of how heat is impacting people. Now, if you look at this, what you see is that the number of excess heat attributable deaths in Miami is actually 0. And this gives you the impression that heat is not a problem. We're perfectly well adapted to it. And so don't worry about it. And this perspective is borne out actually in our local mitigation strategy, which is looking at hazards across the city or across our county, Miami-Dade County. This can include everything from hurricanes to pandemics to major incidents. And so this is looking at the hazards and coming up with a strategy for the whole community to look at to approach these various hazards. And when they looked at heat, what they said was that, well, if we look back over the last, this is a report, this is the strategy from 2020. If we look back over the last 70 years, there's only been one extreme heat event reported. And during this, there were some modest impacts, and there was no property damage, no crops, efficient air conditioning systems of South Florida and are keeping people cool. And the power company said there was no problem with the surge. And so due to the low impact of this hazard, they said heat will not be considered further by the local mitigation strategy at this time. Now, meanwhile, a little bit more context. So when we talk about extreme heat, every NWS, National Weather Service station, has a different definition of what is extreme. And in the Florida hazard offices, they use a statewide metric, or they have up until 2 years ago, use a statewide metric where you would get a heat advisory if the heat index, so that's a combination of temperature and humidity, exceeds 108 degrees Fahrenheit. And this is a picture from NWS of the heat index of these different levels. You can have caution, extreme caution, danger, and extreme danger. And below caution down here with relative humidities in this range and temperatures in this range, 80 to 90, and relative humidities, that there's no problem. But when you start to get to caution levels is when they start to say that people should start to be aware of the kind of hazard, of the kind of effects that heat can have on your health or on your on infrastructure. So when the heat advisory exceeds this level, an alert goes out to your phones. And I think many people are familiar with this approach that's done all across the entire US and even globally as well. Now, the interesting thing about South Florida is that this heat advisory actually was only exceeded once, as I showed you in the last slide, over a 70-year time period. Now, it seems sort of strange because everyone thinks of South Florida as being a hot place. But it actually turns out that the temperatures and humidities never get actually that extreme. And it's actually because the temperature never gets that extreme. Triple-digit temperatures have never been recorded at the NWS sites in South Florida. So of strictly temperature. Now, when you add humidity into it, it changes the story, and now we'll come back to that. So this begs the question of, are these dangerous levels of heat actually rare in South Florida, as suggested by the official monitoring sites? So in order to answer this question, we took an approach, and this is a collaboration that is published in the Journal of Applied Meteorology and Climatology. We took an approach where we actually engaged citizen scientists to help understand what heat looks like in the community where people are. So the NWS site is at 2 meters, which is actually, higher than most people are breathing in air. And it's also at a place that is well ventilated and outside, outside the urban area. A little bit outside the urban area. And so what we did was we asked people, we took these things that are called iButton sensors, and we had a number of different deployments where we brought community members in, gave them these buttons and a set of instructions, and they were able to report back on where they placed the buttons, and put them out in the community where they were living. So this would be parks or bus stops or public spaces. We also asked them to distinguish between whether they were placing it in a site that had a tree canopy versus one that was in full sun exposure. So we have a collection. This has actually been an ongoing effort, and we have some new papers coming out with data since this time as well. We've put them across the county. These are the locations, and underneath here is the greenness. So it's a measure of how, like where there are more green areas. This is Miami-Dade County. Here's the airport that I mentioned. This is a kind of heavily urbanized downtown area. This is an agricultural area in South Dade. So you can see we put them in a range of different places that are have different levels of greenness. This is what we found. This is just a snippet of a period of time looking at maximum and minimum temperatures. And first, let's focus on the minimum temperatures. So this is the airport. This is the airport shown here. And in the bottom plot, let's look at minimum temperatures. So airport shown in black. And if you overlay the iButton data and either the sunny or the shaded locations, you see it tracks the minimum temperature very, very well. Except when you get down to these cold extremes in the winter time where the instruments don't go measure those cold temperatures. But if we look at the maximum temperatures, it tells a pretty different story. And that is that the maximum temperatures can be very significantly higher in these locations than they are at the airport station. And I'll show you in the next few slides exactly how much higher. So this is a picture. So if we take all of the iButtons that are out there in the count and they are across the whole entire county, and we compare them with that day's minimum temperature. So each dot is an iButton in a day. And what you see here, this is what's being measured at the airport, degrees Fahrenheit. So it's measured at the iButton for that day. And you see a pretty good correlation, one-to-one correlation. There's a lot of scatter that we believe is meaningful scatter. It represents urban heat islands and measures of greenness and even anthropogenic heat that can, like heat due to cars and AC exhaust that can really drive up the heat in certain regions. That's all meaningful scatter, but on average, there's a good representation. But if we go to the maximum temperature, what you see is that there's a significant offset, so that across the entire county, there are places that are cooler than the airport, but in general, the temperatures are much higher in the county at any time at any kind of season, or whether it's the winter or summer. Temperatures are higher in across the county. And you can see that even for the sunny region, for the sunny places and where there's little shade, that the temperatures are even that much higher at those locations. Now, a few of the iButton sensors had both temperature and humidity. And so from that, we were able to combine heat index and compare it against what we were learning, against the thresholds that we had for advisories. So you see here on the x-axis is the heat index from the airport. And again, this is measured at the NWS station. And here are the iButtons. Now, I've shown here the threshold 108 for the heat advisory level. And so let's say 108, you see at the airport along the x-axis here that there weren't any advisories that in this period of time. There weren't any advisories issues, and that's consistent with no heat indices exceeding 108. So that's why there's no data over there. Now, if we draw the same line here, 108, you can see that there are a number of locations, days and times, when the heat index does exceed that level in the county when it would have been missed by the official recording station. So again, when the temperatures exceed these values, when you add heat and compare it with the threshold, that we see that heat is in the community is a lot there. These dangerous occurrences of dangerous heat are actually not that rare. And I'll show you here how rare they are not in a moment. So looking backward in time, if we take various thresholds, 108 is here shown here in bars, or in black bars. Red is 106. But basically, the point is, if you get 108-degree threshold, you see it's very rarely exceeded over this period of time. And you can lower the threshold somewhat, and you could start to get days per year that will be exceeding that threshold. I'll return to that in a moment. But the official version, according to the official version, heat advisories really almost never get issued in South Florida. Now, if you take that, if I go back to this relationship between airport heat index and I-button heat index, and I compute based on this regression line an average value for what was missed, what was the airport missing in terms of the heat that people were experiencing in their daily lives. This is the number of days that would have exceeded this heat threshold of 108. So simply correcting for the fact that where people are living is hotter and more humid, and if we calculate the number of days, it is nearly a third of the year. And that number of days is going up at a rate of 6 days per decade. So this is an increasing heat hazard as well, or it has been over the last 70 years. All right, so where does this leave us? Now I'm going to pivot a little bit and talk about, well, one more thing, which is that this data actually helped. We collaborated with the National Weather Service's hazard office in Miami, Florida. And in 2023, they decided to do an experimental test by lowering the heat threshold to actually from 108 to 105 in order to be able to see how does the community react when we start issuing thresholds, issuing advisories, because it hadn't happened. We didn't have experience with it. And that's a bit of another story, which, of what happened. But I think it did, in general, raise the level of awareness that even though he wasn't getting to that 108-degree level, it is a problem for people that, in order to keep people safe during the summertime, I need to be aware of this as a hazard. And the awareness went up a great deal as a consequence of this particular change. I think it represents a really good example of where researchers partnering with the local government and the federal government are working together in order to have the best set of tools for helping their communities. Now, zooming out to my second point here, which is that thinking about heat waves, and I made the argument that heat doesn't come in waves in Miami, and this is an example of where how this is an example showing this. Is that the right way? And my answer to this is no. I'll just give you a hint. So if we look at this is the climatology of heat index that is made by my colleague Brian McNulty. And what you see here is the average high heat index. It's ramps up and starting in May, and it stays high for basically an entire season. And just for reference, this 90-degree threshold is where the National Weather Service would issue a caution level, not an advisory level, but a caution level. And you can see that it goes past that caution level every day. The average high is higher than that 90 degrees heat index value all the way from May until November. And so this really is led to our, this data really from the National Weather Service really helps us make an argument for the fact that heat should not be managed as a wave that comes and goes from week to week, but actually just persists for an entire season. And in fact, that's the approach that the local government has taken to talking about heat as a heat season. Now, just a few more points, because I know I don't want to run out of time. You can think about heat as being an acute versus a chronic situation. And you can see that on the left-hand side, this is that example I gave of Portland, Oregon, where there's, temperatures that heat indices have got to, I think, something like 120 during the heat wave several years ago. But you see they're very rare, these danger values. And if we contrast that with the summertime heat index in Miami, you can see that the entire summertime is in caution, extreme caution, or danger. So this is, again, our argument that we should not be managing heat as an acute thing, that we can just stop the bleeding, save the patient. Instead, we have to manage it as a chronic phenomena that impacts people throughout their lives. And I will say this is not just a characteristic of Miami, but actually could be considered a characteristic of the global tropics and large parts of the United States as well. So on this picture, you see the number of events of heat waves defined by the WMO definition of heat exceeding a 95 95% exceedance of heat for several days. And you can see that's a characteristic of the northern latitudes in particular. But most of the tropics, the colors here of the number of events are basically, they're black. In other words, there's been no measured heat extremes in this areas. And on the color plot, dots here show the average days above a heat index of 90 degrees Fahrenheit, so that caution level. And you can see that in all these regions where WMO definition would indicate that heat waves don't happen, these are the places where heat seasons, or even the entire year, is that heat is what we call a chronic phenomena. And this is just a picture of where, so again, these are basically the zonal average of the plot I just showed, which is the number of days with heat index exceeding a 90 degree threshold. And you can see in the tropics, it's a large number of values over 90. And here's the heat wave data, emphasizes the higher latitudes, but in between you can see in blue, these are the stations that are transitioning from an acute heat, which just comes and goes, manage it with emergency management, and then transitioning into places that is actually chronic. And you can see that map, the little blue X's here are the stations that have become chronic over this period of time from 1993 to 2023. Our chronic definition is having a number of days with heat index maximum over 90, so an entire season. So I think I'm out of time, so I'm going to just end with this final slide and some key takeaways. So heat impacts people in ways that extend throughout their lives for months at a time in a place like Miami. That means at work, at home, and in transit. And what I mean to show here is that I have some more data. I don't have some time. People can ask questions about it. Is that whenever you look at the heat hazard that's out there, there are a lot of people at risk, and it impacts them not just for a moment in time, but it impacts them all day long and sometimes for months at a time. And so I'll just get to my key takeaways, which are that our research shows that dangerous levels of heat occur throughout this heavily urbanized subtropical region, even when official reporting stations do not indicate a threat. Many regions of the globe, heat is not an acute or episodic phenomena, but instead a chronic stressor. And northern subtropical regions are transitioning from acute to chronic heat hazard, especially in the United States. Chronic heat affects people both indoors and outdoors for months at a time. If people have questions, I can answer. I can give you some data on that. And then we offer novel research framework for keeping people healthy and safe, and for a thriving economy in an increasingly hot and humid subtropical region. So I'll stop there and turn it over to questions, and hopefully I can see you now. Yes, I can see you now.
Yes. Amazing. Thank you so much. What a wonderful talk, and like really highlighting, some of the issues with how we define things and how that has policy ramifications around the world. There's a bunch of questions. We'll try to get through as many as we can in the next 2 minutes or so. But I think let's start, back at the beginning from sort of the tools that you're using. Are those button sensors, do they just do temperature, or are they able to show other kind of measurements like humidity?
Those actually, I'll come back to that. Those they're just temperature and humidity. I mean, you can get them,
Can you hear me?
and they're very low cost also. There's, always as ever with data, there's a lot of time and effort that needs to go into calibrating the instruments ahead of time, and then doing quality control on the post-processing side. So even though they're low cost, I think they're like $25, or maybe that you can, there's somewhere between $25 and $100 each. They're low cost, but there is a lot of labor around them. We were able to take advantage of the citizens that participated in this, and they, for some of the labor of actually placing and retrieving the eye buttons. But there are a lot of other low-cost sensors that are coming online for things like air quality. So purple air sensors, I'm sure people know about that. There are a number of, you can partner with them in order to get, location or sites wherever you want. We also partnered with WeatherStem. We have a number of different sites on our University of Miami campus, and that they measure a whole host of things. If you check out their website, solar radiation, winds, temperature, rainfall, etc. So it's like a little Met station, and I think you can partner with them to get those set up as well if you're interested. Happy to answer any questions along those lines by email as well.
Amazing. Well, I think we just hit 9 o'clock, but thank you so much for joining us. If you have a chance, there's a bunch more questions if you want to open the YouTube stream and go reply there. I'm sure people would appreciate it. Otherwise, people can reach out to you via email. And I think also because my internet is lagging, we're going to transition over to the next host as well. So I'm going to say
thank you so much for doing this. It's wonderful.
Yeah, thank you. All right, hi, Mara. Please rescue me from my internet collapsing around me.
Miriam, and hi everybody. Thank you to the last speaker, and thank you all for joining us here in hour 93 of the Weather and Climate Livestream. Only 7 more hours to go today, so we're nearing the end of this amazing event. But before that, we have another great hour of weather and climate science for you. And in just a moment, we'll be speaking to Christopher Wirz. But before we begin, I want to remind you why we're here and why we're doing this. I think the last speaker really emphasized for us, and our upcoming speaker will as well, really just how important weather forecasts are and how important it is to consider both weather and climate forecasts, particularly in these times of changing climate. And the US really has been a leader. US scientists developed some of the first computerized weather forecasts. And a lot of that was done in government labs or government labs in collaboration with universities. And these computer models are really essential to predict the weather for the next couple of days, but also to understand the impact of climate and greenhouse gas pollution on really long time scales. And they really do have concrete benefits for people's lives. And a lot of the science is done in an interdisciplinary way that considers not just the science, but also the impact and how to communicate that impact. This is only possible with decades of funding of science. These are hard problems that we've worked out over long periods of time. Before we begin, and I hand it over to Christopher to really talk about this in much more detail, I just want to highlight that the administration's proposed budget, which is being considered now by Congress, has far worse cuts than what we've already seen to both the National Science Foundation, to NASA's Earth Science budget, and particularly to NOAA's research arm, all of which are foundational to the advances that we've seen, and really to maintaining the quality of weather and climate forecasts that we have now, not only for research, but also for the next generation of scientists that will cut critical programs that were essential for me and for many of my students and colleagues in training them to be able to take on this research, maintain it, create advances that will have real impacts in people's lives. So if you like what you see here, if you want to take action, please use the link on your screen or what you see scrolling below to contact your representatives and tell them to save our forecasts, to keep the lights on for weather and climate science so we can really continue all of this work and this amazing work that does have real impact. So please spread the word about the live stream as well. And with that, I'll introduce our first speaker, Christopher Wirz.
All right, good morning. Hopefully you can hear me. Give me a thumbs up if I got it.
Yep.
Okay, perfect.
To hear from you.
All right, so thanks for joining the 93rd hour. It's impressive that y'all have organized so much great content, and I appreciate you having me and organizing all this great stuff. I'm coming to you from Colorado, so it's a nice early 7 o'clock for some good social science. And I'm actually at the National Center for Atmospheric Research here in Boulder, Colorado, and transitioning to the University of Illinois Urbana-Champaign in the fall. But like I said, I'm here more like in the personal context, not representing those organizations, but that's where a lot of this work has come from that I'm gonna build on. But what I want to talk about is something slightly differently, and Amy actually set me up really well for it. It's kind of the human dimensions of the systems, right, of science. And so I'm going to talk about social science specifically, which is what I do, and seeing how that can really focus on understanding the weather and climate systems and making sure our science gets to people that need them. And I put in climate in parentheses there because a lot of stuff I'll focus on is weather, but this applies also to the climate scales too. And so to start off, my plan is to go through what I do as a social scientist. So we've heard a lot from physical scientists and biological scientists, and I want to make sure kind of cover and give people an overview of what that is, because it's maybe not the most intuitive thing that people that study people. And then I want to talk about how that really fits into weather and climate research today, and then as well as what the benefits are of that work. Like, how does the public benefit from it, and what could some of these budget cuts have an effect on? And so my goals here, right? So with that plan, is that I would love for you all to walk away with an understanding and appreciation of what social science is generally, a pretty high level bar, but also then demonstrate why we need to continue to research on communication decision making related to weather and climate. So those are two big things. I'll revisit this at the end that I hope you walk away with. And so with that, I saw a few people do this, a little bit of background on what they do and how they got here, which I thought was really interesting. So I'm going to add those in. So my story starts where all great stories start, high school. I really was interested in science stuff generically, but also communication. So I was like, okay, I want to take the advanced biology class, but also be a really classic theater kid. And I moved that interest into undergrad at University of Wisconsin-Madison, thinking about science, right? So I want to do biology and environmental science and communication as like different majors. And so at the end of undergrad, a couple pandemics ago, Ebola was happening, and I was in this risk communication class. And I was really confused, like, why are people freaking out in the media about Ebola and not the flu? Like, the flu kills so many more people. Ebola has like 2 deaths in the whole country, and they're like pretty well contained. Why are we like every headline's on Ebola? This is so weird to me. And my professor of risk communication was like, well, let me tell you, we've got a lot of theory literature. This is what I study. We can dig into it. Let's do like a senior paper on this. And so I got really interested in that. Like, how do we think about risks in science communication, right? And so putting those two things together was really what I then decided to go to grad school for, like kind of the science of communication. So researching the actual processes and kind of decision-making systems behind communication. And so I studied pandemics because, Ebola was my undergrad, and then Zika was my master's, and COVID was my PhD. And then unfortunately, you can only study and live through so many pandemics at a time. And I was like, I really want to go back to my interest in environmental work. I'd done some things on different technologies. And so I took a postdoc at NCAR, where I've been working for the last 4 years, and really started digging into these weather hazards. So thinking about interdisciplinary risk in science communication is what I work on, right? So a lot of it's been around AI and weather hazards. And so that's what I'll be continuing doing as I move to the University of Illinois. So it's roughly where I sit in my background and how I got here. And so what that means is that I study these high impact science and risks, things like severe weather, winter weather, floods, that type of stuff. And I then look at it from a communication perspective, but I don't think of it as just like, we hand someone in the public information, right? The dissemination of information. I also think about how do we develop that information, right? So how do we work as a team of interdisciplinary scientists, like the last speaker talked about, and think about what is the information we're actually making and how we make it so that's actually helpful for decision making and communication processes. So all these related ways, like there's information that we make, and there's information that's helpful for decision making, and then there's also information we just need to share. So I think about all these different dynamics is where my research really hits on. And we do that mostly, I've been focused on environmental risks and technological risks. And how we actually study that as social scientists is a lot of ways you can get data, right? So everything from like surveys and experiments. So surveys, any type of data that you would kind of fill out a survey for could then be used to like do modeling or understand kind of different patterns of behavior across all of everyone's respondents, so more quantitative data. Or do experiments, like say we give a bunch of people this type of communication and then a bunch of people that communication. What was the difference? How did they respond differently? We can also do interviews, like having long conversations with people, or observations, going into the field, understanding how a community was affected by a tornado and observing different processes, just kind of with our own senses. And we also can look at media studies or big data stuff. So like, let's collect all the social media posts that were about a certain event and try to understand different patterns and understanding media coverage. So that's really what I do as a social scientist. Like you're studying the human system specifically. And we think about how does this matter for our talking about this weather and climate stuff. So forecast information is really what we're focusing on, right? So that could be a climate scale or weather scale. But the first thing is the role of social science in this space is understanding how to better develop this forecast information. And so we see this, we kind of have this idea, we have researchers and developers, we're going to do science, we're going to make this forecast information. A user is going to take that information and we're going to have these like positive outcomes, things like maybe they're generating knowledge or behaviors or communication. And I think it's like easy to assume this is a pretty linear process or should be a linear process. We make the science, we hand it to people. But as we talk about it in other ways, there's a couple other factors at play here. Because when we think about how we make forecast information, a lot of decisions we make as scientists are affecting what forecast information is available, what variables we're using, what we're trying to model, what we're trying to predict at what scales, at what locations. So a lot of our own perceptions are going into it. But then there's also the users, how they actually are making decisions, what type of information they're pulling from, how they're going to act on it. And essentially their use decisions totally matter in this system too, that are going to facilitate what outcomes actually happen. So this is going to be things like, are they going to communicate this forecast information a certain way or communicate correctly? Are they then going to look for more information, do more information seeking? Or are they just going to straight up rely on it? A lot of different factors that come into play here. And if it's not complicated enough, each of these types of people are embedded in their own individual context, right? So both us as researchers and developers, as well as the potential users of this, like a forecaster or even an emergency manager or someone from the public, we have our own experiences, our past relationship with whatever is being forecasted. We have different expertises and backgrounds. We have different propensities. Maybe we're a little bit more skeptical of quantitative data, or maybe we're not, or maybe we have different roles, like we have different kind of obligations to be upholding within our kind of specific sphere, or different goals that we're trying to work on and navigate. And this is also embedded in a group level context, right? So if you're working as a researcher, the potential norms of your institution or your field may dictate essentially the forecast information you're making and how, as well as things like the culture with which you're embedded, the different power authority structures, your goals and priorities as an institution. All those things are going to shape the forecast information you're making to some way, shape, or form. And then to, again, add another layer here is the way that we are also like perceiving and understanding some of these contexts. Do we trust different types of forecast information? So trust in AI is something I'll actually briefly talk about in a little bit. How we actually really look at our information we're making in our science, and the way that people are interpreting and perceiving and understanding our science and forecast information we're making is really important. Are they have confidence in it? Are they comprehending what we're doing? Are there any kind of breakdowns or maybe misperceptions in this system that we need to navigate in order to lead to these better outcomes? And so we put these kind of things together, and it's like, this is a really, really complicated process that involves back and forth ideally, right? So Amy showed a good example in the last talk about working with across researchers and developers and these kind of users of the information to see, okay, what are our thresholds for heat and things like that? So that's a perfect example where there's more of this kind of give and take, and this like iterative cycles is the ideal, as opposed to just, researchers handing out science, which is sometimes what we think about. But again, this is a pretty complex and nonlinear system that influences, what science is used and how the science is used. And that's really what I try to figure out, right? So what are kind of the ways we can get science through this system in a more effective way, or can we meet users' needs more effectively, or can we work more collaboratively in a way that's still sustainable for science to make sure we have like the best possible forecast information that we can, right? So really bridging across the research and operational spaces is one part of what I work on. And so one example of how I've done that from some of my research is thinking about trustworthy AI, which I just mentioned. And this is a phrase, I don't know, many people have heard it before, but it's really, really strong and prevalent. It's something where it's in many of our own policy documents. Like there's been different executive orders and different, like actual congressional points that discuss trustworthy AI specifically. It's not just a US thing, it's in documents around the world, both in the EU and other places, that talk about development of trustworthy AI. And what I did in a paper is like, what do you really mean by that? As a social scientist, we know a lot about trust, and it's a really, emotionally laden concept that people really understand for themselves. You know who you trust and who you don't. It doesn't matter what a scientist says you should or shouldn't do. And so what I did is look through a bunch of this literature and was like, what do we really mean by trustworthy AI? And so essentially was using social science to understand our goals and how to achieve them, right? So kind of keeping on target. And what we found for this example with trustworthy AI is that when we think about trustworthiness, it's relationship based, right? So someone has to trust something or someone, right? You can't have trust exist without a potential truster. It's very relational, and trustworthiness is kind of that evaluation. Like when you're deciding, should I trust this person? Maybe not. If you had a pet sitter or a babysitter or a plant sitter and you went to a website, okay, I need to find someone that's going to watch my animal, plant, or kid, and they have a 99 out of 100 on a trust score, you'd be like, you'd want to know why, right? Like, what are the criteria? Do you know how to are you prioritizing the same things I would prioritize? This is really kind of an important perspective thing, which is why we say trust is perceptual, right? It's in the eye of the beholder, right? Someone's going to want to evaluate that for themselves, and the context is totally dependent. Because when we say, do we trust AI? It's like, are you trusting AI to pick your next song on Spotify? Or are you trusting AI to make a decision about, killing someone for a military application? Those are really different contexts. And so thinking about how the AI is being used, how it's being governed, and how it was made is all going to really matter here. And so this is an example of how we can use social science to really understand our goals better based on past research that we've done with these human systems. And so another way we can think about that is then thinking about these operational folks. So continue with the AI example, we can collect data to facilitate effective integration of new technology with frontline decision makers. And what I mean is, like, essentially when we make new stuff, understanding the people who are going to use it, right? Are they ready for it? Are they excited to be using AI or tools? Or do they have any hesitations or potential concerns, right? So making sure that our science that we do is actually going to meet the operational needs and concerns of those people that are going to be the front line. So with forecasters like the National Weather Service, those are probably the folks that would use the AI tools that we would make in the weather and climate the most, right, for these kind of decisions. And so what we did is we interviewed like 30 forecasters from across the US over a couple different, over a few years as AI was coming out, be like, where are they at with it? And what we found is that these folks are really committed to the National Weather Service mission, right? Providing the best possible forecasts and services were really, really the first thing. And so people were generally pretty open to using AI if it could meet that mission really well, right? So if you can give me less uncertainty and better communication and better forecast services, I'm down to try whatever. But it did range. Some people were like, I'm on board 100%, let's use AI. And some people were, and I'm open to it, but I have some concerns. And then also we found a pretty big range in familiarity with AI. Some forecasters were like, I did this in grad school, I'm pretty familiar with AI, here's my kind of breakdown. Other people like, I've heard of it, but I don't really know much beyond the Terminator, right? So you have a big scale of familiarity, so kind of room to improve overall knowledge, but it was also an interest in people wanting to learn more. But also an important thing is that these AI tools that we were looking at and evaluating, people mentioned it's like we use a lot of tools. So this would be another tool in the toolkit, right? So this is something that would guide part of your decision making, but forecasters look at so many things. And so making sure we understand our science is fitting in along a suite of information, not the only tool people will use. And the paper is there with a little QR code if you want to check that one out. And the second part I think about for social science in the weather and climate research space is really going into improving communication and forecast information. And so from this, we think, okay, we've made this forecast information, right? So between the science and the researchers and developers and operational users, and then we have to think about how it's communicated. That's a whole nother challenge, kind of the second part that I think about. And so we think about, okay, we've got the forecast information, usually think it goes to a forecast office. Like this could be a model or some observations that's going out to an NSF or NWS office. They're going to make these formal products, things like website, reportings and their briefings, put out warnings. They put things out to the weather radio, some discussions, special weather statements, and then that's going to go out to like their core partners, like broadcast meteorologists, for example, emergency managers, and the public. It's a pretty linear system here. But actually, what we know from how forecasters work is they communicate in a lot of different ways. So just from one of our communicators, they're sending out decision support service packets, right? So they're sending out briefing material to and hosting actual live briefings with their partners. They're also having a chat, right? So they're going through and having Slack channels and communicating with people live as events are happening continually. They're also calling and texting different people. They're also going to be having, interactions with folks on social media, as well as thinking about public events and communicating with folks as well. And so this is actually a diagram I made from a study that I'll talk about in just a bit. But just this idea of the communication system is really complicated, even from one of our communicators. And it's also important to think about, the importance of National Weather Service is that, okay, well, they give us a few products. I'm like, no, they're communicating behind the scenes in a lot of different ways, right? And they're making sure that all the folks in this weather enterprise are really on the same page and can respond to the needs of the situation as best they can. But it's also important to remember that these other folks are also types of communicators. So broadcasters are also then doing their own communication with this information, with some of their own information too. Emergency managers are sharing both things from broadcasters as well as from the forecast office. And then the public's also a source of information. So folks are talking about the weather that they've heard or seen, they're contacting each other, having conversations, right? So it's a really complicated web of information. So even if we have the perfect forecast information, we have to figure out how to send it out, right? It's a pretty big system to work on. And so ways that I've started to try to figure that out, like how do we really communicate this stuff, is through a few different studies. Like an example here is from the December 2021 tornadoes that were in Kentucky primarily. And what essentially we did is went out and did a bunch of interviews with folks around, emergency managers, broadcast meteorologists, the forecast office, and people in the public to understand when we look at these events, the successes and challenges for communication, right? So just seeing how the system works. And that's actually where the diagram I showed comes from, is understanding that system. And what we found was in that dynamic, there was formal and informal communication pathways were really crucial, right? So there was not just the things that you kind of think technically, but people's relationships and understanding of their community was also super important for effective communication about these tornadoes. And then also thinking about your community ties, and so the fact that the National Weather Services are based in these communities and understand their group really well was crucial for being successful in the communication, along with that community cohesion and understanding. Right, was how they responded really effectively. So we can kind of think about one way to understand the system is just to look at what happened and understand what the dynamics were. And the other type of studies we do would be like testing communication. So this work comes from, essentially we showed a bunch of different graphics of essentially potential probabilistic tornado information graphics. So if we change how tornado warnings are done with this on the right side of the screen, how do people react to that? Right? Or would they understand it differently? Would they take different behaviors? And so this was an experiment where we showed people either, the deterministic ones on the left, which is a box like you normally see. We showed some folks that the ones with the red shading. We put them in a bunch of different locations to understand, how is that format affecting how they'd respond? So that when we go to think about, should we be using probabilistic tornadoes, we know some of the trade-offs. And we're making sure we're ready and scientifically based when we're making decisions about how we should be communicating to folks. And what we found there was that there is really no silver bullet for how to communicate these things. There's no one right best answer. And there was a lot of differences, right? So when you're in that probabilistic version, you're probably fine tuning like, oh, well, I'm on the edge of this. Like I'm only in a 30% chance for a tornado, but like there's worse here, right? So kind of doing some relative risk assessment essentially, versus you wouldn't do that in the deterministic condition. And so kind of a few little notes there, and no one's going to be totally perfect. So we're trying to understand what the potential trade-offs would be, right? So that's one way we can understand the communication system is by testing specific products. And so pulling this together, like why does the public benefit from this? If you can't see it already, the main idea is that when we facilitate the development of better, more useful and usable forecast information for experts, right? So that first part I talked about, to improve forecast and communication of weather and climate risks. Right. So if we understand the right tools that need to be made so people can make better decisions, that's going to get you better information down the road. Right. So we're actually making sure our science is doing the right things, getting to the right people in ways that they can access. That's going to help you. It's like your experts are more informed with better science. And when we think about that second part, so setting the public communication, why is that important? what we do is essentially that's where we see, this decision-making environment lets us determine what information people need, how they're making their decisions, and essentially how do we keep them safe, right? So that they have the information they need to make the decisions that are relevant for them in their lives. And so how are budget cuts going to be important for this? And so this is where I want to take a step back. Before, what I've talked about is more what I would call my assessment as a scientist, right? That's what my science says. And now I'm going to say this is a judgment, which more in a political kind of realm. Like, this is what I think as an individual. We don't see the National Weather Service maybe all the time, but there is someone in your area 24/7 to keep you safe, right? And we need to be investing more in the infrastructure and not less. Right. So when we have more people who are better rested, who have, more time to be creative and to explore how to communicate and keep their community safe in the space that they live and that they understand really well, that's going to benefit us greatly. Right. So this is something that's going to be a really strong service that we can offer. And so then also cuts to social science, which is another thing that's being discussed pretty heavily. That's going to really limit our ability to leverage forecast information to save lives and property. Right. So without rigorously understanding the scientific way, the human systems of this, we won't really make progress. Right. Because if you think about it, you put all this scientific information in an effort into understanding the climate and weather. If we don't understand the human system, we're just kind of guessing or not being very scientific with how we disseminate it. So we need to study that part if we want to realize the actual benefits that keep people safe. But this is an essential part of the system. We need to understand that part really well. If we want to keep doing these things. Otherwise, like, you can think about, the perfect science doesn't actually lead to societal benefits necessarily. Right? You could think you could make the perfect vaccine for a disease, but if no one takes it, it doesn't work. Right? So we have to think about how do we get people to take vaccines, or how do we understand why they won't, so we can actually navigate those big barriers. And similar for weather. And so just a conclusion, coming back to the key takeaways, social science is a central part of this research space. And many of our overarching goals, right, for our work to be useful, used, and trustworthy need social science, right? And same with saving lives and property. We need to understand the social systems within those people's systems that is working. And so if we come back to my goals, I hope you walk away with an understanding of social science and hopefully an appreciation, and understand why we need continued research on communication decision-making, related to weather climate. And then that's all I have. Again, hopefully I have some time for some questions if folks are feeling ready and riled up on a Sunday morning to talk about some social science. Thank you.
Thank you. That was a really fantastic talk, a fantastic overview of the connection between social science, weather forecasting, and its real impact. So we have a couple of questions. First, I think everybody really appreciated the way you started with your career path. And so could you talk a little bit more about what made you decide to pursue this career path? What were some key turning points for you in becoming a climate social scientist?
Yeah, so I think the main point was that class, right? So in undergrad, I was kind of not trying to force a bunch of things together, but I was like, I don't want to close any doors, right? Like, I like science, but none of the scientific classes are really, I don't know, just that exciting. I was like, okay, I can get through biochemistry. I can get through OChem. I can get through some of those classes. And it was that first one was this graduate seminar on social science that I was like, holy crap, you can do science of people, right? And I was like, this is something I'd never thought of before. And I was like, it just clicked, where I'm like reading studies like I never read it before, where I'm like pulling apart. I'm like, well, how did you know that? How did you do this? Like, what is evidence for that count? I'm like, well, I would have done it differently. And it was like, oh, this is what people feel about in other classes, right? Like your peers in some of the other classes. And I was like, oh, I just was so excited about it. I had more and more questions, right? You had that deep curiosity and I wanted more, right? And I did the extra readings. And I was like, this is just clicking with me really well. And I kind of did a full send where I was like, all right, the application of the master's program is due in a month. I'm doing it. Like, I'm going for it. And then it just was like, I got into it more and more. And I really loved the research. And I was like, this is exactly what I was looking for, right? It just feels right. After, not quite clicking for most of the undergrad process, I was like, this is a thing I actually care about. Let's do it. And so that's what it made me. And I didn't really look back after that. And I was like, I like it. This is really fun. This is cool questions. And I've also pivoted a decent amount in what I studied, just kind of like following that curiosity and like what opportunities were there, and kind of checking in with yourself was really helpful. I'm like, man, I do not want it. Health communication is not where I want to be. It was really cool because like the big crises were health problems, but I was like, I really do care more about the environmental stuff, and like being okay pivoting, not like, but that's where my background is. I think has also been really helpful, because then you approach problems differently. It's like, oh, we know that from health. or we know that from other spaces. And so trying to like rebrand pivots as like helpful strengthening points as opposed to like, I can't change, I think has also been helpful, if that makes sense.
Yeah, that's awesome. Thank you. Yeah, so we have another question. We have a couple of questions about your communication research. And so let's start with the one, how does countering mis and disinformation figure into communication and decisions about communication? And maybe I'll ask some of the others, just thinking about limited time. So there's questions about who are the best messengers, maybe that appears, and questions about narrative.
Yeah, so those are both like some loaded questions. I'm gonna start with the messenger one because that's something I think is really key, is knowing that there isn't one messenger, right? Like we have to think about a communication system, right? So there's different speakers are gonna have different power or clout with different audiences, right? So if you think about any sort of scientific background, you're gonna wanna have kind of your go-to sets of speakers, right? So like an emergency manager in a small community is going to have a lot more clout with them than someone who's like from the city a couple 100 miles away who's never been to their town, right? Just because like you maybe have that familiarity aspect, or you might have certain types of jobs that have more trust or perceived as more or less trustworthy. And so making sure that you have more of like a web as opposed to like, a direct channel down, so that like you're trickling down information around in many sources from many different ways. And I think being okay with that, the message may shift a little bit as we go, right? So they might not say the right points about cape and shear for the tornado system, but they're like, hey, it's looking bad and that could be okay, right? And so not trying to control the message a ton, I think is actually helpful. Let people communicate how they need to their own audiences so that they're all doing the best thing, right? So it's a little bit of a counter theme, but most people are like, let's control the narrative really strictly. And it's like, I don't think that's a good idea, right? So I think making sure that consistent narrative is good, but letting a little bit of communication freedom, I think, is really important so that it makes sure our mini communicators have the latitude they need to get to their audiences in ways they know. And so that's kind of one point. Mis and disinformation is a beast, right? Because sometimes, like, is it really misinformation or is it bad journalism? Or is it bad kind of like understanding of a past forecast? Is it hyping? Is it a bot, right? There's a lot of big questions there. And I think understanding where it comes from is more important than countering specific statements, right? So why are people excited about, something that you think is not right? Right? Or what does that matter? And a lot of times you find out what disinformation is, the worst thing you can do is respond to it, right? You can like fan the fire and it like gives it more credibility and makes a discussion. So sometimes it's like, how do we be okay letting that go? Right? And kind of like, is the best use of our time addressing, this like one tweet that's really annoying you? Or is it like making sure you have a couple more tweets that show a consistent message so that when people look at their feed, they see a lot of the right information and they can kind of see that maybe this is an outlier, right? Or it only has one, like or retweet. It's not really that important. So kind of balancing why we as scientists are reacting to it, right? And it's like, you're part of the system, right? Is this something that it needs to be addressed scientifically, or is this something you're personally responding to? I think is a really important thing we need to do more of. That makes sense.
Great. Thank you so much. Thank you again for a fantastic talk. And you can check out the chat and see the ways that you've been inspiring and changing the way that people are thinking about these sorts of questions. Great. Okay, so our next speaker for this hour is Brian Mapes, who's a professor at University of Miami. And he'll be taking us into some of the background of how do these weather forecasts come to be? What are some of the fundamental knowledge, and how do we get the fundamental knowledge that we need to improve our understanding of weather and climate so we can make better forecasts. And with that, I'll hand it over to you.
Okay, well, hopefully that means I'm online here. And what I do is just go to this thing. Go to full screen. Are you seeing me and hearing me okay?
Yep, looks great.
Seeing slides and hearing me okay. All right, well, welcome to the last session here. I didn't know if these sessions had a theme or anything, or if it's a bit of a mix and match. But I will play a little with the contrast, with the former speaker, I guess. I'm going to show you some very pie in the sky work about, invisible waves. And, plea for don't forget the exploratory work as we speak of these services to the nation and stuff. But, with all humility and gratitude to all these agencies, and it's a funny historical mix that have funded the kind of work I do and many of us do. So, gratitude's the main thing. There's sort of an ancient theme in Western civilization here, which is shown by this Glaucon-Socrates dialogue here in the Republic. To know something about the seasons, the months, and the years is of use for military purposes, as well as for agriculture and for navigation. Socrates says, it amuses me to see how afraid you are lest the common herd of people should accuse you of recommending useless studies. Anyway, not that I'm any Socrates or that any of us want to end up the way he did, but there's a situation here that natural philosophy needs love too. That's what I'm defending. So we're looking here at a generational setback. This is a graph here of federal funding for the sciences just shooting up, and the request that came out Friday for both NASA and NSF that I glanced at is 50% cuts, not just in our geosciences but biology too. It's amazing. It's just anti-science all the way down. So of course, still please do plead with your senators. Congress does often boost these requests from the administration. Back in normal times, that has happened many times. So it's a good time to be in contact. But as a community, we probably do need to have some kind of triage plans. At least it's a useful question, I guess. And where do we stand on applied, basic, or even fundamental research? Big and small science is a long time. A versus B, labs and universities, external grants and internal labs, and seasoned pros versus the new faces. So, what are we going to do about all this? It is unclear, and these are way beyond my pay grade and tough questions. And I have as much sympathy for the leadership that's going to have to do these rethinkings as for the lopped scientists I know so far. So anyway, tough times, and my heart goes out to really everybody at every level in this. It does seem we'll need to rejuvenate the case for our science, and part of that, this stream is great. We are part of an important stream of services, public services forecasts, including climate scenario projections and things. But I hope we also don't lose the wonder and appreciation of the world aspect of science, including this careening human experiment. Social scientists are having an interesting experiment, I guess, and including political science, but mainly with humility at our enormous privilege for a lifetime behind me at this point, and gratitude for what we get, and but a commitment to integrity that doesn't sell out. So thanks to the country as it's been, the organizers, and all of you for showing up. I am here going to tell you about formerly invisible waves in the sky, which is a project from the National Science Foundation. It's kind of a full stack academic project here with a postdoc, a PhD student who's starting Monday morning, I think, with her research, and an undergrad from the fall. So it'll be fascinating. You've all seen waves in the sky, and you've all seen, the 1 in a billion selected overdramatic waves in the sky, but maybe fewer people know the sky is just full of waves, but it's waves as sort of the fourth type of flow that we see in the world. The wind blows and things slide along. That's the easiest part of dynamics, I suppose. Convection is interesting and creates a lot of texture. Vortices downwind of islands and this Cape of Baja here in this example, vortices, and of course tropical cyclones, everybody sees those. And the waves are a little bit, but of course in this one you see these pinchy little highly periodic waves, but you also see just, waves radiating out of the southeast corner and off toward the northwest, at many, many scales all the time. I've been noticing that for a lifetime, and just wanted to get a handle on it here. So sliding motions are easy. They just have a speed and a direction of the wind. Vortices are a little trickier. They have centers and strengths, and then the tangential wind, drops off with a 1 over radius from there. Convection's kind of similar. There's cell centers, and the divergent wind or radial wind drops off as 1 over radius from there. those are ways to think about those. But waves are complicated. They have in a snapshot, they have an amplitude and phase, but there's a time continuity of crests and troughs. That's really what we mean by waves. And those crests and troughs come in packets. They aren't just everywhere all the time. So we need a sort of a packet view as well. So waves are interesting that way. And as I said, it's been a long time puzzle to me to see these waves on satellite animations, and never been able to get a handle or quantify them. It just didn't have the computational tools, the software tools, I guess, maybe till now. So the project is we use low clouds here just as an observatory for gravity waves, and they're everywhere on every scale. This is out of a plane window, and of course there's a barely cloud deck, and you can see the waves making the difference between cloudy and not cloudy. And here's the entire southern Indian Ocean, and on this scale we have these wave fronts. Maybe a little clearer in an animation that runs from day to night. Don't you definitely see waves coming out of Cyclone Freddy here on the right? But the more times you stare at this, you'd say, oh, there's also waves coming out of the northwest here. Anyway, it's just among the things that is not the first most variance kind of phenomena here are these waves. And anyway, it's just it's my white whale hunt here. So anyway, of course, these have been noticed in the literature. This is a case manually tracked here with lines on a map, and this is Peru and the Southeast Pacific, which I'll be showing you some more of. And these waves, perturb the marine stratocumulus, as well known and well shown. Here's how they did it, just satellite images here with Peru in the upper right corner of all of them, and sort of zoomed in over here. One thing, to sell this is sometimes the wave troughs clear so much that they expose the underlying ocean, or completely change the albedo. And sometimes these waves in their crests make precipitation happens, which clears an area and has a lasting effect, a rectified effect. And the way to think about this in climate terms, if you must, the game of Earth's photon budget, waves tend to drive the cloud fraction toward 50%, really from either side. Just the other day in an airplane, I was noticing, some of this, over here, it might well be overcast here if there weren't waves. And there certainly wouldn't be any clouds at all over here if there weren't waves. So whatever the waves do, you can puzzle it out as well. They nudge the cloud fraction toward 50%. So that's an interesting way to think about it as a climate effect, if everything must be. Waves are funny because they're kind of like ghosts in the law of motion. In fact, the words are full of this. This is a specter, it comes from French spectre, ghostly. And, the spectrum that we see of white light turned into colored light is, comes from this word of what a ghostly thing that is, what a surprising thing that is. And in the case of fluid dynamics, the spectral laws involve a phase velocity, the motion of crests and troughs, as opposed to a group velocity of packets of waves. And those can be different. And the phase velocity, again, coming from these phantasma or phantom, the phase velocity, the motion of the crests and troughs. And the group velocity comes from a word for, lump masses and lumps. So anyway, the speed of phantoms and the speed of lumps are different in general for waves, which is a fascinating thing, and for different kinds of waves. The kinds of waves we're looking at here are called gravity waves or buoyancy waves or internal waves, depending who you ask, in the ocean or the atmosphere. And they're these kind of back and forth tilted sliding motions in which buoyant flow feels an upward force. Eventually that makes it rise, which makes it cool, which makes it feel the downward force. So it's kind of there's a restoring force of gravity to these sloping motions that have a little bit of a vertical component to them. And the phase propagation in this case is to the left, the way it's depicted. Those red and blue stripes have moved to the left. But the group velocity is actually and downward a little, and the group velocity is actually upward. So that's the puzzle of, that's the funny way these waves work, is the energy of packets goes up as the phases of crests and troughs go down. And they obey this, what's called a dispersion relation, which relates the frequency of the wave to this property n, which is how stratified the air is, and k, l, and m, which are wave numbers, 2 pi over wavelength in the x direction, the y direction, and the z direction. And just to show you that, there's one relationship among 4 variables here, and the other 3 are set by well, how are the other 3 set? So that's kind of the textbook view of it. If we look right near the surface and just think about long waves, weather making waves, I suppose it gets a little simpler. You can just think of the winds as reversing direction if there's no background wind, and upward motion here maybe at the front. This would be a wave moving to the right with a phase speed c. Upward motion ahead of the crests, so that here the blue surface rises and soon the crest has arrived, and everything's moving to the right here. And for these long or hydrostatic waves, the phase velocity and the group velocity are equal. They're both just horizontal, and they're just this n, buoyancy frequency of how stratified the air is, over m, the vertical wavelength. So in other words, their vertical wavelength per about 10 minutes in the troposphere. So an 8 kilometer vertical wavelength in 10 minutes moves 8 kilometers horizontally. That was such a puzzle to me to learn as a student. I didn't trust it. I didn't believe it. It's in the math, and it's simple math, as partial differential equations go. But I didn't really believe it till I went into a laboratory in a classroom, actually, and did this. Made a stratified fluid here in a tank, and put some dye lines in it, just dropping little fluorescein balls in, and then setting off a kind of a buoyancy event here. It was just a ball of salty water down into the tank. I've inverted this so it looks like a cumulus cloud rising up, but it was, that's just an upside down photograph. But when you have a complicated event here that's turbulent and messy, it has all kinds of fine structures in the vertical. But if you watch it happen, look at this. The first thing this dye line knows about this very complicated event is, oh my gosh, it's 1/2 wavelength of it. Perfectly mathematically smooth out here. And then as time goes on, these are strobe images, 1, 2, 3, 4, 5, 6, 7, 8, 9, buoyancy periods, I guess. You can see that the finer and finer vertical wavelengths arrive slower and slower out here in the far field until eventually, everything's parallel that way. So I didn't really believe this dispersion of horizontal speed by vertical wavelength till I saw it with my own, camera. And it's true. It is true. I went looking for this outdoors a little bit in some of these nuclear bomb photos where they would send up these rocket trails. Maybe you can sort of glimpse that being real. That's how stratified air works. Invisible stratified air. So invisible waves and invisible stratified air. That's all very textbooky here. And the question is, what should we go looking for outdoors? Waves, as we've seen out the window of the plane, many scales and frequencies can exist anywhere there's a stratified fluid, n is greater than 0. And, they'll obey this relationship among 4 variables. That doesn't tell you what'll happen. It just constrains what will happen in this 4-dimensional space down to 3. So what we have to expect to see is whatever has a forcing, whatever has a driver is what exists in the world. And so now we got to talk about these drivers. The most famous internal gravity waves in the atmosphere are flow over a mountain. And maybe that's a little clearer if you think of a corrugated sheet in a laboratory and you drag it to the right. Anyway, the front faces of these corrugations, push a column of air, upward, and behind, as the thing slides past, the column of air can slump back down behind it. So, what kind of waves are driven? Well, the corrugations set the horizontal wavelength, K and L measure that, and the speed of the thing, or the speed of the wind over the mountains, sets the phase speed of the wave. So we're controlling the horizontal scale and the phase speed, and the vertical scale, or in other words, the tilt of these waves, because when you send up a vertical thing, you're measuring how tilted they are, or you measure your vertical waviness depends how tilted they are. So the tilt or the vertical scale is somehow implied by the equations. So that's a case where horizontal scale and speed are set, and then the vertical scale, comes out of the problem or comes out of the math, depending on the nature of doing the math. Here's the second common form of wave, is just something bouncing up and down in the sky, and that might be overshooting cloud tops. And so you can imagine what that does. The cloud has a scale, a horizontal scale, and it bumps up and down at some frequency. So in a laboratory, you put a little disc in the fluid and raise it up and down. So you're setting again the horizontal scale, and this time you're setting the frequency, and now the speed of the waves and the vertical scale are really determined by the equations. So that's a different kind of an oscillator forcing. Here's a third way that waves are often excited: if we have a heating rate Q, which might be like a latent heating in a thunderstorm, a rain event. All that rain coming out involves a pulse of heat put into the atmosphere, and here the timing over which that heat is put into the atmosphere sets a frequency, and the profile, the depth of the convection, sets the vertical wavelength, and then the horizontal scales just come out, as the math of the problem. And maybe a fourth thing which might be similar is nonlinear momentum imbalances, just the way the winds are just crashing into each other everywhere all the time. It's sort of a form of turbulence. When winds crash into winds, something's got to get out of the way, and these things involve vertical excursions of parcels that jiggle and wiggle. And I think that might be similar to the heating, but instead of pushing the density field with a heat source on the temperature, it's pushing the wind fields because they crash into other winds. This one's just a hairball of complications, of course, but I think it may be another case where, the profile of the winds, the jet stream depth or whatever, sets the profile, and then some time scale of how long it takes the winds to, the slow motion train wreck of the jet stream into a stagnant air mass or something, maybe sets the frequency. I don't know, but we'll see some of those later on in the movies, I suppose. It's what I find is a common source. So, the way we measure waves is, do they resemble a wave? So we make what's called a mother wavelet function here, which is a wavy function that's contained. This is an envelope of waves, a wave packet, and we just measure the resemblance of the image to the structure like this. And if it looks like it, we call it a wave. It looks like a wave and quacks like a wave, we call it a wave. And so let's look at this a little bit here. This is an infrared image, kind of contrast enhanced. This is a visible image loop. And let's see, and here's Peru again over on the right. This is the Southeast Pacific again. Now, am I crazy, or do I see a wave in here propagating toward the northeast? Toward the northeast, dark and light bands propagating toward the northeast in the bottom of the picture here. There's also maybe some things coming down from the northwest up in here. Some of that is outflow from the high clouds of the tropics. So maybe the cleanest purely wave thing is a thing like this going about 45 degrees to the east. So that's, so we've, I'm in one slide here, I'm showing you months of work of the mathemagic of how we measure that. We take our scales and angles of the wavelets and display them as like a wave rose at each little sublocation within the image here. And we find that, yes, in the southern part here, we have waves moving toward the northeast, scales about 128 kilometers because they're every factor of 2. And also some waves coming down from the north, maybe east of that. So, we could watch that again, but I won't bother with it. But point is, we can now measure this mathematically. So our eyes are, better than any kind of math, but we now have some math that pins it down. And we can calibrate that with synthetic data where we put in a wave and recover that specified wave. And then we're ready to automate. We're ready to fish through months and months and years of data all around the world. And with the contrast boosting of the infrared, we're ready to look for these waves. And one more new way, just 2024 here, discovery really, new way to see the invisible is vapor imagery in the infrared. If you take a time difference of it, you can suddenly see clear air vertical motions from space. Imagine that, brilliant new piece of work here just in 2024. And I'll just show you briefly how that works. In the infrared, often when we look at infrared imagery, we're looking at a window region where water vapor doesn't emit, and we look down through the atmosphere and see the low clouds here. This is a low cloud scene near Barbados. But if you look in these 6.7 micron, these infrared bands where water vapor emits a lot, you don't see down through the atmosphere anymore into the clouds. You see the kind of the emission temperature of water vapor, which is way up in the upper middle troposphere here. And it's smooth because water vapors last a long time. It's a well-mixed gas, somewhat well-mixed gas, and it's just got a little bit streaky, but basically smooth. And so you don't see much in this water vapor imagery. This is how maybe this didn't get discovered. But you take a time difference over 10 minutes of that water vapor imagery, and way down here at the 0.1 Kelvin precision, the waves just pop out, and you see, oh my gosh, the clear sky is full of waves here. And if you make a time and latitude diagram here, you see those waves are propagating at just a perfectly clear speed, both directions. They pass right through each other. It's just waves everywhere you look, like the surface of a sea or something. So it's an amazing finding here. And again here, these authors and also we tend to find a kind of a 14 meter per second wave speed, pretty fast, somewhat fast. And that implies, if you like, an 8 kilometer vertical wavelength. So where's that coming from? We got this 14 meter per second waves implying about an 8 kilometer vertical wavelength. How, why are these so common? Why are these so common? One way we can further pin down this vertical wavelength is, I was showing you the stratocumulus waves. We see those clearings and brightenings and darkenings here. And for a right moving wave here, the crests of the wave would be tilted back here. For an 8 kilometer wave, the crest of the wave would be tilted back here. And this level where the water vapors see in it, maybe up here at 6 or 7 kilometers, we could say that the channel 9 is right above the cloud trough. If we go off looking for that, yes, sir, here where the clouds are cleared, the water vapor difference in channel 9 is positive. So it does seem like this 8 kilometer wavelength is, directly measured as well as implied by the speed. So I think we're finally pinning down what these waves, and we're pinning about both the wavelength and the speed, which agree, which they must mathematically, but it's nice to see. And the question is, what source is producing these? And back to a 25-year-old paper of mine, I think that constant N profiles lack something that the N of the real atmosphere, which follows a moist adiabat up to the stratosphere, has, which is this 14 meter per second thing that has, puzzled me for 25 years. I think I'm finally seeing it outdoors in nature. So I'm excited about that, and maybe heating profiles or these momentum imbalance events might just be hitting kind of a mode of the waveguide of the troposphere, which comes from the properties of a moist adiabat, and that would be why they're so common, I hope. So anyway, just last palette cleanser here. Here's the first video that started with on this project, and again, Peru up here on the right, and you see these things out of the southwest. I think that's where the South Pacific jet stream is, crashing into air masses, or it has vortices and troughs in it. So that's maybe synoptic source. Here's a hurricane-like source, and you see these waves rippling across here. But actually, if you look real carefully, where do these? If you follow these waves back to their confocal point, it's way up here. It's not necessarily the heating in the hurricane. It could be the winds blowing over the mountains or something. anyway, we need to measure these things to pin them down. But just to say that it doesn't have to be heating. These momentum effects, even vortices without clouds and heating in them, radiate waves. This is just a ditch in the Everglades where you just can't stop waves from being everywhere. Complicated flows vibrate among their many other properties. So in conclusion, I guess here, internal waves are everywhere. The sources determine what actually occurs. We can see them on stratocumulus. This 14 meter per second or 8 kilometer wavelength seems to be everywhere. And I think it might be a fundamental property of the atmosphere we've missed. So again, my huge gratitude for a lifetime of funding support, and try to keep up to exploring and learning and not just forecasts as an economic enterprise. So that's my spiel. Thank you.
Yeah, that was beautiful. Thank you so much. I think there's many takeaways from that, really highlighting the power of mathematics. I think we're all going to be seeing waves everywhere now. And so showing really how science helps us to see things that were previously invisible, but also really your example at the end showing that it does take decades of investment to make some of these advances that are going to be fundamental. Okay, so I think we have time for one quick question. And so one quick question we'll go with is, when you look at these waves, or when we're looking at these videos, it looks somewhat chaotic. But can you talk about some of the structured patterns that repeat? So consistent dynamics in certain seasons or certain geographical regions, and I guess just less than a minute for an answer.
Right. Well, the sky is always yes and, right? So there's wind and there's vortices and there's convection and there's waves. And this is exactly what I wanted to get to, is to automate the measure of the waves so that we can now run, I want to run a year of data and have a climatology, right? Are there more in the winter, more in the summer? We just have none of that because we haven't been able to measure them, right? You can see them with your eyes, and I've seen them for years and everybody's seen them for years, but if you can't measure it, you can't start turning it into data and ask about climatology and anomalies and possibly trends and changes like that. So the ability to measure things, which includes the math of how to digitally, log them, is sort of an art in itself. And I'm just thrilled to have it in my hands now after a lifetime of sort of puzzling over these things and not quite believing them. But it's always yes and we're looking for the fourth effect. The first three effects are well studied by other people long ago, and the fourth effect we're finally being able to tease out and quantify. So.
Fantastic.
Yeah.
Thank you so much again. If you can look at the chat and see how much people valued it. There'll be a few other questions in there if you have time to jump in.
All right. Thanks very much.
Yeah.
Cheers.
Thank you. Okay. So we're going to transition a little bit now, but before that, I'm going to welcome everybody again, remind you why we're here, what we're doing here. And so we're now in hour 94 of the Weather and Climate Livestream. So there's only 6 hours left to go today. And here we have another great hour of weather and climate science for you. And in this hour, we'll be talking with scientists who are studying hurricanes. But before we begin with those, I really want to remind you why we're doing this and why we're on your screens here. We really appreciate that you all are here. And we know that you're probably here because you really value fundamental science because of its inherent beauty, as we were just seeing, or because of its concrete value that these forecasts have for our lives, for our economies, and for human health. And climate and weather prediction really relies on both scientific understanding, like we were just hearing, and on good data, both good data of things like waves or data what the weather is today. And so scientists in the US at both our national labs, like the NOAA labs, and at universities have made fundamental advances, including developing the first computerized weather forecasts so that you can know the weather that's coming in the next days and weeks ahead. So you can prepare for extreme weather like hurricanes. US scientists also develop climate models so that we know how extreme weather may change in the coming decades. I think one thing that's really important to understand is that weather forecasts don't work without observations of weather today. Just like scientists need observations for understanding, in order to forecast the weather tomorrow, we really need to know what the weather is today. And we've created unparalleled networks of observations, including weather stations, satellites, planes, balloons, boats, floats, this huge array. And it's not just the US, it's part of a global network, and each part is essential to weather forecasts in the US and globally. The resulting forecast and observation system creates extraordinary value in people's lives. Weather forecasts are invaluable. I check the weather every day, you check the weather every day. And we're really excited in this live stream to be able to share some of the people and the work that underlie these forecasts. And so scientific tools and advancements are made possible by decades of investment by the American public. And funding cuts put this entire system at risk. Now weather stations are short-staffed, so we're losing observations that we use to make good weather forecasts. We're also losing the capacity to have experts analyze models. Laboratories that are dedicated to understanding our climate's future are being closed and shrunk. And so that's hurting our ability to understand what may come. And the proposed budget has far worse cuts in it. This is being considered by Congress, and it really would slash NSF and NASA Earth Science and completely eliminate NOAA's research arm. And for many scientists, this is seen really as an existential threat to what we do, not just because of the immediate cuts, but also because of a lack of investment in the future generation. That's really essential to be able to sustain some of this knowledge generation and these decades of investment. And so I'll just say, no matter what, thank you for being here. We really value your active conversation in the chat, your engagement with these topics. And we'd like to ask you to take the next step as well. So please use the link on your screen to contact your representatives and to say, save our forecasts, keep the lights on for weather and climate science, so we can keep this scientific capacity, this extraordinary science alive. And so feel free to ask questions about our science in the chat. Keep up the active conversation. And with that, I'll hand it over to our first speaker for this hour, Andy Hazelton.
Good morning, everyone. Thanks for being here and participating in this. I'm going to be talking about hurricane forecasting, specifically hurricane research flights and reconnaissance flights, and some of how that data is used. And also, I'll be talking about how hurricane forecasts have improved over the last few decades and just the importance of that and why we need to keep doing that. So when we talk about hurricane flights, both the NOAA and Air Force are involved in that right now. So I'm with NOAA, I'm at the University of Miami, but both NOAA and the Air Force are involved in flying. The Air Force missions tend to be generally strictly operational, meaning that they're only there to see where the storm is, how strong it is, whereas NOAA does that, but and collecting data, but also has a research component that allows us to collect data to study and understand storms better. And NOAA we have both the P-3 aircraft, which is on the top there, that's used to fly through storms. Those are the ones that I've been participating in. And then also a G4 jet that's used for sort of synoptic surveillance to look at the large scale steering and environment that the storm is in. So you may not realize it, but there's a lot of logistics that go into a flight. When you're putting the 15, 20 people in through a hurricane and collecting this data, it makes sense. Typically, the Air Force will, when they're doing their flights, they'll do it every 6 or 12 hours, sometimes more frequently as the storm approaches land. The NOAA planes, we go twice a day typically, and centered on either the 12Z, so 8 a.m. or 0Z, 8 p.m. Time window, because that's when a lot of our key weather models are initialized is 0Z, 12Z. And so that is a key time to collect data on a storm that can then be fed into these computer models to improve the forecasts. The flights can be anywhere from 6 to 9 hours or so, depending on how much time it takes to get to the storm. If you're further away from it, we'll talk about that in a minute. And then typically you get about 3 to 5 hours in the storm, again, depending on how close you are and that kind of thing. And we're going to look at some of the specific patterns that are flown. And then there are also research modules. There's sometimes where we're trying to understand developing storms or certain rain band patterns. And so there are additional research things we can add on to that as well. Okay, so these are some of the more common P3 flight patterns. There are others, like especially for bigger storms, but for mature hurricanes, these are some of kind of the key ones. There's the figure 4. This is basically you get 2 passes across the storm. The green circles are where represent locations where we typically drop a drop sonde, meaning a tube with all sorts of weather instruments on it that descends with a parachute. So that's one of the instruments, along with the radar that we'll talk about, and lots of other instruments. The butterfly pattern, you get 3 passes across the storm. And then the rotated figure 4 is kind of the best coverage where you actually get 4 passes across the storm. And so if you're close to the storm and it doesn't take long to get out there, you can typically get something like this. Maybe if you're a lot further away, you have to do something with fewer passes across the storm. So these circles represent the range of operations. NOAA's Aircraft Operations Center, the headquarters is in Lakeland, Florida. So that's where we'll fly out of for stuff in the Gulf or Bahamas or Northwest Caribbean region. But we have a couple of other locations, Barbados and St. Croix, that are used to sort of forward deploy when there's a storm coming out of the central Atlantic here or in the Southwest Atlantic or maybe the Northeast Caribbean. So that allows us to sort of get out, and data and studies have shown that getting to storms early is critical for making the forecast better. And then Bermuda and Cabo Verde are also places you can use to fly certain storms, especially more for research purposes. So there's a lot of data that's collected. One of the big ones is the data along the flight level, and websites. You can go and visualize this data. It comes off the National Hurricane Center website. But basically, the flight level wind, that's one key piece of data that's used to sort of observe the storm. The pressure, temperature, dew point, those are all things. There are surface winds that are also measured. There's actually a lot of research going on to work on the calibration of that. And so that's really shows why ongoing science and ongoing investment to understand and refine these instruments is critical. I talked about those drop sondes that basically are dropped from flight level around 10,000 feet or higher for the G4. And they descend either into the eye wall or the eye or whatever part of the storm, collecting temperature, pressure, and humidity data. This data is also fed back into the models and also used by forecasters. So you can see, this is an example from Hurricane Milton last year. This is one in the eye. You can see the pressure, 899 millibars at the surface. I think it was a 5th or 6th lowest ever recorded in a hurricane in the Atlantic. And then this was an eye wall. So you can see how the wind started off from the southeast and then switched around to the northwest, because as the drop sonde falls, it rotates with the wind of the storms. This was a pretty extreme eye wall sounding. And so just an example of some of the fine data that we can get. And like I said, all these things cost money. They all take investment, but this data is critical for helping warn the public. The tail Doppler radar is one of the big ones that that the NOAA planes use. There's this Doppler radar on the tail of the P3 plane, and it's used to collect wind and reflectivity data that tells us a lot about the structure, like the tilt of the vortex and things like that. And this data is also available on HRD's website for viewing. So you can, if you're nerdy and you're interested, you look at it publicly, and it's also fed into the publicly available models. So we'll talk about that here. That's probably one of the biggest parts of this data, and one of the key reasons we do these flights is by flying through the Doppler radar, we basically make a 3-dimensional picture of the storm that provides an accurate initial state to the model, like HAPS, which is what I've worked on. HWRF is an older model that still runs. And both of these bring in that data, and then so you help use this data and other data to make an accurate initial state, and then the forecast is based off of that going forward. And so you can see here, when you get this radar data, it makes the model initialization a lot more accurate. Like you see on the top, 2 examples. This is Helene with sort of a larger storm with a broader eye. Milton was a very tiny storm with a very compact core. And both cases, getting the HAPS data or the model data in there allowed HAPS to initialize a lot better. And both of these cases, we were able to forecast the rapid intensification very well, which is not something we were able to do even as much as 10 or 15 years ago. And obviously, the data is also critical for operational analyses of forecasting or of storm intensity. The National Hurricane Center, you'll often see them in their discussions, their advisories, cite the NOAA or Air Force planes, because satellites do give us a lot of data, a lot of critical info. We need more satellites for sure. But this these flying through and the storms like we do is really the only way to get that full three-dimensional picture. And it really is critical for the Hurricane Center to assess what these storms are doing. And studies have shown, this is a nice figure from my colleague Sarah Ditchek, that the intensity forecast is improved by up to 10% by bringing in this data. This is specifically looking at drop zones near the inner core of the storm. So it really has been shown to substantially improve the forecasting. Same thing with track from these the G4. These again, it kind of flies around the outside of the storm or the environment to sample the large scale, high and low pressure areas that are steering the storm as it moves across the ocean, and track forecast improvement up to 6 or 7% from that. And we also have ways where we basically take model data and things like that and use it to then look at what areas are most sensitive to, where can we target our observations to improve our models and make these forecasts more accurate. So you often see this, especially for a storm that's coming toward land, like Joaquin was in the Bahamas, forecasted to get close to the Carolinas. So this model data then was used to basically design a flight pattern where we could sample regions that were most sensitive to those observations and improve the model forecasts. So these are some pictures of mine from Hurricane Helene last year. It was a huge storm, so the outer rain bands were approaching already as we flew out of Lakeland. This is inside the eye, so that was a pretty surreal experience as it approached Tallahassee, Florida, where I went to school at Florida State there. So one thing, as we were flying through the eye of Helene, this is the radar on board the plane, one of them, and we saw these little finger-like features. Think back to Brian's talk, there's always these waves, always these perturbations in the atmosphere, and even in a hurricane, which is a huge perturbation, a huge disturbance in of itself, there's these smaller scale features in the eye wall, these mesovortices, and these can be very turbulent. So the crew decided not to fly through those, and we took another way out of the storm. So we're always trying to be safe and collect as much data as we can at the same time. And thinking about Helene, we were able to, because of a lot of this data that was collected and the work that my colleagues and I have been able to do at NOAA and all our collaborators, the forecast was actually really good for Helene. Our models did a good job of predicting the potential for flooding rain, this large wind field, which drove storm surge into Tampa and along the coast. These outer rain bands which produce tornadoes were all forecast. And this is another project I was working on with predicting inland wind gusts. And the models showed hurricane force winds well up into Georgia and South Carolina. And we know that was one of the biggest impacts of Helene as well, as this large swath of inland wind damage. So while they're not perfect, the models did a good job in this case of predicting and allowing us to get better warnings out there. So this is the track forecast from Helene from one of our HASS models last year. You can see that basically from the start, it was almost perfectly honed in on the Big Bend region. So even when the storm had just formed, we had hurricane warnings up for this area, and that allowed people to prepare and get out of harm's way. Hurricane Milton was another one where we had our models were pretty accurate, and we ran our experimental model version of HASS on this last year as well. And you can see, although the track forecasts were very similar, the experimental version of the model, which some of those changes are going to be brought in this year, did a little bit better because it showed the storm actually hitting south of Tampa, which is where it actually hit. And that's critical for storm surge, because when you have a storm hitting north of Tampa, the wind basically pushes the water into the bay, but south of Tampa, the water gets actually pushed out of the bay. And so with that huge population center, getting those track details right is critical for that. And so, as much progress as we made, we have a lot more to do to be able to really get these fine scale details right and improve our warnings. And Milton was another one where we had all sorts of impacts that were predicted well. The heavy rainfall along I-4 here in Florida. Again, the storm surge from the wind field. Tornadoes, this was one of the most prolific tornado outbreaks in Florida history. And you can see that the models show these cells in the outer bands that produce this. And also the wind gusts from this sort of sting jet feature for my weather nerds out there on the backside of the storm, and did things like rip the roof off of Tropicana Field there. So again, lots of hazards from hurricanes, and the model data and the radar data, the aircraft data informs all of this. And so just to kind of get the broader picture of what this has gotten us, all the work on modeling and observations over the last 30 years, we've seen now that track forecasters have been steadily lowering over the last 30 years. And a 5-day forecast from last year was actually about as accurate as a 1 to 2 day forecast was in 1992, which is when Hurricane Andra hit down here in South Florida. And so that allows people to prepare a lot earlier and basically get out of harm's way. And intensity forecasting, unfortunately, for a long time did not show the same forecast improvement. But then you see there, over the last decade or so, we've seen big improvements in intensity forecasting as our models have gotten better. We've refined ways to use this aircraft data. And now we're still not perfect, but we're sometimes able to get these rapid intensification and structures forecast well. And what that really does is it allows us to not just tell us where the storm's going to be, but how strong it's going to be, and really a lot more details of impacts to the public. And so what that gives us is, when we look at hurricane forecast improvement, you can see what they have for the circles here. This is an example from Hurricane Milton, basically when it was near the Yucatan, 3 days before landfall, basically. What the different circles are basically what the average 3-day forecast error was in 1992, 2004, and 2024. So in 1992, the red circle was basically kind of where you would expect based on an average error the storm could be. And really it was anywhere almost in all of Florida. So you probably would have had to have watches up for a large area. And then pretty much the whole state would have had to evacuate or close down schools and businesses, things like that. 2005, 2004, we started to make improvements, and it was focused on the Florida Peninsula, but still kind of a larger area than was actually impacted. In 2004, now with the improvements last year, we were able almost 3 days out to focus on the fact this is going to be in the Tampa Bay area in some region. And what these forecast improvements do is that, like I said, obviously it allows the people in harm's way to get out sooner, and we'll see another example of that in a second. But it also means that you don't have to unnecessarily evacuate huge areas that don't get hit. And that leads to economic improvement, because you don't have to close schools or businesses unnecessarily. And so studies have shown that each storm, each major hurricane like this that makes landfall, the improvements in hurricane forecasting save about $5 billion per storm on average. And so really, a lot of ways, NOAA and NASA and all this hurricane work, it pays for itself every time we get a hurricane, because the forecasts lead to saving lives and property. And this is an example from a very well-known hurricane, Katrina. This was from when it was in the Bahamas, several days before it hit Louisiana. It was impacting Florida. So this was the official forecast at the time. You can see how wide the cone was at the time. Again, that's come down as forecasts have improved, but the official forecast was up into the Florida Big Bend at that point, and then in reality, it hit in Louisiana and Mississippi there. And this was a one of the modern ensemble models, like I've been working on, and basically did a much better job. If we had modern models with Katrina, we would do a much better job of honing in on the actual final landfall point days out. So again, we'd have people in Southeast Louisiana and Mississippi would be able to prepare sooner, and people here in the Big Bend of Florida hopefully wouldn't have to unnecessarily worry about the storm coming. And so saving lives in the area it actually hits, and allowing them to protect their property, and also protecting economic activity in the areas that aren't hit, and really being able to focus these warnings on the areas that need it. So just to summarize, hurricane reconnaissance flights, and they're a really critical part of the backbone of U.S. hurricane prediction. Air Force and NOAA crews are both critical to this. So it involves, these are expensive instruments, are expensive to maintain. You need personnel to be able to staff these and keep them going around the clock, because it's important to keep continuous coverage when you have a storm approaching land. And also the models. That's one of the big parts of what I do, is working on the models. But that takes a lot of expertise. As AI becomes a bigger thing, we're going to have to work on ways to use artificial intelligence and bring in expertise on that, so that we keep up with the technology on that. And so, because hurricane forecasts have been steadily improving in recent decades, but we have a lot of work to do. What we don't want to see is a situation where, due to cuts and due to lack of resources, that we see a reversal. Because we still have cases like Hurricane Otis from 2023, which kind of unexpectedly hit Acapulco, Mexico, as a Category 5, and it wasn't well forecast. And so we don't get all of them right, and we want to keep doing that right. We don't want to see cases like that. We don't want to see major U.S. cities hit without warning. And so we need to keep investing in people and the technology to not only maintain the skill and improvements that we made, but to keep making progress and keep using the new technology. Because there's cool instruments like artificial intelligence at the modeling side. There's drones that we've been part of testing that can sort of get down in the lower parts of these hurricanes in areas that it's not safe to fly the P3. So technology is going to allow us to do some great things if we keep investing in it. And so with that, I will finish and be happy to take any questions.
Thank you. What a fantastic talk. And I think everybody really felt the sense of adventure at the beginning and is really impressed by the modeling improvements that have happened. And so the first question that I want to pose to you from the chat is, what are some of those improvements to the modeling, and what is the role of the observations that have led to these improvements in our ability to predict over the past couple decades?
Thanks. That's a great question. So one of the big improvements, obviously, is resolution. Basically, a model runs on a grid, and the finer the resolution, the more details you can see. And so over the last 30 years, obviously, we've had exponential increases in computer power that have allowed finer resolution. So that's one. But really, the other thing is that hurricane physics are complicated, and there's a lot going on because you have exchange of energy from the ocean and the atmosphere and the lower atmosphere, and then it's miles up in the sky. You have outflow, and so you have to get the lower boundary with the ocean and that interaction right, and you have to get the upper atmosphere right. And so we've collected observations in all these different areas. And so for example, what we call the boundary layer, the lowest 1 to 2 kilometers. That was an area we didn't really well understand, and we still don't perfectly, but a lot of the observations from those drop zones and other things have allowed us to then refine our approximations, our parameterizations of the boundary layer in the model. And that's one of the we saw in the 2010s, big improvements in intensity and structure when we started correcting how we were parameterizing the boundary layer directly based on observations. And I've been part of working on that in HAFS. And so without the aircraft data, we wouldn't have been able to realize that we were doing it wrong.
Awesome, thank you. And maybe a related question, there's a question of if you could talk a little bit more about how measuring around the storm helps you figure out where it goes next.
Sure, yeah. So flying through the storm like we do with the P3, that gives us a lot of details about the structure and the depth and the intensity. But hurricanes are steered by large-scale weather systems, the jet stream or Bermuda High, areas of large-scale high and low pressure. And so by taking measurements of those large-scale features that are sort of steering the storm, it improves how our models are initializing or starting off those features. And then, so that makes the whole forecast more accurate and basically a much more accurate steering picture. Because satellites give us some of that information, but the satellites don't have the vertical detail needed to get all those steering details right all the time.
Excellent, thank you. Okay, there's also interest in knowing a little bit more about your experience. We have a question, what was your first hurricane flight like?
So yeah, so I flew actually as a student intern here in 2013, and I flew into Tropical Storm Karen. So thankfully that one was pretty weak. We still had a couple good bumps. My first storm that I flew through that was actually a hurricane was Hurricane Michael in 2018. So that was kind of a pretty intense one because that was one of only 4 U.S. Mainland Category 5 landfalls, and I flew 2 or 3 missions, including the one right before it made landfall. So that was very bumpy, very turbulent in the eye wall, and definitely pretty surreal knowing a storm of that power was about to hit land.
Awesome. Yeah, I think one of the things that came out in the chat was this impact of the data being publicly available. I think a lot of people didn't realize they could see this data immediately. And so could you talk a little bit more about where that data is made available and also the ideas behind this data being publicly available?
Sure, yeah, that's one thing.
Maybe a related question of as funding is being cut, how might people see a loss of data and how else will they be able to access data?
Sure, yeah, that's one thing where the U.S. has really been a leader is in open access of data. All this, the model data is publicly available on website. You can grab it from NOAA's data portals. You can make your own plots. You can go to places like Tropical Tidbits, which is one of my FSU colleagues, Levi, runs, or there's lots of websites that make these. The aircraft data is the same thing, that you can grab it yourself off the National Hurricane Center website as it comes in and make your own plots, or you can go to some of these sites that have aircraft recon data. Then they make their own plots, and you can sort of visualize it yourself. And that's one of the really, I think, the key thing. We've been a leader in taking these tax dollars and putting it to work in valuable data that people can directly see for themselves what it's doing. And so, yeah, if cuts come and we have to do fewer flights, you won't see this data as often. We'll be guessing a little bit more on what storms are doing. The models, hopefully the model data will still be there, but maybe it won't be as accurate. You won't get to do these upgrades as frequently. And so I think people just, need to realize that these investments honestly pay for themselves and then some. I think like I said, the 5 billion number, and it's not just hurricanes. Severe weather tornado forecasts are getting better, and just across the board, these forecasts lead to, it's really one of the most, thinking about efficiency, it's one of the most efficient things in bang for your buck and investment. And we want people to access the data and go look at it and ask questions about it, and that's one of the things you get from this investment.
Awesome. Thank you. And then I guess one final science question for you was asking, so you talked a little bit about the rapidly intensifying storm that hit Acapulco. So could you talk a little bit more about how the flights help us learn about these suddenly amplifying storms and improve predictions in real time?
Sure. Yeah. So, because sometimes, like I said, satellites, have gaps or just don't get things. So if you fly into a storm, no matter whether it's weak or strong, you're going to get a full detailed three-dimensional picture. And so that's one of the reasons why we like to fly through these at early stage, because when you get data in there early, it helps the models have a more accurate structure from the beginning, and you don't get these surprises. Whereas, if you don't fly a storm, like for example, Otis, the one I was talking about where we missed, we didn't have flights into that in the East Pacific. And so, we'd like to be able to fly every storm, but again, that takes more investment and more resources and things like that. And so, being able to get that accurate three-dimensional picture from the early life cycle of the storm is really critical.
Great. Thank you so much. Thank you again for your talk. And we learned a lot from you.
Thank you.
Yeah. And so as we transition to the next speaker, this is, as a reminder, a full hour about hurricanes. I just want to say, as you notice at the banner below, today is the first day of hurricane season. So very timely to be talking about this. But it's also really highlighting the importance and value of being able to take these observations in real time. I talked at the top of the hour about how critical observations are to forecasts. And so just a reminder, is you'll see a link on your screen where you can take action to ensure that that funding cuts do not impact the accuracy of these forecasts, both this season, but also in the long term, our ability to make those improvements that you really just saw over the past decades. And so with that, I will introduce our next speaker. So we're going to be hearing from Andra Garner, who's a professor at Rowan University, and continuing these conversations about hurricanes.
All right, great. Hopefully everyone can hear me. I'm going to go ahead and get started here. So I'm going to be talking about my work studying hurricanes and climate change and focusing on hope amidst storms of change. So I'll go ahead and get started here. So I want to start with a look at my office wall, actually. And so here on my office wall, we can see a picture of two hurricanes. And these two hurricanes are the first down here on the bottom right is Hurricane Katrina. And Hurricane Katrina gets a picture on my wall because Hurricane Katrina was actually the first hurricane that I kind of really remember being aware of and tracking. And Hurricane Katrina happened just before I actually entered my senior year of high school. And so it was at a time when I was starting to think about what I wanted to do for my career. And this was something that really caught my attention and got me thinking that maybe I wanted to study weather or hurricanes in particular. As it turned out, I went to my undergraduate and studied math. So I was not studying weather for a little while, but I did ultimately come back to wanting to study weather and meteorology, and enrolled in a graduate program at Penn State for atmospheric science. So up here on the top left is another hurricane, and this is Hurricane Sandy. And Hurricane Sandy gets its spot on my wall because Hurricane Sandy happened just before I actually did start some of that graduate work looking at hurricanes. And my graduate studies were actually taking a look at how hurricanes are impacted by climate change. And in particular, we were planning to assess how hurricane flooding, due to both the storms themselves as well as higher sea levels, might be changing. And we were going to be looking at the New York region. So having Hurricane Sandy occur so close to that time when I was about to start my studies really was, I suppose, motivating to have seen the kinds of damage that we saw with Sandy, which I'm sure many remember, the storm surge flooding that we saw throughout New York and New Jersey. And so it was good motivation for a lot of my graduate work then, studying how these kinds of storms are changing. And I'll talk a little bit more about that in just a few minutes. All right. So when it comes to hurricanes, we know that these storms are a $1 billion problem. From 2012 to 2022, we had over 160 different $1 billion weather and climate disasters that occurred here in the United States. And among those disasters were Hurricane Sandy, 2012. We have Hurricane Harvey, Irma, and Maria, all in 2017, which caused a lot of devastation from everywhere from Puerto Rico over to Texas. We had Hurricane Ida in 2021, which we know caused a lot of damage down in the Gulf where it made landfall, but also continued to cause a lot of damage and wreak havoc here in the Northeast where I'm located, as we saw unprecedented rainfall amounts from that storm. And we have Hurricane Ian, which occurred in 2022 as a very strong storm in Florida, and of course caused a lot of devastation there. So again, we can see that these kinds of storms are a $1 billion problem. And in fact, these were actually the 6 costliest $1 billion weather and climate disasters that we saw in that period from 2012 to 2022. All 6 are hurricanes. And so hurricanes really are a costly hazard for the United States. And we also know that hurricanes are getting worse in a changing climate. So as we take a look here at what's going on with hurricanes and with climate change, we know and have known for quite a while that when we produce heat-trapping gases like carbon dioxide, we will warm the planet. That carbon dioxide gets into the atmosphere and acts like a blanket and heats up the planet. But we also have noticed in recent decades, and I know there have been a couple talks pointing this out, that a lot of that warming is going into our oceans. So over here, we can take a look at this graph from NOAA, which looks at ocean heat content changes over the last several decades. And as we look at that, we can see that about 90% of the excess warmth that humans have generated in recent decades has been absorbed by our oceans. Now that can be good for us in that, in a way, our oceans are doing us a bit of a favor in preventing maybe the atmosphere and the land from warming quite as much, but it's actually really dangerous for hurricanes because that warmth in our oceans is a critical fuel source for hurricanes to not just form, but to form and then strengthen. And when we're heating our oceans up to levels that are abnormally warm, we're creating the opportunity for those hurricanes to potentially strengthen very quickly. So I'm taking a look here at some of my research that I've done. I thought about this a bit a few years ago and embarked on a journey to try to understand how the rates at which Atlantic hurricanes strengthen have been changing over time. So we know that, again, we've seen these storms capable of strengthening especially quickly as we have those extra warm ocean waters. And so what I wanted to do was to take a look especially at how often Atlantic hurricanes are strengthening from what we might call a fairly weak storm, something that's a category 1 or less. So it's going to have lower wind speeds, perhaps lower storm surge amounts, and how often storms are strengthening from those kinds of storms into what we classify as a major hurricane, which are our category 3, 4, or 5 storms. So we looked at a couple different time periods for this over the last 50 years. The first time period I'll pull up here are historical storms from 1971 to 1990. So in the 70s and 80s, when we look at the data from the National Hurricane Center and our observed storms, we can see that this type of thing, storms going from a fairly weak storm into a major hurricane in 12 hours, 24 hours, or 36 hours, was a pretty rare event. We had just over 1% of storms make that jump in 12 hours during this 1971 to 1990 time period. A little over 3% make that jump into a major hurricane from a weak storm in 24 hours, and a little over 4% make that jump in 36 hours. When we look at the more modern time period, so now we're looking at 2001 to 2020 here in the orange, when we look at that, we can now see that while it's still a relatively rare event for a storm to make this jump from a weak hurricane into a major hurricane in 36 hours or less, it is much more common than it used to be. And so over here, if we compare these bars, we can see, for example, in that 12-hour window, it is now more than 3 times as likely as it was in the historical time for storms to make this jump from a weak storm to a major hurricane in 12 hours or less. We can see that that chance of making that jump in 24 hours or less is up to 8.12% in the modern time period compared to a little over 3% in the historical time period. And when we get to 36 hours, we can again see that the chance of making that jump in 36 hours is more than double now than what it used to be. And these are results that when we look at the statistical analysis, we can see that it would have been impossible to find this number of storms, this percentage of storms in the modern time period, making that jump if there hadn't been some kind of change environmentally, some kind of change to the conditions in which these storms are forming. We also can see when we think about this, that this lines up pretty well with some of what we've seen in recent years. So here is an image of Hurricane Helene, which strengthened very quickly before making landfall. It strengthened from a category 1 into a major hurricane in less than 12 hours prior to landfall. And we, of course, know the kind of devastation that we saw with Helene last year. We can also take a look at Hurricane Milton, which strengthened from category 1 into category 5 very quickly last year. Hurricane Milton was one that even, surprised a lot of forecasters as they were looking at this storm, as they were looking at how quickly it strengthened. I have heard stories from people that, fly into these storms and were flying into a storm like Milton, expecting it to maybe be category 1 and found that it was actually category 4 or 5. So this was one that really was shocking and made that jump from that weak storm into a category 5 storm in under 10 hours. The other thing we know about storms and hurricanes and climate change is that they're not happening in isolation, right? We have a lot of different climate change impacts that we know are occurring. And some of those interact with our storms as well. One of those climate change impacts that we can take a look at is up here on the screen now. And this is looking at changing sea levels and the impact that those changing sea levels have on storm surge. So when we take a look at our storm surge, we can see from this diagram, the storm surge is that water that the hurricane is pushing ashore due to its strong winds. And we have this water coming ashore, but how far that water goes depends on the level of the ocean that it's starting at. So as we can see on this animation, as our sea levels get higher because of human warming, causing ocean waters to expand as they get warmer, causing ice sheets and glaciers to melt and get into the ocean, we push our sea levels higher. And when we push our sea levels higher, we're increasing kind of that starting point for the storm surge. It's like we're giving the storm surge from a hurricane a head start, and it's able to reach further inland. It might reach greater depths and ultimately causes more damage for our coastal communities, even if the storms themselves were not to change very much. So again, this is actually related to some of the work that I did for my graduate studies as I worked towards my PhD. And so when we see here on the left, we're going to be looking at how often a 7.4 foot flood occurs at the Battery in New York City. And so 7.4 feet is actually a little lower than what we saw with Hurricane Sandy. But if you can imagine a wall of 7.4 feet of water getting pushed into the New York and New Jersey region, I think we can all agree that would be a very significant and fairly catastrophic flood event. When we looked at our data, we used modeled hurricanes, simulated hurricanes for different climates. And the first climate we looked at was a pre-industrial climate. So this is for a climate prior to 1800, before humans were starting to have a really big impact on the climate. And when we looked at this, we found that on average, this kind of flood, 7.4 feet, is something that only happened about once every 500 years. So maybe something that a person would never see in their lifetime. When we move forward in time to the modern time period, we now see a lot more blue dots up here. Those blue dots are representing the years out of all the other dots that we would see these types of floods. When we look at the modern time period, we found that the frequency of the 7.4 foot flood is something that could happen on average about once every 25 years. So now we've gone from something that maybe would never happen in your lifetime to something that could happen several times in a person's lifetime. And then as we look forward into the future, we have, by about the middle of the century, the potential for this type of flood to be something that could happen about once every 5 years. And so this is something that has gone from something you might never see in your lifetime to potentially fairly soon being a relatively frequent occurrence on average. And when we looked at our data, we found that the primary reason for this increase in the likelihood of these flood events is due to the sea level rise. The storms might play a small role, but mostly it's those higher sea levels that are driving the worsening impacts of storm surge flooding in New York City. So we'll go ahead and move forward here, but this is something that other studies have looked at as well. There have been studies looking at Sandy in particular that have found that Hurricane Sandy caused an additional $8 billion worth of damage due to just sea level rise, human-caused sea level rise alone. So I want to talk now a little bit about some of the work that I'm doing looking at sea level rise, which is incorporated into what I'm calling the Beaches Project, which is better enabling assessments of coastal hazards and expanding seas. This is work that is possible because of funding from the National Science Foundation. If you're interested in learning more about it, I encourage you to scan the QR code that's on the screen right now, and you can go to our website where you can see some of the work that my students and I have been doing. The goal with this project is going to be to really continue to understand sea level rise and its uncertainties, and think about how we can bridge those knowledge gaps that might exist between science and the coastal communities who need the science, so that we can make sure we're really understanding the scientific information, getting it into the hands of people who can use it to take action to protect our coastal communities, not only from sea level rise, but also from other coastal hazards that are made worse by sea level rise, like hurricanes. So I want to wrap up here by talking about the good news and the bad news. We'll start with the bad news first and get that out of the way, right? We know that we're the problem here. So we know and have known for quite a while that humans are the cause of the climate change that we're seeing now. Dr. Dessler earlier this week actually gave a really great talk about the history of climate science. I encourage you to go check that out if you get a chance. But that was, showing that this is something that we have known for about 200 years. We've known the science of if we add greenhouse gases to the atmosphere, that we are anticipating that we will warm the planet, that those gases will trap heat near the Earth's surface and make the planet warmer. We also know from data that we've collected through organizations like NOAA that a lot of that excess heat that we are causing by burning fossil fuels has been going into our oceans. And when that heat gets into our oceans, it can cause worsening hurricane impacts by allowing them to strengthen really quickly. The good news, on the other hand, is that actually the same as the bad news, we know that we're the problem. And so the good news there is that we can also be the solution. And so we know that since we're the problem, we can be the solution here. And we actually already have the technology at hand to allow us to be the solution. And this is great news because I like to think, as an alternative, if we weren't the problem here and actually the problem was something like the sun is getting brighter, that would be pretty terrifying because we wouldn't have any way to deal with it. Or, as I've actually been asked about several times in recent hurricane seasons, if the problem was that there was some nefarious actor out there with a weather machine that could create hurricanes and steer them, we know that that's something that would also be a very terrifying situation. Luckily, that's all sci-fi, but we do know that we are the problem here, that it's us burning fossil fuels that's causing this issue. And so we can also very much so be the solution. And that's great news for us. And I'll just end on a little bit more good news, but it's good news if we can keep it. And the good news is that we have the right tools for the job. And so I've already talked a lot just now about some of the critical data sets that we have from NOAA that allows us to not only see hurricanes and learn about them, but to study how climate is impacting hurricanes. Some of those data sets include our $1 billion weather and climate disaster data set, which unfortunately has recently been discontinued, but that has been a super valuable data set for us to be able to track these kinds of hazards and see how they're changing. We've talked about the ocean heat content that we measure, and we have decades worth of data that we've been working to be able to track that and understand how it's changing. We have lots of critical data from the National Hurricane Center, which is what has allowed me to do some of the work that I showed looking at how hurricanes are strengthening. All that data came from observational records from the National Hurricane Center. We have other organizations like NASA, which are constantly collecting all kinds of information that's really critical for us to be able to understand how carbon dioxide is changing, how all sorts of global signals are changing. And we have also, we can see how important this data is. And the talk before me did a good job of showing exactly how valuable this data is for our hurricane forecasts. But we've seen studies that have shown that from 2009 to 2020, hurricanes forecasts saved us about $7 billion. And that's 20 times the amount of money that we spent on improving those hurricane forecasts. We also know that when it comes to the National Weather Service, which is housed within NOAA, that for every $1 that taxpayers spend on the National Weather Service, we see about an estimated value of more than $73 coming back to us from the excellent forecasts that we get there that are critical for saving lives as well. So I'll leave it there, but I hope that this has left you with some hope and hopefully some motivation to make sure that we can keep these kinds of data sets moving forward.
Fantastic. Thank you so much for this amazing talk and also your insights on where to go next. So there were a lot of questions for you in the chat. I'm going to start with one, which is a question of, will stronger storm surges also cause more coastal erosion? So your animation was
sorry, go ahead.
Yeah.
Yeah, so I mean, coastal erosion is certainly something that we see as an impact from large storm surge events, and that can be, storm surges from hurricanes, but it can also, for us here, especially in the Northeast, be from powerful winter storms like extratropical cyclones or nor'easters. And when we have those higher sea levels, it does amplify that storm surge, and it very much can cause the erosion that we see along our beaches to become worse.
Great, thank you. There was another question asking, is there any way that we can see historic hurricanes to take a paleoclimate view on hurricanes, and asking, were there other times in the past where we've seen more intense hurricanes?
Yeah, that's a really great question. That's actually something that I'm working with a colleague who does more paleo work at my university, Rowan, to try to put together a grant right now to get funding to study that. With that, that's something that we'd like to look at Florida, where we've seen many major hurricanes make landfall in recent years. And, our paleo record really is a valuable additional set of data for us to be able to get a sense of how hurricanes have behaved in the past, to be able to take a look at a longer term record than what we have just from the observational data, which, goes back at best about a century or so. And so the paleo record really is a critical resource, and it's something that there are always ongoing studies, and something that I think, we need to continue to support funding to be able to gather more paleo records, which are time and resource intensive to gather and then assess, so that we can continue to kind of build out our picture of what the past looked like and when and where we might have seen changes in hurricanes over those long time scales in the past.
Excellent. Yeah, there was also questions early on about your path. So you talked a little bit about you had a math degree. And so then the question was, what part of your math degree turned out to be most useful? And I guess a broader question is also, what sort of education would you recommend for people coming into this path?
Yeah, that's a great question. So I would say broadly, from my perspective, the statistics that I took as a math student has been really useful, because a lot of my work does involve now looking at statistical changes over long time periods of how these storms are changing, and being able to assess the uncertainty there, and being able to determine where we see significant signals and changes in the data. I would say, there's a lot of different potential backgrounds for getting into this kind of field. For me, it was math, which turned out to be really good because I was able to take those math skills and then apply them into atmospheric science in the future. There are, of course, also several undergraduate programs in atmospheric science or meteorology around the country that would also be good options. As another example, right now, I teach in an environmental science department, and I have had students graduate from that and then go on and study meteorology a little more specifically. So I think there are a number of paths. Physics might be another good option to get into studying our atmosphere, because certainly physics plays an important role in some of the things that we look at there too.
Excellent. Thank you so much. And I guess just one final question. So you're obviously educating the next generation of scientists, and you've talked about some of your future work. I think in the next couple of years, in the next decade, what do you see as being the most important thing for climate and weather scientists to take on, the most important challenge for us?
Yeah, that's a really good question. I think there are going to be a lot of really important things for us to take on. I think continuing to work to really understand the impacts, because again, we know the science of climate change. We know why this is occurring. I think further understanding what some of those impacts are and how they're changing and how they might continue to change into the future will be really important. And I think then continuing to bridge that gap to not only understand what those changes are, but to think about how we can implement solutions to the climate impacts that we're seeing, which might include adaptation measures along our coast, but should also definitely include thinking about how to mitigate climate change from a global standpoint, thinking about how we can improve our communication and build the ties that we need to really work at the root of the problem and cut our emissions so that we do have that hopeful future of maybe the impacts not meeting a worst case scenario, but being able to curb some of those impacts moving forward.
Excellent. And this is concluding our hour on hurricane talks. And so could you just tell us, so we have on the banner, today is the first day of hurricane season. What does it mean that today is the first day of hurricane season?
Yeah, so with it being the first day of hurricane season, I'm grateful to have been able to talk about hurricanes a bit today. And I think that it's something that, as the talk before me mentioned, we have really valuable improvements in our forecasts. And so I hope that we can continue to have the data that we need to keep those forecasts on a positive trajectory. As was mentioned, we don't want to go back. I would say also, being the first day of hurricane season, knowing that climate change is affecting our storms, making them worse, is something that I hope that everyone, in the path of hurricanes who might be in a region where a hurricane could strike, now is the time to kind of have your action plan, get that together, think about how you're going to be prepared. If you do get one of those warnings about a hurricane, heed the warnings. Scientists are good at what we do, and our work is ultimately trying to protect people and infrastructure along the coast. So just again, be sure to pay attention to any potential warnings that might come up throughout the hurricane season. And it'll be something that we all need to just keep an eye on and watch out for in the coming months.
Yeah. Thank you again. As the comments say, that was outstanding. Thank you for a fabulous talk.
Yeah, thank you.
And with that, I'm going to hand over the hosting responsibility to Matt Longo, who's another early career climate scientist.
Yeah, hi, Mara. Thanks, everyone. Happy to be here on this final day. It's been pretty amazing to see the work that our directors have put together here. So hi everyone, my name is Matt Luongo. I'm a climate scientist and oceanographer. I'm calling in from Seattle, Washington today. Thank you for joining in hour 95 of the Weather and Climate Livestream. We have another great hour of climate, ocean, and weather science for you. We'll be speaking to Professor Amato Evan and Maria Fernanda Morales Aleman. Before we begin, we want to remind you why we're here on your screens. We know how important weather and climate forecasts are to you and to everyone in this country. Luckily, the US has long been a world leader in weather and climate prediction. We developed the first computerized weather forecasts to help you know what you can expect in the coming weeks, and we made the first computer models of the climate impacts of carbon pollution, so you can know what to expect in the decades to come. To make these forecasts work, we've created an unparalleled network of observations, using everything from weather stations to satellites, planes, balloons, boats, and floats. The resulting forecasting and observation system is a true scientific miracle, and we're excited to share some of that here with you today. This miracle has been made possible by decades of investment by you, the American public, but in recent weeks, funding cuts have put this miracle at risk. Weather stations are so short-staffed that we're losing observational coverage, which is already hurting our forecasts. Laboratories dedicated to understanding our climate's futures are being shrunk or closed, and funding for our basic understanding of weather and climate is disappearing. The administration's proposed budget, which is now being considered by Congress, is far, far worse. It would cut the NSF and NASA's Earth science budgets in half, completely eliminate NOAA's research arm, which is what I'm personally funded by, and end foundational programs for young scientists like the NSF Research Experiences for undergraduates and graduate research fellowships. But it doesn't have to be this way. If you like what you've seen here over the past few days, then we ask you to please use the link on your screen to contact your representatives and tell them to save our forecasts, to keep the lights on for weather and climate science, so we can keep this miracle alive. And please spread the word to join this live stream. We have a few hours left, and we'd like folks to be on as much as possible right till the bitter end. Last, a brief reminder that all speakers are here in their own personal capacity and their views are their own. So we've seen a lot of great talks, and our next speaker will be no exception. Today, our first speaker in my hosting slot is Professor Amato Evan. Professor Evan is an atmospheric scientist based in La Jolla, California, and today he'll be speaking about dry lakes, drought, and dust storms' effect on air quality in Southern California. Morning, Amato.
Hey, Matt. Good morning. All right. Let me get my timer going. Cool. Yeah, just firstly, thanks to the organizers for putting together such a fantastic event. And let's see. So I wanted to talk to you. Darn it. I have a video right here that I was hoping was going to render, but it looks like it's not. But that's okay. We can make it work without the videos. What you're looking at right here is an image of a dust storm traveling across the Salton Sea, which is a large inland lake down in the southeastern corner of California. And this is an area where I do a lot of work. And of course, this talk is going to be about dust storms specific to the state of California. And a lot of the work here is that I'm going to discuss here is in a report, a group I'm part of called UC Dust, just put out on dust storms, their causes, impacts, future, and some adaptation and mitigation strategies that we think are required to protect the environment and the population of the state. Now, let's see. Darn it. Well, this is what it looks like inside of a dust storm. And the way that a dust storm happens is that you have really large particles. When the wind picks up, you have large particles on the surface in a dry area that bounce along the surface. And as those large particles, called saltators, bounce along the surface, either they break up into very fine particles that then are lofted high into the atmosphere, or they dislodge those fine particles that are also at the surface that maybe just can't get mobilized themselves by the wind. And then those get mobilized into the atmosphere and travel long distances. And when I say small particles, I'm thinking dust particles that have a diameter that might be on the order of maybe 1/10 the width of one of your hairs. And you can see kind of in the right-hand corner there's an instrument that we take out, or on the right-hand side of that image, or a set of instruments that we take out when we go out into dust storms. I'm not going to be talking about those measurements because it's kind of in the weeds, but these are measurements that we make. We go out and do what I would call dust storm chasing, and try to make measurements that we think will improve our ability to forecast dust, both in terms of weather, like looking out days in advance, and especially climate, so looking out years to decades in advance. And yeah, I'm sorry, this image isn't working. There was another image of being inside of a dust storm, but the types of landscapes where you have dust storms, it's a little intuitive what you might think. Basically, you take a desert area, but it should be pretty flat, not very rocky, not much vegetation, because vegetation actually slows down the winds, and then an area with a lot of fine soils. So, these types of areas might be locations, say, of dry lake beds, dry stream beds, areas where there's a lot of runoff coming from the mountains. And when I say runoff, like water, after big rainstorms that have a lot of eroded material traveling with them. These are just what I would think of as like the natural sources of dust in a desert environment. But we have a lot of then what I would call anthropogenic sources of dust in the state. And it's not just specific to California, it's really worldwide. And one of those is agriculture, not lands where we do irrigation and where crops are being grown, but when we have lands that are being fallowed. And that could be fallowed lands just because where a farm is in terms of the annual cycle of planting and harvesting, or because cropland, agricultural land has been, just rendered unusable for a number of reasons for, a longer period of time. And those fallowed agricultural lands can be quite a bit more emissive, meaning that they tend to be really good sources for dust storms just because they're flat, the ground has been tilled, and so the surface is really disturbed as well. And so those, then you put high wind speeds over a landscape like that, and you generate dust, which isn't good for the people around there. And it's also not good for the farmers, because then that represents a loss of topsoil that tends to be pretty nutrient rich. Another source of anthropogenic dust is off-road activity. Not to say off-road activity is bad. I like four-wheeling a lot. But, if you have off-road activity, it disturbs the landscape. And really just because of the mechanical action of a vehicle traveling over a desert surface. And this image implies, well, it's just when the trucks are going by and that's not a big deal. But really the important thing is that, when we drive over desert landscapes, we disturb the soil. And so, and that disturbance then, so taking soil that might be otherwise have like a crust on it, and then disturbing that crust, well, then what you've done is you've created this landscape with a lot of fine material, oftentimes over a flat, unvegetated area, especially if you're driving over vegetation that disturbs, these natural barriers to dust production. And then that landscape can remain in this more emissive state for really long periods of time. And by that, I mean like, days to weeks to even years. And so, right. So if you take a desert landscape and you have a big off-road party over it, you can increase the amount of dust that comes off it by, up to 4 orders of magnitude. So quite a bit. Another source of dust, and this one is very specific to California, would be water diversion, right? Or really in the Western US, we move water around for agricultural activity, and we've been doing that for, over 150 years now. But usually you take water from one place, or, you want to irrigate crops in one place, you've taken water from somewhere else. And this is a prime example. This is called the Owens Dry Lake. The Los Angeles Department of Water and Power in the early part of the 20th century started diverting water from Owens Valley, which is a valley in the Eastern Sierras, down towards Los Angeles to support the growth of the city. And as a result, this lake bed dried up. And this was at the time one of the largest kind of irrigation projects on planet Earth. That lake that was up in this area called Owens Lake dried up, and it became this huge source of dust. And what you're looking at right now are these clouds of dust being lifted off of that dry lake bed. And, fortunately, it took until the 1990s, but the Los Angeles Department of Water and Power took responsibility for the dust source they had created here in Owens Valley. And now the ratepayers in Los Angeles have spent north of $2 billion to try to address the dust that's coming off, to do all types of mitigation projects on that dry lake, so it's not such a health hazard for the people that live in the communities of the Owens Valley. So if you put all these sources of dust together, we came up with a map of areas where we think dust storms occurred just in California. And so that's all these shaded regions. So as far north as the northern part of the San Joaquin Valley, this is that area in orange, and as far south as the southeastern tip of the state. And this is really a massive area, spanning about 55,000 square miles and home to almost 5 million Californians. And to put those numbers in perspective, that's an area and a population greater than half of the states in the US. So it's really just this massive, massive area where dust storms occur. And there are a lot of impacts of dust storms that we think of as being adverse for the environment, the economy, and the health of the folks living in these areas. And I'll just highlight a couple here. One of those is the impact on solar energy generation, right? We tend to put solar panels and solar power plants out in desert regions because there's a lot of land and it's really sunny. But if you get a lot of dust deposited on those solar panels, it can reduce the amount of energy that you're producing by 25%. And then also another problem is that, it requires a lot of water to then clean these solar panels. And this is already a water limited area, right? So you're taking water out of the environment to clean off solar panels. There's also a huge public safety component, and this is a really big deal. If there's a large dust storm, visibility goes down, and weather-related traffic accidents, when they're caused by problems in visibility, tend to have double the fatality rate of other weather-related accidents. And I think it's mainly because people don't slow down enough when they can't see in a dust storm. And oftentimes too, if somebody pulls over on the side of the road, they leave the lights on in their car, someone comes from behind them and smashes into the back of the car. So it's a really awful problem. And health-wise, I mean, this is a totally different top. We could go on for like a very long time talking about the health impacts of dust storm. A lot of these are just associated with being in the middle of a dust storm and breathing in that dust. And this ranges from respiratory illness, cardiovascular disease, allergic response, adverse birth outcomes. But then dust can actually carry contaminants that are in the environment. And so, we think about heavy metals that might have been associated with some kind of industrial activity, or pesticides associated with agricultural activities, especially agricultural activity that happened, maybe decades ago when, we were using these long-lived, really toxic pesticides. And dust storms also carry these biological species. So talking about bacteria, fungi. And so these types of biological species can get whipped up in the dust. And we think this is a big reason why there's this outbreak of a disease called valley fever, especially in the Central Valley of California, in the San Joaquin Valley, because it's a fungi that gets kicked up in the dust. And then folks, if they're in the middle of the dust storm, they're exposed to everything else that was in the dust. Then also agricultural activity. And I talked about agricultural fallowed lands being a source of dust, but dust isn't great, not only because of the loss of topsoil, but dust storms over an agricultural area can cause physical damage to the plants. That's this image at left. It almost looks like these plants are burned, but they've just been abraded by dust. Dust falling on plants reduces their photosynthetic and conductance. So basically how efficient these plants are at converting sunlight into energy, and also just labor productivity, right? It's pretty darn hard to do work out in the middle of a dust storm. And so just the folks that are out there aren't going to be as productive. And so then if we think about those adverse impacts, all those areas in the state where dust storms occur, and then we want to talk about, well, what's happening in the future? And climate change is thought to probably exacerbate all of these factors that go into creating a dust storm. Firstly, we have a pretty good idea that as the planet warms up, when it rains, we get less frequent rain precipitation events. And when those precipitation events happen, they're more intense. And what that does is it creates more erosion. So more fine material that might be coming off of the surrounding landscape that's draining into the desert region, or coming off of mountains and draining into, for example, dry washes, which is this image at left. So you get these areas filled with more fine sediment that can be lofted into the atmosphere. Another thing that we know is happening is as the planet is warming, the landscape is drying, right? Our arid regions are becoming more arid, and we might have longer periods of drought. And what that does is it causes the surface to become drier, which makes it more apt for, or more effective at creating dust storms. And then we have like this loss of soil health, meaning the organic material in the soil just isn't there because we don't have as much vegetation. And so those factors go into just creating surfaces in general that are more conducive to dust storms. And then we also have this issue that is a big deal in the West, and obviously even as far north as Canada, is wildfire. Take an area that is covered in vegetation, and when you have a large wildfire, obviously you get rid of that vegetation. But in addition, you change the chemistry of the soil, making the soil more hydrophilic, meaning that water doesn't necessarily seep into the soil and make the soil moist, but rather it rolls off of the soil. And so a wildfire, post-wildfire, a burn scar is an area where dust storms will occur as well. And then we have this other component that's thinking about the future of dust storms that's not related to climate change, but rather how we manage water. And one of those things is the Sustainable Groundwater Management Act. This is an act in California designed to, or that requires communities to ensure that their aquifers are filled to, I can't remember, to some capacity, not 100%, but greater than it is right now. We've had these droughts in California. You can actually see from satellite that the land is sinking, and that's because we've taken so much water out of those underwater reservoirs or underground reservoirs. And so the way that communities respond to this is by fallowing agricultural lands. And that's what we're looking at left, an agricultural land that's been fallowed with the idea that, well, okay, now this community doesn't have to use as much water. But then by fallowing, we're creating these new areas that are probably good sources of dust, particularly when that happens in arid environments, in which there are a lot of those in the state of California. And so now I want to focus in on the southeastern corner of the state, the Salton Sea, in the next 5 minutes. It's a big topic, but what you're looking at right here is this large inland lake, one of the largest inland lakes in the western U.S. And in black here, and you'll see a little blue pin. That's a field site that I have there, a place where we make measurements. And so, and I'll show a picture of that in a little bit. But you can see this inland lake. This is the bottom of a subsea level basin, meaning that like water that is in the mountains or in the valleys surrounding that lake will all flow down into that area. If you're in the middle of the lake, everywhere you look, you would go uphill. And that lake is surrounded by agricultural regions as well, spanning back to the 1800s. And in 1904, the modern Salton Sea was created by an irrigation disaster. Essentially, water was being diverted from the Colorado River into the valley to the south of the Salton Sea in that image I just showed, starting back, I believe, in the late 1800s. And in 1904, through a series of events, the Colorado River water burst through the levees that had been created to divert some of that water for irrigation into the Imperial Valley. And essentially the entirety of the Colorado River was redirected into that area now that we think of as the Salton Sea for about 5 years before they were able to breach that levee. So that's really what created this modern lake that we have right now. And to make a long story short, that sea is now, the level of that sea and the area of that sea is declining quite rapidly. And the main reason why is basically that we don't divert Colorado River water, or we don't divert that much Colorado River water directly or indirectly into the Salton Sea anymore. And, water resources are really limited in the Western US. And what you're looking at here is a time series, and these little squiggles, this represents the height of the Salton Sea. And you'll notice these numbers are negative. This is meters above sea level, and it's a sub-sea level basin. And I think the really important thing is just to note that around 2003, the level starts going down. And then in 2017 as well, we have this very steady decline in the height of the Salton Sea. And what this is due to is basically, back in 2003, there was an agreement that was made to say, hey, we need to stop using so much water. Hey, California, the federal government said, you're using way more water from the Colorado River than you should be. And through this huge agreement, the end result was that there was going to be less water going into the Salton Sea. And this 2017 right here, this represents the time when we stopped putting water. In 2003, everybody knew, hey, the Salton Sea is going to decline. We got to come up with a solution. We'll put a little extra water into it until 2017 when we have a solution. And 2017 came and went. Nothing really happened, and the sea kept declining. And to see what that looks like, right? This is a very shallow body of water. Deepest point, I think, now is like on the order of 12 meters. And so here's what the shoreline looks like in 1985. And then here's what it looks like in 2025. And let me just flip through here. You can see that expanding, what we call a playa. So just a very large increase in area that used to be underwater that is no longer underwater. And to kind of, if we take that trend and we think about how that might look in time, what you're looking at right here are contours of height. And this blue line represents the Salton Sea as we know it right now. Well, in 2024, the contour of this, or the limit of the Salton Sea is, as we just kind of go forward in time to 2034, 2044, 54, and by 2064, potentially having maybe just a northern and southern end of the Salton Sea. And this just represents a problem of extraordinary magnitude. And I showed you this Owens Dry Lake earlier, that it's cost about north of $2 billion and ongoing to mitigate, to try to reduce the amount of dust that's coming off, this is a problem that's 3, 4, 5 times greater than that one. And there are a lot of community concerns associated with this shrinking Salton Sea as well. And I'm running out of time, so I'm going to go fast, but just to say that these blue lines represent rivers that are coming into the Salton Sea, and those rivers carry a lot of pollution historically. One of those rivers in the south is originating in Mexicali, and it's been one of the most polluted waterways in the country. But there's also all this agricultural runoff that's been going into the Salton Sea for decades, and there's a concern that, hey, DDT was used in this valley, and that DDT that's in the soil or that was underwater in the sediment is now being exposed to the air, and is that blowing around? And our group sees this good opportunity, or this rich opportunity, to try to mitigate at least some of the harmful human health impacts associated with dust storms, just by helping people to mitigate their exposure, meaning people need to have dust forecasts. And right now, our dust forecast products, specifically for that area, are not good. And what you're looking at on this vertical axis, this represents like the accuracy of a dust forecast that was in the area that now is gone. So there are no dust forecasts anymore. The dust forecasts we used to have. So the vertical axis is accuracy, and the horizontal axis says how many days ahead of time. And so if we look at, for example, a forecast day of 0, that means you wake up in the morning, you look at the dust forecast, and there's about a 5% chance it was accurate. So it's really not that great. And so we think, wow, we can do so much better than this. And my group, darn it, video didn't render. Sorry, my group has been out in the desert. This was that field, that little blue pin I showed you a while ago. We've been out in the desert for years now, measuring, taking instruments. We go out to dust storms. We were launching weather balloons in the middle of dust storms to improve our ability to model the weather events that create dust. And we see, so we're pretty good at modeling the weather now. And this is using like models that have been developed in the US that have been around for a long time. So building on the success of a specific model called the Weather Research and Forecasting Model, but essentially like tuning it to this region to figure out like, well, what do we need to do to make sure it's right? But the big issue is quantifying the land surface. We have to go out and understand how all of these different landscapes that are in the area, how much dust they produce when the meteorology is right for a dust storm. And I just have this picture because it shows the complexity of those the land surface. We have the lake, we have irrigated cropland, we have fallowed cropland, we have places on that now exposed playa, places that used to be underwater, that some are vegetated, some are barren. And so it's a really time-consuming process as well, because it actually means that we have to go out there on the land and make measurements. And so that it's expensive, it's time-consuming, but it's way cheaper than, for example, trying to mitigate, it's not something in the billions of dollars, but, more in the hundreds of thousands to millions of dollars. And it's something that would at least provide tools for the community to protect themselves, and even to like businesses to know, for example, when is a good time to fallow your lands or when maybe isn't. Can you delay your harvesting a couple days because we know that there's going to be a big windstorm and it's going to generate dust and you'll lose topsoil. So I'll stop there with this slide that has just some summary points. Thanks.
Awesome. Thanks, Amato. That was a really nice talk. And it's always just interesting and fun to hear more about the Salton Sea, because it's a truly crazy place. So we have some questions in the chat. Maybe you could take a couple minutes to just talk more about how you are measuring the dust storm severity, or talk a little bit more about your instrumentation setup, because you're on the ground rather than using the satellites, correct?
Yeah, so we use both of those things, but yeah, we're on the ground because nothing beats being out on the ground. And so this is like, this field site, for example, this tower right here, this is actually shooting a laser up into the sky. So when dust storms would blow over this site, we would be able to measure where the dust is, how much dust there is, like the top of the dust layer, the bottom of the dust layer, and then this instrument right here, this is a sun photometer. This is actually a NASA instrument that they put out at our field site. This is measuring some of the characteristics of the dust that are important for understanding and how those dust storms change the energy budget. So those are a couple instruments that we use to understand the characteristics of those dust storms. We also have some regular meteorological measurements as well, like wind speed, temperature, pressure, and then this right here, which would have been a weather balloon, right? So we actually are out in the middle of a dust storm, launching a balloon that has an instrument at the end of a long string that measures temperature, pressure, wind speed. And so we launch those in the middle of dust storms to try to understand the meteorological aspects of those dust storms as well. And way back on that earlier slide, we have a lot of instruments that give us more detailed information about the dust particles, their sizes. We go out and we measure their composition, and that means actually like collecting dust on tiny little pieces of tape that are made of carbon, and then we can take them to a pretty fancy microscope. And so those are some of the instruments that we use right now to understand both the weather and the dust that comes along with it.
Awesome. Another interesting question. How are dust storms in California affecting neighbors like Arizona? And maybe you could talk more generally about kind of the size of these dust storms.
Yeah, so it really depends on the characteristics of the storms themselves, right? So dust storms here in California can travel hundreds of miles for sure. It depends a little bit on where they're generated. So dust storms that are generated in the San Joaquin Valley, kind of in the center of the state, would probably not be traveling, over into Arizona or Nevada. Dust storms that are created in the Salton Sea, originate in the Salton Sea area, definitely would be traveling over through Arizona, like especially the communities, a pretty large community in Yuma, Arizona. So a lot of it, dust storms that are generated in the Mojave Desert definitely will be traveling over Nevada. It's a little bit hard to know, how much dust from California is going through Arizona, right? Because it's a big desert. And so dust is being generated all over the place.
Yeah.
And when I say a big desert, I mean like the Sonoran Desert, the Mojave Desert,
sure.
They span multiple states.
Okay, probably last question here. So the photos of fingers wiped across the solar panel seem to indicate that waterless cleaning could be feasible. Do you have any idea if waterless cleaning of the solar panels is practical? Is this kind of a technical way to move around this?
Yeah, I know this is a current area of research. What I've read on that kind of waterless cleaning is that it tends to cause a lot of damage to the PV panels, so it's not really economically viable. That would be the goal, but yeah, for right now, it is not something that's being implemented at a large scale.
Awesome. And maybe just really briefly, Amato, how did you get into the field? And maybe more generally, how did you get into dust? Because I think you maybe have pivoted into that a little bit more recently, right?
Well, I've actually always been interested in dust storms. I think from the days when I was an undergraduate student and I studied the dust in the tail of a comet as my senior project.
Oh, super cool.
Yeah, and so and I liked physics, I liked math, but I also like being out in the desert. I've always liked hiking and rock climbing and off-roading, and so taking my interest in math and my interest in the environment, it was a pretty awesome place. It was once I found out that, hey, dust storms are these big things that happen all over the place, and there's so much we don't know about them, particularly because they happen in places where people tend not to live, so we don't have a lot of measurements of dust storms. It seemed like, wow, this is what a natural place for me to start to do work. And it's been more recently that I've been out in the field. I used to do that just with computer models, but probably over the last 10 years, I've been focusing more on getting out in the field and making measurements that I think we need to improve our forecasting of dust.
Yeah, and you're in such a great location for it. I mean, it was always fun to head out to Anza Borrego in the Salton Sea when I was in La Jolla also.
And I'll be out there tomorrow morning again, bright and early.
Okay, great. Well, thanks. Right. Let's thank Professor Evan in the chat. Really appreciate your talk and your time this morning, Amato. Awesome. So we are halfway through the 95th hour of the Weather and Climate live stream. We are really coming towards the end here. Before we move on, let's briefly recap why we're here. Weather and climate forecasts are critical to everyone in this country. The U.S. is a world leader in weather and climate prediction. As an oceanographer myself, while I'm hosting on the half hours, I'd like to briefly highlight an oceanographic scientific innovation that federal support from the American public has made possible. So first, I'd like to highlight Alvin, which is a deep ocean research submersible owned by the U.S. Navy and Woods Hole Oceanographic Institution. Alvin allows 2 scientists and 1 pilot to dive for up to 9 hours at 6,500 meters, which is about 21,000 feet, to explore the deep ocean with its 2 robotic arms. In the late 1970s, marine geologists used Alvin to explore seafloor spreading centers in the East Pacific, and they discovered these deep-sea hydrothermal vents, which had rich biological communities. Of particular note is the discovery of black smokers, where superheated water from below Earth's crust comes through the ocean floor at temperatures of 400 C, or about 750 Fahrenheit, spewing out sulfide-bearing minerals that precipitate once they hit the ocean water. These black smokers are often between 2,500 to 3,000 meters deep, and despite being in the icy black, support a thriving ecosystem due to the fact that bacteria here participate in chemosynthesis, which means that they harvest chemical energy from minerals and chemicals rather than from sunlight and CO2. As primary producers, these vent microbes allow these ecological communities to flourish and show that the deep sea is teeming with life. Originally, hundreds of years ago, folks thought the deep sea was entirely lifeless. Dr. Bob Ballard called these hydrothermal vents a more important discovery than when he explored the sunken Titanic, which he also used Alvin to do. So the federal research support that leads to these sorts of technologies and discoveries is at risk, though. We ask you to please use the link on your screen to contact your representatives and to tell them to save our forecasts, to keep the lights on for weather and climate science, and research programs like allowing Alvin to go down to the deep ocean and explore. We'd like to keep this miracle alive. Our next speaker is going to be Margaret Duffy, one of our organizers. Margaret is an atmospheric scientist, and I'm not entirely sure what you're talking about today, Margaret.
Clouds.
Excellent. We love it.
All right. So today I'm going to tell you about clouds, their role in our climate, and their role in climate change. And here are some pretty pictures of clouds. Okay, so clouds do come in different types. And I think we've all spent some time looking up at the clouds and categorizing clouds by like what cute animals they look like and stuff. And when you become a climate scientist, you graduate from doing that to, looking at these other types of clouds. And so we categorize clouds by their type, by their height, their thickness. And there's a good reason why we do this. And that is because they impact the climate through their radiative effects. That's a technical term, and I'll say what that is. But the radiative impacts or the radiative effects of a cloud depend on the details of the cloud. And so that's why we need these different categories. Okay, so let's go over radiative effects. So let's say that there were no clouds. This little green circle is, I'm not super artistic. This is my little planet Earth. And then here, this is hopefully it's clear that this is the sun. This is the sunlight coming in, hitting planet Earth. This is the same sunlight that gives you a sunburn. And planet Earth also radiates away back out to space because of its temperature. And now let's throw some clouds into this little schematic here. The sunlight, this is a red arrow in the previous schematic because it's warming the planet, and the radiation leaving the planet has a net cooling effect. I'm not talking about climate change yet. I'm just talking about how planet Earth works. So if we throw a cloud in here, then the cloud reflects some of that sunlight back out to space and reduces the amount of sunlight that we see here on Earth, reducing that warming effect. So that's an overall cooling effect of a cloud. But clouds also have a warming effect because they trap the radiation that's trying to leave, and that has a net warming effect to those of us standing right here on the surface of the Earth. Okay, so clouds have both a cooling impact and a warming impact, which is why they play such a big role in our climate and are so tricky to study. Which one wins, warming or cooling? Well, it depends on the details of the cloud. And that's why we need these different categories. So high clouds typically have this warming effect, right? And specifically these like cirrocumulus and cirrus clouds, they're very thin. And so they don't have much of, don't have very much albedo, don't reflect very much of the incoming sunlight back out to space. But they do trap, they are still able to trap the radiation that's trying to leave. And so they have an overall warming effect on our climate. On the other hand, these very low clouds, like stratocumulus clouds and cumulus clouds, these tend to be very thick and very reflective. And so they're cooling effect winds because they're reflecting so much of the incoming sunlight back out to space. This is a bit of an oversimplification. I've talked about the thickness and the height of the cloud. The phase of the cloud also matters for its radiative effect. But we'll stick with this for today. Okay, so globally, if you take the average of all the clouds on the whole planet, does the warming effect win or the cooling effect win? Turns out to be the cooling effect. The planet is cooler than it would be if we had no clouds by a fair number of degrees, I think about 10 degrees Celsius, although that estimate is not perfect. Okay, so Earth is cooler than it would be without clouds. Thank you, clouds. But what about climate change? How is this effect changing with climate change? So now we have this understanding of what's going on in just a regular old climate, but how is this picture changing with warming? Okay, so I think you all are pretty familiar with this concept, but I'll just go over it again, get us on the same page. We have our emissions, our greenhouse gas emissions that comes from burning fossil fuels. And so that is adding to the concentrations of greenhouse gases in the atmosphere. And that has a warming effect on the planet through the greenhouse effect, which we're all pretty familiar with. So there's two important steps here. We burn the fossil fuel, so we do the emitting. The atmospheric concentrations increase. And remember, we've seen from other talks that some of that carbon dioxide, some of that carbon doesn't stay in the atmosphere. Some of it's absorbed by the ocean and various other places, but some of it does stay in the atmosphere. So when we increase our emissions, we increase the atmospheric concentrations. That's one step. And then the second step is that increase in concentrations has a greenhouse effect. The greenhouse effect is near the second arrow, and that's what affects warming. Okay. And so clouds are super important to this question of wanting to know how emissions translates into warming. There's actually a lot of uncertainty in both of these relationships. There's uncertainty in how emissions translate into concentrations, and then how concentrations translate into warming. And so that's obviously pretty important to pin down, right? Because if we wanted to, say, meet our goal of limiting warming to 2 degrees, we would need to know what levels of emissions that translated to, if we wanted to do a really good targeted job of trying to meet that goal. And so, the role of the scientist is to figure out what that is. And so there's two really big sources of uncertainty. In the relationship between emissions and concentrations, the biggest source of uncertainty is what we call carbon cycle feedbacks. And we've heard a lot of talks about that already. I won't talk about that today. But in this relationship between the concentrations in the atmosphere and the amount of warming that we see, the biggest uncertainty is the cloud feedbacks. So the role of changes in clouds is the biggest source of uncertainty in that relationship between concentrations and warming. By the way, that relationship is called the climate sensitivity, and that is something that you've probably heard if you've been tuning in to the live stream for a while. Okay, so clouds are one of the most important things, along with carbon cycle feedbacks, to sort out if we want to do a good job of relating emissions to warming. Okay. So we talked about the cloud radiative effect in the intro. And changes in the cloud radiative effect are more or less called cloud feedbacks. And so what makes cloud feedbacks? Why do we call them that? Well, what happens is the Earth warms due to the greenhouse effect. We know this. And because of that warming, clouds change. And they change in all sorts of ways depending on the details of the cloud. And remember, the clouds have an overall cooling effect. And so if clouds change in such a way as to increase their net cooling effect, then we would see less warming than we would without the cloud changes. And if clouds change in such a way as to decrease their cooling effect, then we see more warming than we would otherwise see without those changes in clouds. So this is why it's a feedback. And actually, it's been a pretty difficult problem to figure out whether the cloud feedback is this kind of scary amplifying feedback or this reassuring stabilizing feedback, because clouds are just so darn hard to study, and I'll talk more about why that is in a minute. Okay, so but we're gonna in a minute, a little figure with our best estimate of what the cloud feedback is going to pop up on the slide. And so if that estimate is over here, that means that the changes in clouds are having an overall cooling effect. And we would get less warming than we would otherwise get without those changes in clouds. And if the answer is over here, that means we get a little bit additional warming due to the changes in clouds. And this, the end of this blue bar is our best estimate. And so unfortunately, it's over here in this positive amplifying side of things. So we get a little bit more warming, or maybe more than a little bit, more warming than we would otherwise get without these changes in clouds, these responses of clouds to the warming from the greenhouse effect. But you'll notice, if you look at this horizontal black bar, that there's a lot of uncertainty in this estimate. And it's been really hard to pin down. This black bar even almost touches 0, meaning that we're pretty sure that it's a positive feedback. But it's taken a lot of work to be pretty sure that it's even a positive feedback, let alone and not a negative feedback. So I want to emphasize how big this bar is, and that is why this relationship between concentrations and warming is so uncertain and hard to pin down. Okay, but what this means overall, if you take one thing from this slide, it means that for a given increase in atmospheric greenhouse gas concentrations, we expect probably more warming than we would if the clouds weren't changing at all. So the cloud changes contribute a little bit of extra warming. We call that a positive feedback, even though it's a bad thing. So how do we know this? Lots of things, but historical observations is one of them. So we've heard about satellites and other observing systems that we can use to take a look at the clouds. That's in the that's what I'm kind of pointing out in the top left here. We also know from theory, we can sit around and think about the physics of the atmosphere and the cloud system, and learn things from ideas from physics. And then there are different kinds of climate models. I want to talk about 2 kinds of climate models today. One is cloud resolving climate models. And we can see from this little schematic here that cloud resolving climate models are cool because they have fine enough resolution that you can actually get some sense of what the clouds are doing in them, but they don't cover the whole globe. We can't at this point represent all, the whole globe in a cloud resolving model on climate timescales. We're getting there. There's been a lot of really awesome progress in that area, but we're not quite there to where we can run a cloud resolving model at super high resolution over the whole globe for a long time. On the other hand, we have these global climate models. You've probably heard of these. These are the ones that go into the IPCC report. These are global climate models. Global climate models are awesome because we can estimate all of the processes all at once. Obviously, you've heard a lot of talks on a lot of different subjects, and the global climate models take a stab at estimating all of those things all together and how they interact with each other. The problem with global climate models is that they, just due to limitations in computing power, they just only have so much resolution. And so the resolution is not fine enough to resolve all of the clouds. Okay, so that best estimate that we saw 2 slides ago here, this estimate came from a really, really cool paper by Stephen Sherwood, Mark Webb, and co-authors, where they basically they looked at what the observations were doing, what the theories were doing, what the models were doing, and they put those things all together using a statistical framework to give us this estimate of what the clouds were doing. So this estimate takes into account evidence from all of these different sources of information. Okay. So the total cloud feedback that we saw before, that's now this bottom row. I on the very first slide talked about how we have different kinds of clouds, and different kinds of clouds are changing in different ways and contributing differently to this bottom row. And that's what we're seeing in these top 6 rows. And I have a box just around one of them, the tropical marine low cloud. And we are going to just talk about that one type of cloud feedback today, but just note that there's also a lot of research happening on other kinds of cloud feedbacks too. And the reason why this tropical marine low cloud feedback is something that I want to talk to you all about today is that if you look at these error bars, they also are very large. This and what we call the anvil cloud area feedback are the 2 most uncertain cloud feedbacks, and the 2 kinds of clouds that are responsible for this large uncertainty in the total cloud feedback, if that makes sense. Okay, what are tropical marine low clouds? I think you all remember this figure from early slides. They're clouds like the stratocumulus clouds here that tend to have that cooling effect because they're so thick and they reflect so much sunlight back out to space. So they have such a cooling effect. And here's a little, just so we know on the globe where we are, right? Like this is the darker colors, the redder colors are where there's more low cloud. So we can see like off these kind of subtropical coastal regions that there are a lot of these low, thick stratocumulus clouds. These are what we call the stratocumulus regions. And so I just wanted to orient you as to where we're talking about. And it's these red regions on that graph. Okay, why is the tropical marine low cloud feedback positive? And remember, in this jargon, positive is actually a scary thing. So the low clouds have a net cooling effect in our normal climate. Well, they always have a net cooling effect because they reflect more radiation than they trap. But as the climate warms, so does the humidity profile through the atmosphere. And as the humidity profile changes, we're seeing a bigger what we call gradient, a bigger difference in the humidity at the top of the cloud than at the bottom of the cloud. And that can shrink the cloud because the clouds are made of the water vapor. And so with that bigger humidity gradient, we get smaller clouds. And having smaller of these, having these clouds be smaller, these reflective clouds, having them be smaller means that they're reflecting less sunlight back out to space and are overall having a net warming effect. Their changes are having a net warming effect. But it's actually complicated because there's another process in the atmosphere that tends to want that's happening with warming, another change in the atmosphere that's happening with warming, that tends to want to increase the size of these low, thick clouds. And that is now this profile, instead of being humidity, is temperature. A lot of times these low clouds are under a temperature inversion. You've probably heard of a temperature inversion in conversations about air quality. And temperature inversion just means that instead of temperature going down with height through the atmosphere, that near the surface it actually increases with height. And that tends to trap things because that's very what we call stable. And so and that includes clouds. So the increase in the inversion strength also increases the size of the cloud. So we have these competing effects on the tropical marine low clouds. We have the role of humidity wanting to shrink the size of the cloud, and we have the role of temperature wanting to increase the size of the cloud. And that is why this error bar is so big. We have these competing effects, and we have to sort out the details of these competing effects on the tropical marine low clouds. It turns out that that we think that the shrinking effect is greater than the increasing effect, but of course there's a lot of uncertainty there. Okay, so that's one challenge, right? Is that the clouds the cloud radiative effects and the cloud feedbacks result from compensating warming effects and cooling effects. And so we have to really quantify the warming effect, really quantify the cooling effect, and then look at the net effect in order to know the impact of the cloud changes on climate. And that just makes for really a lot of uncertainty. Another reason why there's a lot of uncertainty is the resolution of these global climate models, which is rapidly improving. But for now, global climate models tend to have a resolution of what we call 1 degree latitude by 1 degree longitude. And typically, depending on where you are on Earth, but typically a degree latitude and a degree longitude is about 60 miles. So if you think about a 60 mile by 60 mile grid box, and you think about the number of clouds in a 60 mile by 60 mile region, you realize we're totally not representing these clouds very well in our global climate models. And we have to do something called parameterize the impact of the cloud on the climate. That just means that we're basically estimating the overall effect of all of the clouds in the 60 mile by 60 mile grid box. Of course, that approximation leads to difficulty in representing clouds in global climate models. All right, so let me wrap it up and tell you a little bit more about the role of government funding in my own research. So one way forward to deal with all of these challenges that we have in studying clouds is something called cloud controlling factors. And the idea there is that rather than study the cloud itself, you kind of say, okay, we know that clouds depend on things like humidity and temperature and wind speed. And so we basically figure out what the humidity, temperature, wind speed, et cetera, are doing, and then use that to inform an educated guess at what the cloud should be doing. And this is beneficial because of it sidesteps some of the issues that I mentioned before. And we can derive this relationship from observations. We don't need climate models. We only need climate models to understand then how these, what we call environmental or cloud controlling factors, are changing. So it reduces the role of global climate models in the analysis and sidesteps that, that issue that we're having with climate models not having the full resolution to be able to represent clouds. This has been, there's been a lot of work on this subject. We've made great progress. What I'm showing here is a figure where the climate model estimates of the low cloud changes are on the right, and the cloud controlling factor estimate is on the left. And we can see, if we look at how big this spread is, that we're really able to reduce our uncertainty using this method. But I think that we can reduce the uncertainty even more. This is focused on low clouds, but what about high clouds? Have we thought of all the predictors? What about nonlinear relationships between clouds and their environment? So there's a whole host of ways that we can, I think, make more progress on this. And I wrote a proposal to NOAA about a year and a half ago. I wrote it. I'm early career, so this was actually my very first proposal that I had recommended for funding as the lead PI. It was recommended for funding, but unfortunately, the money has not arrived. It was supposed to arrive in January of this year, but because of the federal funding changes to NOAA, it just hasn't arrived. And so we have not been able to do this work, trying to make more progress on narrowing that uncertainty in cloud changes, and ultimately on pinning down the relationship between greenhouse gas concentrations and warming. And so just wanted to mention that I'm kind of bummed about that. This was my first one. And so it's been kind of hard to not be able to do the work that I wanted to do.
Oh, well,
Hit me
thanks for
with
the
your
great
questions.
presentation, Margaret. Sorry to hear about that. That's a real bummer. So we probably have time for maybe 2 or 3 questions. So I'll start with a really simple one. What potential cloud feedback effects might come from proposals to seed clouds to induce rain or to increase their reflectivity? And that's a joke because that feels pretty difficult, but what do you think?
Yeah, okay. I don't know too much about cloud seeding. I think you can see from this talk why some people have had the idea, like why it's popped into their heads, right? Because clouds do have this net cooling effect. But we also know, I'm just going to speak generally here, right? We also know that messing with the climate is bad, right? Like we're seeing that in real time. And the reason why it's bad is because we're adapted to a particular climate, right? Like we live where we live. We have settlements where we settle. We have farms where there are farms, because we're adapted to a particular climate. And so when we go in and mess with stuff, we change that. And then we create a climate that we're not adapted to. And so this concern about unintended consequences is 100% warranted. Because typically things like, this is what we call geoengineering. So something like cloud seeding or stratospheric aerosol injection, typically that doesn't get us back to the climate that we had before, right? That's not the same as taking out the carbon dioxide that we put in and returning our climate back to normal. It's just 2 different changes to the climate system. Kind of like how we've been putting carbon dioxide and aerosols into the atmosphere at the same time. One has a warming effect and one has a cooling effect, but we're still seeing really big changes in our climate. And so it's a scary thing. So I'm not saying that we shouldn't study this, and I'm not saying that it's a bad idea, but I think the hesitation is extremely warranted.
Yeah. And one thing that someone has brought up here is that we still have to find joy in our marvelous world where we can. What's the coolest joyful cloud for you personally?
The coolest joyful cloud. Okay, I love these stratocumulus clouds. They're so thick and reflective, and like just like the stratocumulus regions are just so interesting and fun to study. And so yeah, I love seeing some good stratocumulus clouds. Although I will also give a shout out. We don't see these too often, but the lenticular clouds that come from like when you have like a wave that sometimes is induced by, say, topography. You can see these really cool cloud shapes too. So gotta love looking at clouds. And thank you for asking such a positive question.
Yeah, lenticular clouds are pretty awesome. In Seattle, occasionally you can see one over Mount Rainier, which is pretty sweet.
What a treat.
Yeah. All right. Well, thanks, Margaret. Appreciate you stepping in there and talking for a bit about clouds and showing some of your interest and passion.
Thank you.
So for those of you who are just joining, we have now entered hour 96 of the Weather and Climate live stream. That's 96 out of 100. So we're really reaching the final few hours here. For those of you just joining, my name is Matt Luongo. I'm your host. I'm a climate scientist and oceanographer. Thank you for joining us. We are nearing the end, but before that, we have another great hour of weather and climate science for you. We'll be speaking to Ash Gilbert and Sarah Ogle, who are both PhD candidates in climate science. Before we begin, we want to remind you why we're here on your screens. We know how important weather and climate forecasts are to you and to everyone in this country. Luckily, the US has long been a world leader in weather and climate prediction. We developed the first computerized weather forecast to help you know what you can expect in the coming weeks, and we made the first computer models of the climate impacts of carbon pollution, so you can know what to expect in the decades to come. To make these forecasts work, we've created an unparalleled network of observations using everything from weather stations to satellites, planes, balloons, boats, and floats. The resulting forecasting and observation system is a true scientific miracle, and we're excited to share details from that with you here over the past few days. This miracle was made possible by decades of investment by you, the American public. But in recent weeks, the funding cuts have put this at risk. Weather stations are so short-staffed that we are losing our observational coverage, which is already hurting our forecasts. Laboratories dedicated to understanding our climate's future are being closed or shrunk, and funding for our basic understanding of the weather and climate is disappearing. The administration's proposed budget being considered now by Congress is far, far worse. It would cut the NSF and NASA's Earth science budgets in half, completely eliminate NOAA's research arm, and end foundational programs for young scientists like the NSF Research Experience for Undergraduate and the Graduate Research Fellowship. But it doesn't have to be this way. If you like what you see here, then we ask you to please use the link on your screen to contact your representatives and tell them to save our forecasts, to keep the lights on for weather and climate science so we can keep this miracle alive. And please spread the word to join this live stream in the final hours. Last, a brief reminder that all speakers are here in their own personal capacity and their views are their own. So we've seen a lot of great talks over the past few days. I've learned so much, and it's been really nice to see the positivity and catch up with colleagues. And our next speaker will be no exception. Our first speaker in this hour will be Ash Gilbert, a PhD student in climate science. Ash will be talking to us today about how to improve a climate model. Please put questions for Ash in the chat, and we'll get to them in a little bit. Morning, Ash.
Hey, all right, so I feel like I've been set up very well because I will also kind of be talking about clouds, so thank you for that, Margaret. So today I'm going to talk about how to improve a climate model. So just wanted to give a little start about me. I graduated in 2022 with my bachelor's in climate meteorology from the University of Michigan. And then when I was at Michigan, I had the chance to go to Greenland when I was a sophomore, which sort of forever cemented my love of polar science. Here's me with a picture of Russell Glacier. And after Michigan, why is this not working? I went to the University of Colorado Boulder, and I got my master's recently this spring, and currently I am a PhD candidate there. But let me start out. So what is a climate model? So in a climate model, we have different components. And so for example, we have in the atmosphere component, we have like cloud physics, convection, cloud formation, which I know Margaret talked about. And then in the ocean component, we've got biogeochemistry, eddies, and then here on this globe, I have plotted SST, or sea surface temperatures. We also have a wave component, so we sort of have a wave parameterization that sort of models how they move across. And then we also have a river component, which sort of models river runoff from land, land component, which we sort of model the carbon cycle, gross primary production, like plant, which is basically plant photosynthesis, and it's plotted here on the land surface. We also model ice sheets, just Greenland, and glaciers. And then lastly, we also have sea ice, which we sort of parameterize and it melt, ice formation. We have heat transfer within the ice, and I've plotted here the sea ice concentration. And all of these components talk to each other using a climate model coupler, which exchanges data between the components and sometimes transforms data between grids, because often the atmosphere and the ocean sea ice have different grids. And all these components in the coupler working together make up a climate model that creates a simulated representation of Earth's climate. So why do we care that climate models are accurate? Well, we need to have the best representation of the Earth possible to make the most accurate prediction of climate and to understand what's going on right now. Looking here, you can see that this is the global temperature. Well, again, this has been shown various forms over the last couple of days. We sort of have various observational data sets in black and two sets of sort of models, CMAP 5 in red and CMAP 6 in blue. You can see that the models do a pretty good job at simulating the past climate, but there's room for improvement. You know, and also with models, we can do things that are not possible to do with observations to understand current and past climate. For example, my current project, which I'm not presenting here, puts observed winds from 1980 to 2023 in a pre-industrial climate to see how much Arctic warming and sea ice loss the winds can cause alone. I cannot do that kind of assessment with observations. But to get that wind contribution to warming and sea ice loss and trust it, I have to have a good climate model. So now I'm going to show you one of the ways that climate models are improved with the case study from my own work. This is my first PhD project. I'm going to improve a parameterization, this is the official definition from the American Meteorological Society Glossary, which is an amazing resource. Basically it says that a parameterization is a thing that's too small for us to model directly, so we sort of represent it with sets of equations or variables. For example, a parameterization might be, we can't model a 1 kilometer cloud in a 100 kilometer grid box, as Margaret explained previously, so we parameterize it. And what I want to improve in a climate model was supercooled liquid water optics, which is a lot of big words, so let's splice it. So fun thing, water can be liquid down to 240 Kelvin or negative 33 degrees C or negative 27.4 degrees Fahrenheit. And we call this water supercooled. Now to explain optics, I'm going to do a quick primer on black body radiation. So radiation is the emission of energy, and everything with a temperature greater than 0 degrees Kelvin emits radiation. Y'all are emitting radiation right now. And black body radiation is the idealized radiation an object emits at every wavelength in the electromagnetic spectrum as a function of the temperature of the object. You can describe the black body radiation using this equation called Planck's law. Most of this is constants, but what you need to know to pay attention is this sort of variable B. That's the amount of energy emitted at a given wavelength and object temperature. So lambda is a wavelength and temperature is, well, T is temperature. This nasty little equation produces this lovely curve called the Planck blackbody curve. And we can get different curves depending on different object temperatures. So, the larger the temperature, the higher the peak of the blackbody curve, because, hotter objects emit more energy. So why am I talking about blackbody radiation? Well, it turns out that both the sun and the earth approximate a blackbody. So this is the sun and the earth. I don't know why the optics is there. I think that's the later part of the animation. Sorry, this was pulled together and finished at like 11 p.m. last night. So this is the sun's blackbody curve and the earth's. The sun mostly emits in the visible part of the spectrum, which is why we can see sunlight. And this type of radiation is called shortwave. The Earth has a much lower temperature than the sun and emits in an invisible part of the spectrum called long wave. But these are the sun and Earth spectra right at their surfaces. What happens when the long and shortwave radiation passes through the atmosphere? Well, we get something that looks like this. You can see that there's bits missing from our spectra. Looks like the atmosphere took bites out of our spectra. And there's those bites are different gases like greenhouse gases and clouds in the atmosphere absorbing and scattering the radiation. Radiation. So not all radiation emitted by the sun reaches the surface, and not all radiation emitted by the Earth reaches space. And optics are how we describe the absorption and scattering as a function of wavelength for a given gas or liquid, like water. So how do optics work for a liquid water droplet, for example? Well, radiation can be scattered, or it can be absorbed by the droplet. And we represent the combination of scattering and absorption for a droplet as the complex refractive index, or CRI. And this CRI, like all optics, is again a function of radiation wavelength. But why do we care about liquid water optics? Well, I mentioned previously that clouds scatter and absorb radiation, and optics describe how they do that. But how clouds affect radiation depends on whether the radiation is shortwave or longwave. Shortwave radiation from the sun is reflected and absorbed by the ground, but it is also reflected by the clouds. Now, for long-wave radiation, the Earth, clouds, and atmosphere, and the atmospheric gases, including water vapor, all absorb and emit long-wave. In our climate models, we need to model all of these cloud radiation interactions in order to model our surface energy budget and surface temperature. Now, to do that, we need to know cloud properties, like the cloud temperature, ice crystal radius and concentration, which is basically like the number of ice crystals in a certain volume, and the liquid droplet radius and concentration. And now we take these cloud properties that we have, and we simulate them in a climate model along with the liquid water and ice optics, and we put them into the radiative transfer part of the model, the part of the model that sort of does radiation, and that's how we get to the amounts of long wave and short wave absorbed and scattered by clouds in a climate model. So now that we know what supercooled liquid water optics mean and why they're important, they help us calculate how much radiation supercooled liquid water droplets scatter and absorb, and they in turn help us model the Earth's energy budget and surface temperature. Now for my case study, I'm only going to be caring about the long wave radiation being emitted downward from clouds, aka downwelling long wave radiation, and this is because I'm interested in potential impacts on surface temperature. All right, so now again, we know what supercooled liquid water optics are and why they're important. I'm going to use them to walk through a case study of how to improve a climate model. So first, we sort of start with this new knowledge. In our case, supercooled liquid water optics. We find this cool thing. Then we test it in sort of some specific scenarios to see if it has an effect. And then we look at the effect in a large, in a climate model on a large scale. First, starting with the new knowledge. So generally, this sort of new knowledge comes from lab experiments, field campaigns, satellites, surface station data, or theory. But in our case, it comes from lab experiments. So here, I'm just going to be focusing on the right half of the graph. The top row is the part of the CRI that describes scattering, and the bottom part is describing absorption. And so the x-axis is the wave number, which is another way to say wavelength, which is along the top. And we're looking in the long wave part of the electromagnetic spectrum. This is looking at a summary of different liquid and ice optics from a variety of different laboratory studies. The green is how ice absorbs and scatters at different temperatures. The blue is how liquid water behaves at room temperature. And now the magenta and black, those are supercooled liquid water absorption and scattering. And you can see that they are different from both the room temperature water and the ice. These measurements of supercooled liquid CRI came from two studies, both published in 2005, Zetsky and Wagner. Sort of see at the bottom. Several studies by Rowe and others synthesized these lab measurements into full scattering and absorption CRI spectra for several different temperatures of supercooled liquid water. This graph shows that warmer supercooled liquid water at 273 K or Kelvin, plotted in red, behaves the most like room temperature water, which is plotted in black, but it's still different. And at 240 Kelvin supercooled liquid water, plotted in blue, the coldest possible, behaves the least like room temperature water. So to conclude, optics matter optics for supercooled liquid water are different than room temperature water. And we know that optics matter for modeling long wave radiation. So does accounting for supercooled liquid water change the modeled radiation? We need to check this out. So, we test sort of new knowledge in specific scenarios. We use sort of smaller models. They may be line-by-line radiative transfer model, which are really high resolution. We use large eddy simulations, regional scale models. We can also use other specialized models, like, it's only sort of doing one model component, it has higher resolution, limited domain, etc. In this case, I'm using line-by-line radiative transfer models. In this case, called DISORT. We scientists love to name our models fun things. This work was done by a mentor and co-author of mine, Penny Rowe. Here, she took average cloud properties from the Arctic for a supercooled liquid cloud and modeled the downwelling long-wave spectra with two sets of liquid water optics, one at 300 Kelvin and another at 240 Kelvin. You can see that the 240 Kelvin optics in pink produce slightly more downwelling long-wave radiation than the 300 Kelvin. In total, summing the area between the two spectra, which is called flux, using the optics with the proper temperature for a supercooled liquid cloud modeled 1.7 watts per meter squared more downwelling long-wave flux than using optics that didn't account for the cloud temperature. But that was just using average cloud properties. How about applying it to observed cloud properties? So using profiles collected in the Antarctic, Rowe retrieved cloud properties, and then she used the radiative transfer model called DISORT again and fed it those observed cloud properties to simulate the downwelling radiance for each cloud twice. The first time, she only used the room temperature 300 Kelvin optics, or CRI, and the second time, she matched the cloud temperature to the optics CRI temperature, aka making the optics temperature dependent. Example of this profile is shown here on the left. And like previous spectra, we see that using the optics with the that match the temperature of the supercooled liquid cloud produces more downwelling long-wave radiation than using only 300 Kelvin optics. Now this is one profile. Rowe had several hundred. And so this is where I come in. I took each of these profiles. I calculated the area between the radiation produced by the temperature-dependent optics and the 300 Kelvin optics, aka the flux difference, and I plotted them as a function of optical depth, or the thickness of the cloud as it appears to radiation. I also colored each point according to the liquid fraction, i.e. the higher percent of the cloud is liquid, the more green it is. The point of this graph was to see what kind of clouds using the temperature-dependent optics mattered the most. As you can see, optically thin clouds with optical depths between 0 and 4, and more liquid clouds, sort of more green, produce the largest difference in modeled fluxes, 1.75 watts per meter squared. So, i.e. using the incorrect 300 Kelvin optics for a supercooled liquid cloud matters the most for thin liquid clouds. So to summarize this section, radiative transfer models underestimate downwelling long-wave radiation from supercooled clouds by about 1.7 watts per meter squared, and it's particularly for thin liquid clouds. And if we use the wrong optics, it's not a big error, relatively speaking. Wrong thing. All right, next slide. So now I want to put the change in a climate model. So major climate models assume that the radiation model, that all liquid water behaves like room temperature water, which is, we've shown that's not true. And I have to alter it now to put it so it fits in the climate model format, which I use CESM for, which involved a lot of fun self-learning Fortran, running into CESM errors. But more importantly, this is not a high resolution line-by-line radiative transfer model like I was just using. CESM has 14 long-wave bands, which is much simpler for the climate model to use, but we do lose some information. And I only had to was only able to look at one temperature optic set at a time, i.e. treat all water as if it was supercooled. And I did this because I wanted to see the effect on a large scale here. It wasn't worth doing the effort to match the cloud temp to the dataset temp because that would be a lot of coding work, i.e. Looking at one temperature optic set is the biggest hammer, and if we don't see any effect, it's not worth trading it for a smaller, harder to implement hammer. My first model run was 40 years long. The atmosphere was free running. I didn't constrain it. And it was in a pre-industrial climate because I didn't want the forcing to change. That would just be another variable that I'm adding. And I ran it for 3 different sets of optics. So the basic default CSM control optics, 240 Kelvin and 273 Kelvin. So on the left is the average downwind long wave at the surface from the control. And then the 2 plots to the right show the difference between the 240 Kelvin and the control optics. If you're seeing red, that means that the temperature-dependent optics, the supercooled optics, produced more long wave than the control. So you're seeing here that we are getting more long wave when we use the supercooled in the Arctic, which is where we do have a lot of supercooled liquid clouds. And then the second run I did is very similar, but now I have 3 ensemble members, so I sort of ran that sort of 40-year run 3 times with just little variations in the initial condition. I wanted to do that to sample the internal variability of the climate system. I also nudged the atmosphere to observations because I wanted to constrain the atmosphere such that I didn't get like different storm systems in different optics runs. And this time I only ran the control and 263 Kelvin. And you can see here that we still have red everywhere, so we're still getting more when we use the supercooled optics. But we also have stippling. The stippling shows that the mean downwind long wave radiation is statistically significant from the control, which means that we're seeing a significant difference. And that difference is about 1 to 2 watts per meter squared. And I also looked at surface temperature because, again, if you're changing the amount of downwind long wave the surface receives, you might be changing the energy budget. So you can see here that we do have slightly higher temperatures, like maybe 0.3, 0.6 Kelvin, which is not that big, but it's not nothing. And so to wrap up, when I simulated this, when I had the supercooled optics, the climate model, I simulated 1 to 2 watts per meter squared more downwind long wave radiation. It's a pretty small effect, and it's what we expected. But since it's small, it's also not a priority in updating the model, but it is on the list. And so that's how you go from finding sort of like, new knowledge to implementing it in a climate model. And lastly, I just want to say that I was introduced to this sort of whole optics project during a National Science Foundation RU during the summer of 2020 when I was an undergrad. I was working on sort of the small effect testing portion then, but I liked the project so much that I ended up writing a proposal for sort of the climate model testing for an NSF graduate research fellowship when I was a senior undergrad. I received that fellowship, which is then sort of funded 3 years of my grad school. And with that funding, I did the work that I laid out in my proposal, some of which I showed here, and the rest has been written up in a paper available for preprint. So NSF has basically supported my entire scientific career, and it enables these studies like this that suggest incremental improvements to models, which aren't big scientific breakthroughs or anything, but still contribute to more accurate and better climate models that other scientists use for big breakthroughs. So thank you. Any questions?
Awesome. Thanks, Ash. And just to echo, this came up yesterday when I was hosting as well, just the importance of these NSF REU experiences. I think so many folks have kind of gotten into the field after kind of taking the plunge over the summer and doing an REU and learning what research is. So, I mean, it's cool that that you were working on a similar topic even, and then you decided it was cool enough to go to grad school for. Personally, I did one and I decided I like research, I don't like this topic, and I pivoted pretty intensely. So we have a couple of questions about supercooled water,
All right.
supercooled liquid water. Could you maybe just talk about like where we might expect to find this in the atmosphere, like in the real world?
Yeah, so supercooled liquid occurs all throughout the atmosphere. and we get a lot of it, but it's particularly important for the Arctic and the Antarctic because pretty much all liquid that we get in clouds there is supercooled. So these optics have the biggest effect there.
Okay. Another question we had was, what's your favorite wave number in the spectrum?
Oh gosh, favorite wave number. Man, it might be I wouldn't say it's not a favorite number, it's a favorite window. So there's a window between about like 780 and 1,000 wave numbers, which is called the atmospheric window. It's where the atmosphere is basically transparent to water vapor, and it's where we do a lot of sort of satellite observations of the surface.
Cool. Host privilege in asking a personal question myself. I don't even know how to guess how many parameterizations are in these climate models. Yeah, I don't even know what order it would be. Like, it's certainly more than hundreds, but how did you kind of narrow in on this parameterization? And is there another one that you would be kind of interested in like picking up on next?
Yeah, so I guess I got interested in it because it's sort of, with the small scale testing, we sort of found, hey, there's this 1 to 2 watts per meter square error. Like, does this propagate to a climate model? As far as actually finding it, that took a lot of hunting through the Fortran code. So much hunting.
Yeah, I can empathize with that one.
Yeah. And then when I initially found it, I had to figure out the file format, be able to replicate it, which was not clear. And then also, like, somebody had forgotten to divide by the density of water, and they had to hard code it in later, which caused problems. I had to rerun stuff. So if anyone's from CSN development team is listening, please fix that error and that file. But as far as the next parameterization I'd be interested in, I think, I talked a little bit about like nudging the atmosphere to observations. That's something that I kind of used in this project and really use now, and I would love to make improvements on that. It's a really useful way for like basically inserting observations into a model, or at least observations of the wind components.
Cool. And, I think for those of us who are listening, the Fortran code is quite old that Ash is talking about. It was originally written, it stands for Formula Translation, and it was originally used with punch cards. So we're talking some pretty old code. This is not Python or something that you can just boot up on your laptop. This is run on a compiler on a supercomputer. So props to you for making that work.
Thanks.
Okay, last question. Where do you see, do you see yourself moving more in this supercooled liquid water direction as your PhD progresses, or are you more interested in kind of larger climate, global question? Where do you see yourself going next?
I definitely see myself going. So this project is sort of done for me. Like the paper's out there. It's still in review. I need to get the reviews back. But once I do that and publish this paper, I'm kind of done with this project. I think that I will definitely go into the more like widespread Arctic climate change attribution. Like I said, my current project is looking at how much the observed winds and sort of changes in mean state sea ice thickness we can attribute sort of recent warming and sea ice loss to. That project that I just submitted like a couple weeks ago to a journal. And then after that, I'm going to look at attributing sort of different types of anthropogenic forcing, like greenhouse gases, aerosols, biomass burning, see how much we can attribute changes in the Arctic to each of those. And that's definitely more like broader scale.
Cool. Awesome. Well, thanks, Ash, for the great presentation. Let's give a little bit of love in the chat. Appreciate you joining us this morning.
Yeah.
So for those of you who are just joining, before we move on, let's briefly recap why we're here. We're halfway through the 96th hour of the Weather and Climate live stream. We only have a few hours left. It's been pretty amazing what we've seen so far. And part of the reason that you've seen the community band together and pull this together is because weather and climate forecasts are really critical to everyone in this country. The US is a world leader in weather and climate prediction. And as an oceanographer myself, while I'm hosting on these half hours, I'm briefly highlighting an oceanographic scientific innovation that federal support from the American public has made possible. This is kind of an oceanographic / atmospheric innovation, but I'd be remiss if I didn't mention the work that atmospheric scientist Suki Manabe and oceanographer Kirk Bryan did in the 1960s and 1970s at NOAA's Geophysical Fluid Dynamics Lab in Princeton, New Jersey, where they created a coupled climate model. This work ultimately contributed to Manabe being awarded the 2021 Nobel Prize in Physics, which was a really momentous period for our discipline. So throughout this live stream, including in Ash's recent talk, many of my colleagues have presented work that has used complex global climate models that contain multiple coupled components: atmosphere, ice, land, sea ice sheets, everything that we can think of, waves. And these models are written with millions of lines of Fortran code. I hope you've seen how powerful these GCMs are and how important they are for understanding our past, present, and future. And all of this work really, really rests on the shoulders of the 1969 paper in which Manabe and Bryan at NOAA GFDL successfully coupled the ocean and atmosphere in their models to create a simulation of mean global climate. Now, this was a really simplistic Earth and a simplistic coupling, but it showed an estimate of the climate as the ocean and atmosphere interact together. As time went on, Manabe and others iterated on this work to add complexity, for instance, adding realistic continents and adding multiple levels of the ocean and the atmosphere. And then they were able to research the time-dependent response of the climate to global warming. And to this day, climate scientists can really see Suki Manabe's fingerprints all over the choices of forcing schemes and GCM simulations that we analyze and present to the public in our IPCC reports. If any of you saw Isaac Held's keynote on Friday night, he credited a lot of this continued success to the stability afforded by NOAA's federal support over the many decades at GFDL. And the federal support that leads to these sorts of technologies and discoveries is at risk. We ask you to please use the link on your screen to contact your representatives and tell them to save our forecasts. That's www.wclivestream.com/act to keep the lights on for weather and climate science so we can keep this miracle alive. Our next speaker will be Sarah Ogle. Sarah's coming from La Jolla, California, and is a PhD student in climate science, and we'll be talking about water in California. Morning, Sarah.
Hi, how are you, Matt?
Great.
Great. Well, thank you, Matt. This has been a wonderful live stream. Hi, my name is Sarah Ogle, and I'd like to share the history of something that we all depend on, water. First, let me introduce myself. I go next. Thank you. How do I get next?
Can you click it? Is there a little arrow on your screen when you click it?
Oh, there we go. Okay.
Perfect.
All right, awesome. Okay, so first I'd like to introduce myself. So I have always loved weather, and this might be the only thing that you remember from this presentation, but I was a cloud for Halloween in 5th grade and homemade this costume. Okay. I also joined the Cloud Appreciation Society at a young age, and I've been enjoying all of the cloud talks that we've been having. Shout out to Margaret. And this is the cloud of the month for June right now. Thanks. And the National Weather Service website is probably my most visited website. And today we're having a rare occurrence in San Diego in June. We have some rain and even some lightning around. So then in college, I studied geology. And so here's a quintessential geologist picture with the hard hat in a quarry. And after college, I joined the U.S. Geological Survey as a hydrologist, which is a scientist who studies water. And the USGS is a really important government agency that works with many partners to provide objective and impartial science to resource managers, emergency response managers, and the public. So I've been working at the U.S. Geological Survey during most summers of my PhD program at Scripps Institution of Oceanography, and I've also had the opportunity to be a teaching assistant at Scripps. So today I'm going to introduce you to freshwater on Earth, something that we all know well and depend on. Then I will share a timeline of the history of water, inspired by my TAing of the class SIO 35, which is just called water. And then I will share some current challenges that we have with water and how they relate to my research. So let's dive in. So freshwater is only 2.5% of Earth's water. So this is a really tiny amount, and we depend on this a lot. Unfortunately, this 2.5% is mostly in ice caps and glaciers, so it's really hard for us to access. And then 20% of that 2.5% is in groundwater, which we've been relying on a lot, probably too much. The rest of that little tiny 1% is in lakes, soil, and rivers, and the atmosphere. So really the water that we have access to is a really small amount of our water supply, and it's important that we conserve this water and help keep it clean for everybody. So let's go back in time and explore how we got to this point where we have water on Earth. So we're going to go all the way back 13.8 billion years ago. This is when the universe began in the Big Bang, and hydrogen formed during this time. And we know this because we can look back in time using the Hubble Space Telescope and other tools, and we can see way, way, way in the past. So this picture is looking back 13.2 billion years ago. And we can also sense cosmic microwave background radiation that is remnant of the Big Bang. So after the Big Bang, we have elements, including oxygen, that form during fusion in stars. And again, we can see these new stars with the Hubble Space Telescope. And then we have heavy elements that form in supernova. So we are all made of stardust. I just think this is a really neat fact and puts things in perspective. It also shows that hydrogen and oxygen, the elements that make up water, H2O, have existed since nearly the beginning of our universe. So 4.6 billion years ago, so if we're fast forwarding many, many billions of years forward, was the birth of our solar system. And the red circle shows where Earth is. And this is an artist's rendition. It doesn't look exactly like this, but this shows that Earth is at a very unique position in the solar system. We get just the right amount of sunlight for life to be able to be on Earth and for water to be able to be in 3 different phases. So 4.4 billion years ago, something happened that was crucial to allowing us to have the Earth that we have today. So Earth developed a liquid outer core, which helps create a magnetic field, which protects the Earth from solar wind. So without this magnetic field, we would not be able to have an atmosphere. So the early atmosphere on Earth, it just blew away in the solar wind. But now with the magnetic field, we can keep an atmosphere, and when the solar wind interacts with this magnetic field, we see the beautiful aurora borealis. So about 4 billion years ago, Earth gradually cooled down enough to have liquid water. So when Earth was really young, it was super, super hot, lots of volcanoes, as you can see in these images. And these volcanic eruptions released a lot of water vapor into the atmosphere, which condensed and formed clouds. There may have also been some comet contribution to water as well. So as Earth was cooling, more clouds formed, and these clouds rained, which eventually formed our oceans. So it's kind of crazy to think about our oceans forming 4 billion years ago from rainfall. It's a lot of rain. So then fast forward to 3.5 billion years ago, this is when we had the simplest life on Earth. And it took a really long time for this life to become life as we know it today. But eventually this life began to photosynthesize. And photosynthesis releases oxygen. And so this photosynthesis released oxygen into our atmosphere and gradually led to the atmosphere that we have today. So the atmosphere transformed from being a really water vapor, ammonia and carbon dioxide and methane-rich atmosphere to being what it is today, where we have tons of nitrogen and oxygen and some carbon dioxide. So at 2.4 billion years ago, we have a lot of the things we need. We have water in all 3 phases, we have the oceans, and we have an atmosphere with oxygen. But the continents look really different than what they are today. So the continents are always moving due to plate tectonics. So they're kind of like a crust of 11 plates floating on the mantle, and they move around all the time. So the last time that we had a supercontinent, so all of the plates in one continent, was 250 million years ago in the Permian. So this was called Pangaea. And then 200 million years ago, Pangaea broke up into Laurasia and Gondwanaland, possibly the best name of a continent. Then in the Jurassic and the Cretaceous, you can see the continents moving a little bit closer to what they are today. You might be wondering, why am I talking about the continents? Well, tectonics influences ocean circulation, atmospheric circulation, drainage divides, so when rainfall falls, where does that rainfall run off to? And it influences the distribution of volcanoes and vents. So all of this is really important to the distribution of water and how climate plays out on Earth. So we're going to fast forward to now what the continents look like approximately today. But before we get there, we're going to look at what CO2, carbon dioxide, has looked like in the past. So in my previous slide, we ended in the Cretaceous, okay? And so we're going to start just a little bit after that at 60 million years ago. And I liked this schematic because it says kind of some funny things like alligators in the Arctic 50 million years ago, maybe. And so you can see that atmospheric CO2, the amount of carbon dioxide in the atmosphere, used to be a lot higher. But as we got to the tectonics that we have today, we've entered these relatively low levels of carbon dioxide and these ice age cycles. So the last time that carbon dioxide was as high as it is right now was 3 million years ago, okay? And the last time that Earth was as hot as today is 125,000 years ago. And sometime in those past 3 million years, probably around 3 million years ago, Greenland and Antarctic ice was completely melted. There have been some talks that have talked some about Greenland ice. That was awesome. But I just like to show this because it gives us some perspective about where we are today. And then you can see some potential future scenarios. And we don't really want to get to a point where carbon dioxide is any higher than it is now. So about 12,000 years ago, there was the last ice age. And we know this from studying ice cores. So this is a neat image of the Laurentide ice sheet. So I went to school in Minnesota, and it was right about where the ice sheet started to end. And we got to look at the remnants of what these ice sheets did. So they deposit a lot of sediment and show a lot of evidence of changing the landscape. And this is a photo of showing where we can learn about past climate. So we can drill ice cores and analyze them and reconstruct what the climate was like in the past. And that can be helpful for understanding what it'll be like in the future. So glaciers carved the landscape into what we see today. And this includes this beautiful U-shaped valley and Yosemite and many, many other examples. So now let's get into specifically in the United States, what is happening with our water supply. So I found this map from the Library of Congress, and it's the rivers of the United States in 1870. So over the past few hundred years, the United States has degraded our river systems by hunting beavers, polluting, mining, diverting rivers and streams, and other things. We have also built over 92,000 dams. So all of the blue dots on this map are dams from the National Inventory of Dams. And most of these were built between the 1920 and 1970. So this is a massive, massive change of our landscape and our river systems. This is one example of a dam. This is Fremont Dam on the San Joaquin River in California. And it's just amazing what we've been able to do with water. A little bit frightening. Okay, so after that whirlwind, now we're going to talk about some of the current water challenges we have and how my research addresses these challenges. So our groundwater supplies are declining. So the New York Times did a neat analysis using USGS data and other data and found that 4 out of 10 groundwater monitoring sites, so all of the red dots here, hit their all-time low in the last decade. And a lot of this is due to groundwater pumping for agriculture. So a research project that I've been doing at the U.S. Geological Survey is modeling groundwater and surface water in the Quartz Valley, California. So this map shows where the Quartz Valley is. It's part of the Clement Basin, which recently had some dams removed. And this is the Quartz Valley, and the Quartz Valley Indian Reservation is in this valley. So this work supports efforts to improve groundwater levels. There's been severe groundwater decline in this area. There also have been really low stream flows during the summer, and often the streams will go dry in this area. And that has affected the salmon runs and made it so that the salmon are often unable to enter Quartz Valley. So we completed the Quartz Valley geologic framework that supports the groundwater model. And this is a photo of me at the, right about here where one stream from Quartz Valley enters Scott Valley. And it's a gorgeous area, but tragically the project funding for this has been cut. So after 3 summers working on this project, I was very disheartened when this work was defunded. We had already completed the geologic framework model that was used, that should be used for the groundwater and surface water model. Canceling this now is especially egregious because it primarily hurts the Quartz Valley Indian community. And that's particularly concerning to me given the US government's fraught history with tribal nations. So another challenge that we have, just get a sip. Another challenge that we have is managing our reservoirs under climate change. So with climate change, we're expecting to have more intense storms and less snowpack. And these more intense storms that come more as rain than as snow may lead to needing to use spillways more. We also may have less water stored in the reservoirs for the summertime when we need the water most. So you might be wondering, well, what do these reservoirs do? Why did we build so many of them? So reservoirs are operated for purposes that include flood control, so helping prevent large floods downstream because they can catch water in them. They're also used for water storage, and they're also used for hydropower. And historically, the decisions to release water or maintain water in these reservoirs have been based on past weather patterns. And here are two major reservoirs in California, Lake Oroville and New Bullards Bar. So, as you know from this live stream, weather forecasts have improved a lot over the past decades. So this has allowed us to use weather forecasts in reservoir operations. And this has been done through a program called Forecast-Informed Reservoir Operations, or FIRO. And this program gives reservoir operators flexibility in their decisions to retain or release water. And this program was piloted on Lake Mendocino, which is in Northern California. And the first year that they officially ran this program, they got 20% additional water storage compared to what they would have had without this program. So weather forecasts can really help us manage our water. So more flexible water management can help support climate resilience, and we must fund weather and climate forecasting, research, and observations to make this possible. So thank you so much to all of the places that have funded me in the federal government. This includes NSF, the USGS, the U.S. Army Corps of Engineers, and thank you to the Weather and Climate Livestream organizers, hosts, presenters, and audience. It's been very special. So lastly, I'd like to share a piece that I wrote. It's called Our Power, Our Planet. Feel free to check it out.
Awesome. Thanks, Sarah. And really sorry to hear about the funding being cut on the USGS project.
Thanks.
We have a lot of questions about dams in the chat. Like a lot of questions about dams. Could you maybe go back to the map of all of the blue dots of the dams? That
Yep.
The entire
Pretty shocking map.
Yeah, this one.
Yep.
Okay, so we have a few questions. I'll try to kind of combine a few.
Okay.
Some people specifically were asking why there are so many dams. Some people specifically pointed out Ohio, but you can kind of see the entire East Coast. So do you know if these dams are multi-purpose? Like, are they reservoir or, are they for hydropower? What's your general sense on what's going on over here?
Yeah, really good question. So many of these dams are relatively small. Not all of them are like the massive ones that I showed in that picture of Fremont Dam. But a lot of them are for many purposes. So the 5 main purposes that dams are built for are water supply, really big one, and then reducing flood risk. They can also be built to help with recreation. So a lot of people like to go out and fish or go boating on reservoir lakes. They can also help with environmental flows, sort of, but they definitely disrupt the rivers. And yeah, I think a lot of these are really old. So the average age is 64 years old. And generally it comes from us trying to control these rivers and make it so that we can build right next to them. We can use them for navigation. That's another really big one. And it's just been our effort to control water and be able to use it for everything we want. But we're starting to realize that this has backfired some. So we're starting to remove some dams. One other piece I'll say is that we hunted beavers almost to extinction, and they're starting to come back. But beavers used to provide natural dams, and so we've kind of built our own dams after the beavers have been.
And that's a great segue to Holly Chambers' question, which was, were beavers going to be part of your mitigation strategy up in the Klamath?
Yeah, good question. So actually, that would be one of the scenarios that we would test in our groundwater surface water model. And I've been up in the area, and they have been installing what are called beaver dam analogs, where they construct like a fake beaver dam that will kind of do the similar process of what a normal beaver dam would do, which is like holding back the water, allowing the water to percolate into the groundwater, trapping some sediment, just bringing the stream channel back to better health. And I think there are some natural beavers that are in that area now, but definitely less than there used to be. Good question.
Okay, another question. You touched on this a bit when we're talking about replenishing groundwater. Could you maybe just touch back on that and say, maybe, do you have an estimate of like rates or how it works and that type of thing?
How we can replenish groundwater?
Yeah, like
could we possibly gain groundwater back? I see. Yes, very good question. So we are trying to get our groundwater back. It's difficult because our groundwater supplies have taken a really, really long time to be where they are. So often hundreds, even thousands of years for water to percolate into the ground. And so it's not great that we are pumping this water out so quickly. However, there is hope. In California, I believe it was 2014, there was the Sustainable Groundwater Management Act. And so we're now required to manage our groundwater sustainably, meaning pumping up the same amount that can be kind of recharged. It's hard to enforce that, but there's a lot of work at the USGS and other places to help us get to a point where we can do that. And one of the main projects is something called managed aquifer recharge, which is essentially where you flood an area intentionally and allow that water to percolate into the ground. So there's a lot of really good work going into this.
And on the topic of the USGS, while you've mentioned it, Sarah has this really kind of interesting perspective, I think, from having spent her summers working for USGS and then kind of her school year as a PhD student. Could you maybe just talk about what you've learned from doing that together?
Sure. Yes, it's been a really unique opportunity. I joined the USGS because I really like the idea of doing public science. So the USGS, we're required to release everything we do to the public. So everything that the USGS does is online, available to everybody in the US and around the world. And it's been a unique experience to be able to experience the federal workforce and then learn at UCSD during the school year. However, it has been a bit difficult to balance at some points because I'm doing different projects at each spot. But I've learned from both of them a lot, and it's provided a unique perspective on water management in the US.
Awesome. Well, thanks for sharing, Sarah, and thanks for sharing your essay and giving us kind of a multi-billion year overview.
I hope you enjoyed the whirlwind.
Absolutely. Well,
thanks,
thanks, Sarah. So I've come up on the end of my 2-hour hosting slot. Have just switched over to hour 97. I'm going to pass over to Richard Rood, and thanks everyone for joining.
Thank you, and welcome to hour 97. Another thing that happens with dams is that in Michigan, they collapse when the precipitation increases. Thanks for joining us at the 97th hour of the Weather and Climate Livestream. There are only a few hours to go. I'm Ricky Rude, Professor Emeritus at the University of Michigan in Ann Arbor, and I also spent 20 years at NASA. I'm your host for this segment. We've seen many engaging and insightful talks since our start on Wednesday, and I'm looking forward to the crescendo of the next few hours. The feedback from the audience has been amazing. We've heard talks from students, early and mid-career professionals, and elders. First, I want to remind you that all of our speakers are appearing in their personal capacities and expressing their own views, which may not be those of other participants. However, we are all here for a purpose. Americans need excellent weather and climate forecasts. They are essential for success in a modern society. Budgets at the science agencies have been cut. The proposed budgets reduce spending by 50% or more on much of the federal research enterprise. Some weather and climate research is essentially eliminated. This endangers this country, states, individuals. It's dangerous for national security and living with our environment, which I call environmental security. If people want to change organizations, policies, and governments, there are some tried and true practices. One of these practices is to organize, which we're doing here. Another is to be present and to speak. Presence and speaking do not assure success, but absence and quiet assures failure. Another principle of practice is not to give up on your elected representatives. Support them, encourage them to speak, and to be present. We encourage you to call your representatives and governors. We need to maintain a presence and a constant vigilance of the importance of environmental predictions. There is information to help you to do this in the crawl at the bottom of the screen. Now I'd like to introduce our upcoming speaker, who's Timothy Merlis. He is currently at Princeton University. He studies climate dynamics, and my understanding that he is going to be talking about kilometer-scale modeling.
Thanks so much, Ricky. Can you hear me okay?
Yes.
All right, great. Let's get to it. Thanks for the introduction. Thanks for everyone for organizing. Thanks to those of you online watching. I'm going to talk about kilometer-scale global models of the atmosphere, and the science that I'm going to share is based on a recent journal article from last year called Climate Sensitivity and Relative Humidity Changes in Global Storm Resolving Model Simulations of Climate Change. It's a bit of a mouthful. I've shared all of my co-authors here on the bottom of the screen, color-coded by where we work. So I work at Princeton. The other folks in orange also work at Princeton. The folks in blue work at NOAA's Geophysical Fluid Dynamics Laboratory, which we've heard a lot about. A couple of people are in green, and they work for the Allen Institute for Artificial Intelligence. Now, one person breaks the color coding scheme. That's the second author, Kai-Yuan Cheng. I always had him in red. This is a reproduced slide from other seminars I've given at universities. And I always had him in red because of the heroic contributions that he made to this research, running these really ambitious frontier atmosphere model simulations. And now it's more poignant because Kai was a federal employee, a probationary federal employee who was fired from GFDL in February of 2025. So that sort of highlights, makes vivid in my professional life, the role that these cuts have already played on the weather and climate science that helps America. Because it's the first day of hurricane season, June 1st, I want to also thank the National Weather Service and National Hurricane Center. In my personal life, I benefited from their amazing observational and forecasting capabilities when Hurricane Sandy made landfall in New Jersey when I was a postdoc there about 13 years ago. So thanks to all those folks on the operational side. I'm more on the climate side of the weather climate research area. And so I'd like to start with just this basic schematic of a global atmospheric model. The procedure that we use to develop atmospheric models is to break the world up into little pieces, those gray squares, which we use to then implement the equations, the physical equations of Earth's atmosphere or Earth's ocean And we're encoding the basic conservation laws like the conservation of mass, conservation of energy, implementing those in computer codes and then running them on large computers. And how many little pieces do we break the world up into? This question of what resolution is feasible, it depends on how big your computer is. And so that's a sort of moving goalpost. We always want to do more and more realistic weather and climate simulations. To make that vivid for the non-scientists on the call, on the live stream, I want to share an illustration that's from a website making the analogy to TV screens. So this picture is a sort of downscaled image to DVD resolutions. DVD was a physical media technology that we used to watch movies in the mid to late 90s. And you can see here in this picture, maybe you can make out there's a car that's white, parked in front of a couple of buildings. And over time, we improved our TV screen resolution. Maybe 15 years ago, HD TVs became ubiquitous. And now this website is showing the same image, but at HD TV resolution. And now you can make out a lot more detail, like the hubcaps. You can see the fact that the red staircase is curving is clear now. And of course, as time has gone on, we're now in the world of 8K TVs. And so this final image here is showing the same photograph in 8K resolution. Now you can make out a lot more details. You can see the blue staircase has some faded paint. You can see the texture of the stone wall of the building, and you can even pick out the address of the apartment. I was attracted to this image in part because it really looks like Montreal to me, which is a city there that I lived for the better part of a decade. And using that address and Google Maps, I figured out exactly where this photograph was taken. 4028 Rue Saint-André in Le Plateau, Montreal. You can see the red staircase here in the street view, the blue staircase there. And the cars may be a little bit less exciting than the white convertible used for the image for the TV resolution website. So that increase in resolution, it opened up discovery. This is a sort of trivial example. It doesn't really matter that I could satisfy my curiosity of figuring out exactly where this photograph was taken in Montreal. But the same principle applies to simulating Earth's atmosphere. So we want to go to high resolution to open up discovery. And how high can we go? Where are we at and where are we going? The typical resolution for climate models, for atmospheric component of climate models, is 50 to 100 kilometers. That's 30 to 60 miles. So each of these gray boxes is something like 50 miles across. And on scales smaller than that, this inset image on the left is showing that there's certain important smaller scale processes that we must capture, but we can only do so in an approximate way because we're not explicitly simulating what happens. And as you know from looking outside, there are processes, for example, clouds that are smaller than 50 miles across. And it would be great if we could explicitly simulate more of those processes. So that's what we're doing in this initiative to go to kilometer scale global models of the atmosphere. So in context of conventional climate models, where we were at something like 50 to 100 kilometers, this is more than 20 times the horizontal resolution. And that's a bigger jump than from DVDs to 8K. And that process occurred over 30 years. And we're trying to do this for weather and climate modeling over 5 to 10 years. So this has been going on for about 5 years. And this image on the left is showing a sort of mock-up of what these simulations would look like if we were looking at them from space. And one of the images is showing an actual satellite image of Earth's atmosphere for the same day. And what you can see is some of the model simulations have relatively more or less clouds. You can pick out differences among these scenes. And the experts probably could do a decent job of ruling some out as not being the actual satellite image. The one in the middle is an actual image of Earth's atmosphere taken from space. Okay, so the model that I'm going to share the research results from is called X-Shield. It was developed at the Geophysical Fluid Dynamics Laboratory. It's a NOAA laboratory. And What we did is ran 2-year-long simulations and perturbed the climate to study the climate change of these high-resolution models. And that's in contrast to the previous initiatives where people only ran the simulations for 40 days. So these are much longer simulations and lets us investigate climate change style questions. Now, my not so high-minded philosophy coming into this research was, let's treat these kilometer scale models like conventional climate models and see if they behave similarly or differently. If they do behave similarly, that's good news. That's reassuring. That means people's attempts to approximately capture the small scale processes in conventional climate models is basically successful. And if they are different, then, well, that bears further attention and more scrutiny. So when we show these nice visualizations like this one here, I want to emphasize that the underlying simulation data is higher resolution than the number of pixels that you see here. We're sort of throwing out a bit of information to make the file size reasonable. And just before I logged in to present, I had to make my PDF smaller because even at that downgraded resolution, it was exceeding the streaming platform's capacities. So we're making trade-offs sometimes like that in the context of visualization, but the underlying small-scale simulation is important to the aggregate effect that we're interested in. Okay, science result number one, I'm going to show 2 results. First result is the climate sensitivity of this new class of model. How much global warming do you get when you double the carbon dioxide concentration? That's a simple change in carbon dioxide concentration that is designed to hold that fixed and let us look at the other aspects, the atmospheric response. And we know that anthropogenic activity is increasing the carbon dioxide concentration. So this is a very relevant probe of the aggregate climate response. So this is just a number in units of Kelvin or Celsius or Fahrenheit. And what I'm showing here is conventional climate models are shown in the circles, colored from blue, relatively little temperature increase, to red, relatively more. And that goes from about 2 to 3 Kelvin, which is the same as Celsius, something like 3 to 5 Fahrenheit of global warming. Now, the new storm resolving model is shown in the red star on the right. And you can see it's right in the middle of the pack here. So it's within the range of conventional climate models. And that's reassuring. Why is that happening? One of the key reasons why that's happening is because we have a similar change in the atmosphere's relative humidity in response to the warming. So here we're looking at a plot that's pressure in the vertical. You can think of that as height, with high altitudes at the top and the surface of the earth at the bottom, and latitude on the left-right axis. And the relative humidity change is plotted in red colors for decreases in relative humidity and blue colors for increases in relative humidity. You can see the new model on the left and conventional climate models on the right. Conventional climate models have behaved this way for at least 20 or so years, where there's that drying for some of the atmosphere, and then near the boundary, near where airplanes fly at the tropopause, formerly stratospheric air is humidifying. And you can see that this new class of model also behaves that way. So that's very reassuring, because we know that small scale storms that are now explicitly captured in the new generation of model, we know that that affects the atmospheric humidity, but it doesn't affect how that atmospheric humidity changes in response to warming. Next, second result, moving on to the radiative forcing. This is quantifying how much additional energy does the Earth trap, Earth's atmosphere, when carbon dioxide concentrations are increased. You can see the similar plot style where conventional climate models are in the circles on the left side of the plot, and a higher radiative forcing means that the similar change in CO2 concentration would lead to eventually more warming. And now we see this storm resolving model, the new frontier model, is actually above all of the conventional climate models. So all else equal, that would push towards more global warming. Now, why does our high-res model have a higher carbon dioxide forcing compared to conventional models? Digging under the hood, we found a couple of things. And one thing in particular that's new and exciting is high altitude clouds, these are cumulonimbus clouds that are being explicitly simulated, they're shifting upwards in response to increasing carbon dioxide concentration. So those high altitude clouds, they're also very good at trapping energy in Earth's atmosphere. And so if the carbon dioxide is moving those clouds up, and that's leading to them trapping more energy. And that's what we see in this left-hand side, which is another one of these height versus latitude plots. The blue is the change, the blue and red is the change in the cloud ice. And the gray line is showing where the unchanged clouds were sitting. So when we have the blue above the gray line in the high altitudes, and then the red below that, that means we're shifting the clouds upward. Okay, and so that's explicitly being simulated by this high resolution model. And that's an important line of further scrutiny. I want to say a bit about the larger context of what we're doing at Princeton, Geophysical Fluid Dynamics Laboratory, and the rest of the world. So I just shared the results of one journal article, and there's something like a dozen more by us, meaning people at Princeton and GFDL. And this model output has been used by 2 of the leading AI weather climate groups in the US. And this has been a very financially efficient line of research that draws on the deep expertise of US climate science, in particular climate modeling capabilities. And one metric that you might be interested in is, how many dollars per publication does this research cost? It's very resource intensive on the computing side, but the dollars per publication is in line with typical publications, even though we're working on this frontier. And because it's so resource intensive and it's only being done at a few places around the world, it's natural to ask, how do we make the most of this? How do we bring more people into this exciting research frontier? A couple weeks ago, we did just that by having coordinated hackathons around the world. There were 10 parallel workshops that were bringing new people into this research area and rapidly advancing the research frontier by simultaneously, for the first time, analyzing 6 such models that were run for long timescales to look at climate style questions. We hosted one at Princeton and GFDL. Myself, Lucas Harris, Robert Pincus, and Anna Valerio organized it. And our workshop sponsors, NOAA, provided a lot of the resources, both computational and personnel, and the US National Science Foundation provided participant support. Most of the people who came were early career scientists, either PhD students or postdoctoral fellows. And here's a picture, a midweek picture of our workshop participants. There's about 30 people shown here in front of the GFDL building. And we had a lot more on day 1, but there was a little bit of attrition, or people get distracted working so deeply, maybe they didn't make it out to the photo. So in the future, take the photo on day 1, not day 4. And our goals for this workshop were to analyze this frontier model by bringing in people with different expertise, different specialties. We went from about 20 people who had ever analyzed the output of this really high resolution model to 60 people, tripling the number of people who had ever looked at the output. And we're bringing in new people, new friends and collaborators to build up the capacities in this area. And in terms of the science, we were really doing the first time, world's first comparison across the 6 different models like this that exist throughout the world. Now, it's routine to compare conventional climate models. I was showing you those different colored dots, which amounted to about 12 different conventional climate models. But nobody until 2 weeks ago or 3 weeks ago had done this for kilometer scale models. So that's kind of a world first on the research side. And what did it look like? Here's a photo of the participants hacking away in the Geophysical Fluid Dynamics Laboratory. You might recognize some people from the live stream who were participants. And after 1 week, we assembled this results collage, which amounts to maybe 30% of what we did. And it covers a wide range of different weather climate phenomena, from what the winds look like, to what the temperature looks like, to what the clouds look like and how the clouds affect the flows of energy, and extreme weather events. This top left plot is showing a composite of a blocking event, a sort of stagnating flow in Earth's atmosphere, as well as tropical weather. This is showing a diagram of waves in the tropics, what they look like in this model. And one visualization, which I kind of like because it connects back to this issue of we're sort of not visualizing all the data, is my colleague Lucas Harris made a plot of the precipitation at the actual model resolution. So each pixel here corresponds to a pixel from the model output. And here we're seeing 1 day of precipitation in January. And now we can do the sort of spy show thing where we zoom in successive zoom levels. And here's the Western US. And I was kind of struck as somebody who grew up in California that on this simulated January day, California looks like it's not raining or snowing anywhere. And so then I zoomed in one more notch, and it's still hard to see at this zoom, but there are 3 individual locations with precipitation, and even those are multiple grid cells. So it's really hard to even wrap your head around the impressive resolution that we're using here. And in contrast to this simulated day in California, over the workshop, it was raining for most of the week. And that was a little bit of a downer, but nevertheless, we persisted. Here's us out at a pub with a full rainbow, and there's maybe even a hint of a double rainbow. So that's on the making friends and having fun side of things. And I just want to close with a sort of larger arc. I'm really trying to bring you up to speed on the current events of, what we're doing at GFDL in Princeton and how exciting it is. But that comes from this long lineage. We've heard several people talk about the 2021 Nobel Prize in Physics from Suki Manabe, who earned that for doing this really groundbreaking work about climate sensitivity, the same question I was interrogating. And a couple of years ago, he came and gave a discussion at GFDL, and somebody asked him in particular what he made of this new initiative to go to kilometer scale horizontal resolutions. And at that point, he was probably 91 or 92 years old, and he took in the question, and his response was, don't make the model more complicated, just increase the resolution, and I think you'll have great fun. So we've been trying to carry that spirit forward, and I think this live stream has been a really wonderful example of the fun and positivity of sharing our research and making clear to people what might be lost if there's dramatic cuts. So thank you to the live stream audience and to organizers. I know it was a lot of work to set this all up, and I'm really delighted to get to participate.
Thank you, Tim. Your mention of that by Manabe in the 70s and 80s, GFDL did a model called Sky High. I think it was 1 degree resolution, and they managed to run it for 7 months. And then in one of the things that I think is reflective of the GFDL culture, spent several years analyzing and trying to understand the science and the numerics of that model. And so these sort of forays into high resolution and then really studying what they're doing, I think is one of the essential purposes of the big labs that have the capacity to do things like this. They're not something that can just be done everywhere.
Absolutely. That's why we wanted to bring in the students and postdocs from other places to try and help move along the sort of training dimension.
And that's an amazing way to do what I do, what I call scaling across human mind, gray matter, rather than just thinking about silicon and more computing. Mm-hmm. I'll move now to a couple of questions in the in the chat. So the first one is from Sage, which I think a number of people might be interested in. What got you into this research?
Yeah, great question. I mentioned I used to work, I used to live in Montreal, and I was working at McGill University. And then about 3 years ago, I moved to Princeton and started collaborating with the folks at GFDL. And it became clear that people weren't yet looking at the long time scales in these really high resolution models. So that's kind of the narrow term what got me into this particular research that I was sharing here, is that there was this kind of hole where people were looking at the weather timescale, and we thought we could look at the climate timescale. And then overall, going way back to roughly 20 years ago, I was an undergrad in applied math, and I was in a department with a couple of atmospheric science professors. And so I was really kind of excited by the idea that I could use the mathematical training I had picked up as an undergrad to do something that had relevance to humans, look at the climate science area where there's clear contributions. People who know about applied math, computer programming, physics can make big contributions, and it matters to humanity. It's not sort of so abstract. It's a more tangible area of science.
Thank you. Then there are a couple of quite specific questions. I'll start the first one from Stu Weiss. How does X-Shield simulate marine stratocumulus clouds, especially subtropical?
Yeah, okay. So this is I very briefly touched on this image from a paper from 5 years ago where there's this kind of mock-up of what a geostationary satellite would see. And some of these models are too white, meaning they have too many of these marine stratocumulus clouds, and some of them are too blue, meaning they have too few of those low altitude clouds. And so that's a big area of ongoing research, how to formulate these new models to adequately capture those low clouds, because those low clouds are themselves dependent on even smaller scale processes. So if you're an expert, there is a shallow convection scheme that's being used in this particular model. Other modeling groups make different choices concerning shallow convection, which affects the low cloud simulation.
Okay, and then the final question by Mondo C42, if my eyes work. Can you run the model in the past with past conditions and compare the model results to see how well it's performing?
Yeah, absolutely. That's a very routine part of the evaluation of these new models and really any new models of the atmosphere. So in this case, they were started from the exact weather condition, or the best to the best of our knowledge, and then run forward. But in other cases, we do more aggregate style assessments. So one of these results from the hackathon, which is due to Claire Singer, another GFDL federal civil servant who was fired in February. This bottom plot is comparing to a satellite measurement of the energy flows. And so it's a difference between the model and the satellite observations. And so those are very important evaluations to make sure everything is in line with what we know from observations.
So when you do that particular experiment, are you thinking a little of do you look to see if it does the first El Nino correctly or anything?
Yeah, so these simulations use the observed sea surface temperature as the input. And so we're not at least yet doing coupled models. There are experimental prototypes of trying to take these atmospheres, couple them to interactive oceans, and then you could get that air-sea exchange that's so critical to the El Nino phenomenon.
Okay.
Yeah.
Thank you. And it's time for us to move to the next speaker. So thanks for joining us in hour 96 of the Weather and Climate, Hour 97 of the Weather and Climate live stream. There are only about 3 hours to go. I'm Ricky Rude, Professor Emeritus at the University of Michigan in Ann Arbor, and I also spent 20 years at NASA, and I'm your host for this segment. We've seen many engaging and insightful talks since our start on Wednesday, and I'm looking forward to the crescendo of the next few hours. The feedback from the audience has been amazing. We've heard talks from students, early and mid-career professionals, and elders. First, all of our speakers are appearing on their personal capacity or in their personal capacity and expressing their own views, which may not be those of other participants. However, we are all here with a purpose. Americans need excellent climate and weather forecasts. They are an essential part for success in a modern society. Budgets at the science agencies have been cut. The proposed budgets reduce spending by 50% or more on much of the federal research enterprise. Some climate and weather research is essentially eliminated. This endangers the country, states, and individuals. It is dangerous for national security in living with our environment. If people want to change organizations, policies, and governments, there are some tried and true practices. One of these practices is to organize. Another is to be present and to speak. That's what's happening in this live stream. Presence and speaking do not assure success, but absence and quiet assures failure. Another principle of practice is to not give up on your elected representatives. Support them, encourage them to speak and to be present. We encourage you all to call your representatives and governors. We need to maintain a presence and a constant vigilance of the importance of environmental predictions. There is information to help you to do this in the link in the crawl at the bottom of the screen. We'll now introduce our next speaker, who is Jeff Lazo. He's an independent consulting focused on communication use and the value of weather information. And what it says on my spreadsheet is talk with Jeff Lazo. So I'm assuming you're going to talk, but maybe you and I will introduce ourselves in chat. So.
Yeah. Can you hear me okay?
Yes, I hear you well.
Thank you. Yeah, so thank you. I want to make sure I thank the organizers of this event. It's great to be part of it. I'm probably, as they say in Monty Python, now for something completely different. Haven't watched all the presentations over the last 97 hours, but they've been great. And I'm not sure how many have been social science, but that's basically what I'm talking about here. I'm Jeff Lazo. I'm a semi-retired economist who's done work for several years, largely on the value communication of weather information. I'm going to talk about that and focus a little bit on a particular study that's available now as we go through this. So the takeaway, I'm going to start off with the forecast warnings based on NOAA, National Weather Service. This is the results of a recent study, are used by the US public over 317 billion times a year and worth over $112 billion a year to the US public. So those are some numbers that should get the attention of our congressmen. But much of the public information is a public good, and that should be provided by government and is not and should not be provided by the public sector. And as we go through this, I'll try to talk a little bit about the difference between public goods and private goods and why it's so important to have a public weather service providing this information. Quick outline of my talk. I'm going to talk about why consider economic value, weather and climate information, especially on this talkathon, trying to encourage keeping forecasts and discourage cutting budgets. Going to talk about the concept of the weather information value chain, touch on the economic impact of weather, value of weather information, then talk about the study a little bit more that I just cited some of the results from. So why consider the economic value of weather and climate information? I'm going to focus mainly on weather information, but the distinction's becoming more and more blurred over time. Well, if you look at the National Weather Service, their homepage, the mission vision statement, their mission states that their activities are for the protection of life and property and the enhancement of the national economy. So in order to measure the success of the National Weather Service, we should be measuring protection of life and property and the enhancement of the economy. I would say protection of life and property is very much a public good that should not be and cannot be done by the private sector if somebody wants to privatize the Weather Service. And the enhancement of the economy is also largely a public good, even though some of that could be privatized. So what argument best supports the weather enterprise? First mentioned that damages and impacts do not indicate the value of the weather enterprise. The enterprise creates and disseminates information, and therefore we need to demonstrate the value of information. And that's what I've been doing largely for the last 20 years maybe. A critical related question that I've kind of mentioned here is, can this information be provided by the public or by the private weather sector, or is it best provided by a public weather service? I'm going to mention very quickly the concept of the weather information value chain. A lot of the talks have been about the upstream part, the creation, observations, modeling, forecasting, going into the weather value chain. We have a white paper at the Amidst policy program discussing this concept. Basically, the value chain is trying to articulate and characterize the entire process with the creation, communication, transmission, and use of weather climate information. The value of weather information comes at the end. The economic, social, economic benefits come when the users use that for making decisions. That's where my focus has been, but understanding or characterizing the value chain is critical to getting valid estimates of the economic benefit and also to actually understanding what's being done with the information. And I would say that if someone's doing some type of climate weather modeling, if they don't know what it's being used for, it's going to be very hard to demonstrate any socioeconomic benefit. Briefly, going to touch on what the economic or the concept of economic impact of weather, a very widely cited paper by John Dutton back in 2002. His conclusion was that 1/3 of the US economy is sensitive to weather. That has been widely cited over 20 years. I think we're getting away from that. Basically, has no subjective, it's purely a subjective estimate. Really shouldn't be relied on in terms of validity and reliability. Another area where damages and impacts billion-dollar weather disasters. Roger Pilkey has kind of criticized that effort largely by NOAA. The billion-dollar weather disasters. For some reason, I guess my camera's not working.
Do I have a tech support person who can help? He's moving his slides, but at least I can't hear him or see him anymore.
Can you hear me now?
Yes, you're back. Your slides advanced a little bit after we could no longer hear you. You were on the billion-dollar disasters.
Yeah, I think I was just saying back there that $1 billion is not the best way to justify the enterprise. There's other studies that have looked at the variability of weather and climate. Let's kind of skip ahead here. Really, the best way to justify the enterprise is to talk about the value of the information. I think I'm probably having some bandwidth problems up here in the mountains, so try to keep an eye on that. Just some examples of the type of work that can be done in economics to look at the value of the enterprise. And I'm not the only person doing this, but I'm just going to cite my own work because I know that best. But one study looked at the value of buying a supercomputer, capital investment to use for research. $15 million computer generated at least $116 million in benefits just in certain limited number of sectors. The DOE solar work we did at NCAR, the value of value of research to improve forecasting, that showed a benefit. I'm not going to kind of skip through this. Aggregated up to almost $500 million, and that's just the value of the research to improve the weather forecasting for solar energy utilities. Again, a different approach. Benefits of observing systems. We did some work for NOAA on the GOES-R satellite, and there's been work going on now, I think, on GeoXO. But basically just looked at all the different sectors kind of back of the envelope and showed that benefits were probably significantly larger than the cost of that. So again, a different type of question can be answered. Looked at the benefits of forecast warnings, in this case, hurricanes, with a marginal improvement in accuracy of hurricane forecasts. And it came up with about $13 per household. With 60 million households subject to hurricanes, that adds up to a pretty significant amount, considerably more than the cost of improving those forecasts. So now I'm going to switch to talk about the 2022 study, which was a follow-up to a 2006 study. So a survey of the general public, asking their sources, uses, perceptions, and values for current weather information. Going to focus on the results from the 2022 survey, 1,200 respondents. Can't go through all the details. This is detailed in the report, which is at the AMS policy site. Reached a better sample back in the 2022 than we did in 2006. Again, all the details are in the report. Economists are well known for crunching data. We torture the data till it confesses. So I've been doing that for about the last 3 years. That's what I'll talk about some of the results here. The study was designed to look at the public's sources, perceptions, uses, and values. I'll mainly focus on results on one aspect of sources and then get to talking about the values. First question in the survey asked, do you use weather forecasts? Back in 2006, 3.6% said no. In 2022, 9% said no. That's a significant change. We don't understand why, and that's something that really could use some more research and see if it held up in the general public. That would represent a significant change in behavior with respect to use of forecasts. For purposes of the report, it kind of settled on this report about 5% saying didn't use forecasts. And that number comes in later when I aggregate up values later. So looking at sources, we asked people how often they get them from various sources, TV, radio, websites. The blue columns are the 2006 results, the orange 2022. And what this shows was a understandable and significant shift towards kind of more social media, electronic, web-based devices over that time period. So that all made sense. But what we did with this then is aggregated that up to the average household, say in 2022 using forecast about 118 times a month, then aggregated that up over the entire US population, adjusting for the number who don't use forecast, and came up with this estimate of the US public accessing forecasts about 317 billion times a year. So that's probably a conservative estimate given the way the question was asked. So I'm going to skip a lot of the work on the perceptions and uses of forecasts. A lot of that is in the report, and focus on the valuation question. There was a question in the survey, and this is kind of touch on this, basically saying, you know, the Weather Service provides all the information through taxes. Suppose you were told that X amount was used in taxes towards this, and then different people saw different values between $2 and $508, and then just ask, is it worth it to you? Yes, no, more or less. This is a standard approach in non-market valuation from economics called the contingent valuation method. It's kind of similar to a referendum, a vote on it. It's kind of best practices now to use referendums, but there are significant limitations to the actual implementation of this in this study, which hopefully I can correct or mitigate in a future study or follow-up study. But just a lot of caveats with this, and this is going through peer review, and it's been criticized for some of these shortcomings in the implementation. But I think it's still worth looking at the results. So again, we inserted different values, yes, no, is it worth it to you? People only saw one question, each respondent saw one question with $1 value. Responses in terms of percent said yes to the different values. Over 80% said yes, all the way up and above $500. Given that the actual cost to the average taxpayer is something less than maybe around $5, this does suggest significant public value for forecast information. What we did with this then is did a regression on the yes/no responses, where one of the independent variables, or the independent variables is the cost that was offered them. The regression results in detail, you can't read any of those, don't worry about it. Looked at a lot of different things that could affect that yes/no response. The two I'll mention in particular, as the cost we offered them, as that price we put in went up, their likelihood of saying yes went down. We would expect that from economic theory, that the more a commodity costs, the less people demand of it. The other, at least theoretically based or kind of economic theory based, is the higher people's income, the more likely they were to say yes to the offer. Again, this was for a normal good, that higher income means more of it is demanded. Using the data from the regression, we took the average respondents, so the average across the 1,200 people, which we were taking as, say, the average American member of the public, and fitted a demand curve. So the yes/no from $0 all the way up to a synthetically created data set. The area under this demand curve, you probably can't see my pointer, that represents what we call in economics the willingness to pay. That's the value to the individual for that commodity. So using this demand curve, then we calculated the area under that curve. The point estimate, $991, that's per household value for current weather information, calculated a 95% confidence interval, and just kind of rounded that off, given that there is a lot of uncertainty in this, a lot of variability. It's not to overstate the accuracy of this. Take about $990. What we did with that then was aggregated that up across all households in the U.S., accounting for population, household size, again, the percent who said they don't use forecast, and came up with a aggregate benefit to the U.S. public of current weather forecast of about $113 billion. So in summary, the survey basically, there's a lot of other stuff on sources, uses, perceptions. Most everything is generally consistent internally. Again, the $317 billion use is $991 per household, $113 billion aggregate. Again, that benefit estimate has some caveats with respect to the implementation method. There is a white paper, the policy program on the full study, and there's a BAMS article under review, re-review. I'm not optimistic that it's going to get hit again with some of the problems on the valuation estimate. I'm going to kind of take a few minutes to kind of wrap up on my perspective on this and the value forecast as a member of the public. And this is a book I've just finished reading on called Fire Weather by John Valen about the Fort McMurray fires up in Canada. But he says the willful and ongoing failure to act on climate science is unforgivable. Recrimination is justified, but none will be sufficient. In this case, at the planetary level, there is no justice. The punishment will be shared by all, but most severely by the young, the innocent, and the as yet unborn. So that's mainly talking about climate But what does that have to do with weather and with me? Well, why does the Weather Service matter to me? I live about 100 yards from the confluence of two rivers or two creeks. So we get potential flooding every year. So knowing what the weather or what the flooding potential is important. I live in the WUI. I live at the wildland urban interface. There's plenty of trees right out my window. My former house down in Louisville burnt down a couple years ago. Back there, they said it couldn't happen. And here, my neighbors say it couldn't happen. With climate change and increase in wildfires, I am very concerned about that. Gunnison County, a lot of cattle ranching, a lot of hay operations, very vulnerable to drought, also vulnerable to excess rainfall. So it impacts the economy of the people I live and work with. And also there's two ski areas within 30 miles, one in the county, one just outside. So we're highly dependent on snow, as well as forecasting for avalanches. We lose, unfortunately, a couple people every year in forecasting, and the avalanche forecasting is critical. And that's not to mention just every single day going out, whether I'm riding my bike or mowing the lawn, needing to know that forecast. And again, the blur, the distinction between weather and climate with climate change, more wildfires, more flooding, it's impacting us more so. So again, the takeaway, 317 billion forecast at least used by the US public. So every single member, almost every single member uses it, worth $112 billion. That's information that your congressman should be conscious of when they're cutting budgets. Much of the information is a public good. It can't and shouldn't be provided by the private sector, and that's the function of government, is to provide public goods. And with that, I'll say thank you and take any questions.
Okay, thank you. And sorry, I think I put an L in your name when I introduced you, and then suddenly you disappeared. Are you there?
Can you hear me?
Yes. Anyway, again, I apologize if I put an L in your name when I introduced you. So I have a question to get started. Back when I was in the government, there were a number of people who would do economic analysis of the value of weather forecasts or the value of a particular type of satellite instrument and its impact on forecasts. And sometimes when we went to present them to our overlords, one of the comments would be about who funded this economic study. Are these people, do they have a vested interest in the outcome of the study? So that seemed really to be quite a generic question. So I'm interested in how you think about that and how you potentially address it.
That's always an important question to ask. That's part of what peer review is supposed to do. Is any report and study should be peer reviewed by people outside the agency. The particular study I just mentioned here was funded by the AMS policy program. I forgot to mention it wasn't funded by the government. It was something I did as follow-up to work. I've been funded by quite a bit of the work came through. I ran the Societal Impacts program at NCAR for 13 years. It was funded by NOAA, but the standard was always to be independent and peer reviewable. I've done work for the National Weather Service, for the World Meteorological Organization, for the World Bank, looking at this issue, and always the objective is to have the correct, true, and valid estimate. I've seen poor estimates, highly questionable, but I feel trying to keep something peer reviewable is worth doing that. And yeah, there's potential bias on having the agency pay for the study.
Okay. And just as a quick curiosity, does the reinsurance industry ever pay for research like this? And if it does, is it open or is it proprietary?
As I understand it, most of their stuff is highly proprietary.
Okay.
in conferences and meetings I've had where they have been present, they are highly concerned about the value of information, highly concerned about, especially, changes in climate. But yeah, the private sector probably has much better information on the value and the impact and use of forecasts than the public sector does. If it affects their bottom line, they're going to study it.
Yeah. Some questions from the comments. First, the first one I'll do is from Meow Concha, which is Dr. Lazo. Lazo, what is the best way to keep this information in front of everyone's eyes?
So I think, yeah, any number of the studies I've done and others have done just go on the shelf and the box is checked. I think taking this information in a setting like this is great, but I think really where it needs to go is to reach out to interested parties, whether that be private sector, have them talk to their congressman. Having a cattleman in Gunnison County talk to our congressman is probably much more important than me doing a presentation on this. Every single agency, every single company, the airlines, energy companies, the tourism, agriculture, construction, all use weather information in day-to-day economic decisions. Some of that they can get from the private sector. Much of that comes from the public sector, but they need to advocate to their congressmen and to the government and get in their face and tell them, if you cut this forecast, I'm going to lose money, or my airplanes are going to be, not going to be quite as sure on the safety on airplanes and stuff.
So that's really an expansion of the number of voices that our representatives are hearing from constituents with direct impact to their locality. The next question from Monda C42, which I don't quite unparse, but that $990 US household cost, I'll say, what does that say to you about corporations to push for privatization of these sorts of services?
That's actually a very important question. So it's not, and again, the $990, that's the benefit to the households. That's what they get in terms of increased utility and happiness and use from economic perspective. The reason a number of private sector companies would like to privatize it is because they want to try to grab that benefit. They want to try to grab that consumer surplus and put a price on this. So there is some push for privatization, but a lot of that benefit comes from the public good aspect. You use it for safety. I don't think the private sector wants to be doing watches and warnings for tornadoes where people can die. For just general well-being, you get free information on an app that they put information out. So it may encourage corporations to go for privatizing, but the portion of the public goods aspect of this value is and should be provided by the public sector as any public good, whether you're talking clean air, clean water, national defense, education. There is a huge public portion, and that's the purpose of government, to provide public goods. One of the purposes.
Okay. Thank you. And I think it is time for us to move to the next speaker.
Okay. Thank you.
We're at the end, I think, of hour 97. I'm expecting to see 98 pop up pretty soon. So thank you for joining us at about hour 98 of the Weather and Climate live stream. There are only 2 hours to go. I'm Ricky Root, Professor Emeritus of the University of Michigan in Ann Arbor. I also spent 20 years at NASA, and I'm your host for this segment. We've seen many engaging and insightful talks since the start on Wednesday, and I'm looking forward to the crescendo of the next few hours. The feedback from the audience has been amazing. We have heard talks from students, early and mid-career professionals, and elders. First, all the speakers appearing are here in their personal capacities and expressing their own views, which may not be those of all the other participants. However, we're here for a single purpose. Americans need excellent weather and climate forecasts. They are essential for success in a modern society. Budgets at the science agencies have been cut. The proposed budgets reduce spending by 50% or more on much of the federal research enterprise. Some climate and weather research is essentially eliminated. This endangers the country, states, and individuals. It's dangerous for the national security and living with our environment. If people want to change organizations, policies, and governments, there are some tried and true practices. One of these practices is to organize, which is what we're doing here. Another is to be present and to speak. Presence and speaking do not assure success, but absence and quiet assures failure. Another principle of practice is not to give up on your elected representatives. Support them, encourage them to speak, for them to be present. We encourage you to call your representatives and governors. We need to maintain a presence and a constant vigilance of the importance of environmental predictions. There is information to help you do this in the link in the crawl at the bottom of the screen. And now I will introduce the next speaker, which is perhaps a moment of turning to face the strange. I'm waiting to see Ross show up. Hi, Ross.
Hi, Ricky.
So, Ross Salawitch, we've known each other for a long time. I knew him as a chemist, and he has done some of the most interesting work from my perspective in terms of modeling and climate sensitivity, and also has become an incredible photographer of birds. So I'll turn it over to you, Ross.
Thanks, Ricky. And just to reiterate, these are my views, not those of my employer or funding agency. And it's so great to be here with such a longtime friend and esteemed colleague, Ricky Rude. Thank you, Ricky. Okay, so first off, shout out to NASA. NASA has been a stalwart supporter of the research over my 4-decade career, more than that time, including this book that was published in 2017 that's available for free. That is the NASA ethos, free access to research. NASA is fantastic for that. So we've seen this slide before, the radiative forcing of climate from IPCC. I want to emphasize a few things here, hardly even describe it. Look, you all know this. We think we know what the radiative forcing due to greenhouse gases is pretty well. Aerosols are uncertain. I'll get into that. What I want to state here is that the information in this graphic relies so heavily on laboratory work for spectroscopy, radiative transfer models to calculate what happens in the atmosphere, funded in large part by entities such as NSF, NASA, NOAA, and let's not forget NIST as well. So what is this quantity? The quantity shown in that chart is the change in back radiation shown in this chart. Again, a chart shown many times. Let me add a couple of things. First off, this is the work led by Kevin Trenberth, a Kiwi who was at NCAR working on this. He's now retired back to New Zealand. This represents PhDs, hundreds, if not thousands. My colleague at University of Maryland, Emeritus Rachel Pinker, was very involved with this. Relies so heavily on NASA and NOAA satellites. Let's talk about NASA and NOAA satellites for a moment. Here is a chart showing the Earth fleet of NASA satellites, and this is the most up-to-date version of it. We've seen this chart many times, but I'm going to show you not the chart per se and talk about various instruments yet. I will come back to that. What I want to show you is some important information we've learned from this. So we've seen some changes, I'm not going to try to sing, that have been very strange, and I say strange because they weren't predicted, or they largely weren't predicted. What we've seen is cooling of the eastern tropical Pacific over time, long-term cooling. Now, this is sea surface temperature at the ground. The atmosphere is warming, the ocean is warming, but the tropical Pacific is turning into a more La Nina-like state. there are massive scientific arguments about whether this is a forced response to global warming. Some think it is, static stability, low-lying clouds, all that, or whether it's natural variability. We would love to know what it is. Okay, now, along with the cooling of the Pacific, this paper appeared in Nature, Climate, Atmospheric Science. This paper appeared in Journal of Climate. I had the pleasure of co-authoring with my friend and neighbor, Clark Weaver, shows increased low-level clouds in the tropical Eastern Pacific. So there's more albedo, more reflected sunlight. If this is actually a forced response to global warming, this means the cloud feedback might actually be neutral, because there's increases in high altitude clouds that many have talked about trap heat. So we're debating strenuously whether this is forced response or natural variability, and how do we do that? With satellite instruments. But on Friday, what dropped is news that the flagship of NASA, Terra, Aqua, and Aura, are penciled out in the FY 2006 budget moving forward. A lot of the information that we get about clouds comes from instruments on these Terra, Aqua, and Aura satellites. All right. I saw Liz Moyer talk yesterday. Liz was in hour 76, and Liz showed this chart, which basically we call this the all hell breaks loose chart. I encourage people to go back to the live stream, part 10. This is the QR code to get to the live streams. Part 10's not up yet. I hope there wasn't a problem. I hope it gets up. Liz gave a spectacular description of this chart. This chart comes from a paper I had the pleasure of leading. There's a QR code to get you to the paper in BAMS. The Eminent Data Desert, the Future of Stratospheric Modeling in a Rapidly Changing World. If you can't get the PDF file by going to the QR code, because it's behind the American Meteorological Society has not made it open access, just email me. I'll gladly send you the PDF file, provided you don't post it online. All right, when Liz talked yesterday, she said correctly that when we wrote this paper that she co-authored, we were talking about long-term sort of endemic issues with not supporting stratospheric research, the view that the stratosphere was a solved problem. Liz, of course, said in her talk, the stratosphere is not a solved problem. What Liz didn't say is that on Friday, we got news that SAGE 3, which we had projected would move forward, is also not in the FY 2006 budget. All right, so this is a chart that shows Aura and SAGE 3, the satellite instruments that measure the ozone layer that we talk about here. Now, the next chart is stunning. This chart is, and he has given me permission to show it and to name him. This chart comes courtesy of a friend and colleague, Richard Ekman. This chart shows the projection of what we're going to lose from NASA's amazing Earth fleet moving forward. So as Ricky said very, very eloquently, please write to elected officials and let them know the importance of this work. Okay, let's move forward to why I'm here to talk about Earth's climate system. This is a figure from our book showing on the top radiative forcing due to greenhouse gases for the RCP 4.5 scenario, and on the bottom, what many have talked about here, the fact that aerosols cool, yet we don't know how much they cool. This is going back in time and forward in time. The bottom panel comes from a paper written by Steve Smith and Tammy Bond. Now, we had a big surprise when AR6 came out. In AR5, the best estimate of aerosol radiative forcing was minus 0.9 cooling due to aerosols over the time period I've indicated. AR6 moved forward 8 years and put more cooling in. So they went to a different line on this curve. Now, what I want to do, our prior speaker has talked about looking under the hood. I want to look under the hood as well. Inside of these lines is a whole zoo of particles in the troposphere. Particles that warm, like black carbon. Look, I don't necessarily believe this biomass burning curve went all the way down and came back up, but this is what was inside the RCP 4.5 scenario that we talked about in our book. We have particles that cool, and we scientifically debate how much cooling we get from sulfate as a function of time, the shape of the sulfate, and we also vociferously debate how much warming we've had by black carbon. So this is a snapshot of, I think it's figure 34 of the Bonded-all tome on black carbon warming. Tammy calls this the Fahey plot, for those who know the great Dave Fahey, second author of the paper. On the bottom is the estimate of black carbon warming from IPCC as well as Bonded-all. And what we see is a disconnect between the Bonded-all world that's very data-driven. Now, in defense of IPCC, the data that drives Bonded-all is not throughout the whole world. And the IPCC estimate, which is largely model-driven, we can all say things about models. The part that I want to call out IPCC for is the smallness of their error bars, which I just think is, it's way overconfident that we actually know what black carbon warming is, in my opinion. All right, let's move back. So here's a figure that shows the time series of radiative forcing in red and global warming in black. And, we don't need equations or sophisticated statistics to show there's a relationship here, but wait until I show you the uncertainties. See, here are the uncertainties in radiative forcing, total radiative forcing as greenhouse gases and aerosols. And then we have the 25th and 75th percentile of the thick line, the best value in the middle. And then I think the upper and lower lines are the extremes. They might be the 5th and 95th percentile. So we have to do forecasts of global warming in light of the fact that we don't know how much warming has, how much of the warming due to greenhouse gases has in net been offset by aerosols. We don't know that term. And underlying that is a lot of uncertainty in black carbon. Okay, so what do we do? Okay, now I'm going to segue into the second part of my talk. I know I'm talking fast, but I also know this is being recorded, and I also know I want to save time for a conversation. All right, we've seen this chart before as well. We call this the violin plot. What's the violin plot? The violin plot shows estimates of feedback in the climate system using these funky units that I'm not going to have time to explain. I want to say something that's really not appreciated. What is appreciated, and Isaac Held talked about it. Oh, it's hard to even remember when Isaac talked. He was getting a lot of fan support in the chat. Isaac talked about the Clausius-Clapeyron, and the warmer atmosphere holds more water. We know the water vapor feedback is positive. The lapse rate feedback tends to counteract the water vapor feedback. It tends to be negative. Lapse rate refers to how temperature changes as a function of altitude. And what's been in all of the IPCC reports is we actually know the combined water vapor and lapse rate feedback quite well. So the range of the violins here is very small. And in totality, without going through the math, water vapor and lapse rate together amplify global warming due to greenhouse gases by about 45%. The other thing I want to point out about this chart is the cloud radiative feedback is not well known, and anyone listening to me knows that. Okay, so what do we do at University of Maryland? We have a model that we run that looks at the climate system over many, many years. There was a great talk last night by Zeke Hausfather talking about how we get these observations of temperature, buckets over ships, and all that. We model it by looking at what humans have done to the climate system, let me go to the next slide, easier to look at. What humans have done to the climate system in orange, what's happened to the 11-year solar cycle, volcanoes that put aerosols in the stratosphere. Again, Zeke explained it very well. Changes in the El Nino Southern Oscillation, changes in the Atlantic Meridional overturning circulation. Very, very importantly, the transfer of heat to the ocean. We model all this and we try to deduce what the climate feedback is, but don't worry, I'm going to talk about uncertainty. Let me just show one thing. If we go back to the chart with the equations, we take humans out. I'll go back and forth. Obviously, humans are responsible for the global warming. You all know that. Okay, so where the rubber hits the road is difficulty in projections because those aerosols are going away. There was really great talk about aerosols going away throughout this great series. They're going away because they're really bad for humans to breathe. They cause public health concerns. So in this projection, what I'm assuming is the lower limit to how much, or the lower limit of the least likely amount that aerosols have offset global warming by IPCC minus 0.4, so not much offset. And we take aerosols away, we don't get much of a change because they weren't doing much. I can fit the climate record best by having the total feedback being 0.5, which I've written on the chart, which is about what the water vapor and lapse rate feedback is. I had said 0.45. So in totality, the clouds feedback has to be kind of zero. Maybe it's those low-lying clouds in the tropical Eastern Pacific are offsetting the high altitude clouds. The dang old problem is the IPCC says the best estimate is minus 0.9. Here, I need clouds to be moderately positive. And here I can fit the climate record pretty well as well, because over the historical period, greenhouse gases have been rising. The aerosol offset has been going up. In the future, the aerosol offset's going away because of public health. And I've shown at the end of this chart the projection out to end of century. Here we stay below the Paris upper limit of 2 degrees. Now this is assuming that all the greenhouse gases are, I'm sorry I didn't put this, oh there it is, SSP 3.4. So this is 3.4 watt per meter squared by greenhouse gases. So here we hit the Paris upper limit, and the real problem is I can fit the climate record fairly well by using the upper limit to what IPCC says the most likely range of aerosol cooling is. See here, if aerosols have cooled this much, I need large climate feedback to fit the climate record. And we assume, without knowing better, that whatever feedback we have will stay present going forward. Okay, let's wrap this up. So what we do in our model world is we fit the climate record for a wide range of possibilities of climate feedback on the x-axis and the offset of radiative forcing due to tropospheric aerosols in the magic year 2019 to tie into the latest IPCC Working Group 1 report known as AR6. And we run hundreds of thousands of simulations, but we only show in color the warming at the end of the century for those simulations where, as a physicist, I say I fit the climate record well, fitting temperature over the whole time period, the recent temperature, now recent is from 55 forward, and also the ocean heat content record. During Andy, his thesis defense, which was this week, he was asked a really neat question. Why should you believe reduced complexity climate models, or which ones should you believe? And he answered, only believe the ones that actually do ocean heat export. We have to do the oceans well. All right, so and here is the AR6. One of these lines is the AR6 aerosol radiative forcing curve, and we scale them up and down. We can argue about the shape. We scale them up and down to span a huge range of possibilities. And what we get out of these models is a curve we call the Patriots plot. All of our curves have names. We call it the Patriots plot because of the red, white, and blue color scale. What I'm showing here is a projection of how much we will warm the climate system moving forward in time using spanning the ensemble, but we weight the results from our model that can fit the climate record well by this Gaussian on the top here. And this is the AR6 best estimate of what aerosols have done to offset global warming. Notice for their most cooling curves, minus 1.5, whatever, we can't actually fit the climate record well. And we talk about that in the paper that you can see through the QR code. All right, so the colors on this plot indicate, the blue indicates we're going to warm at least this much, and the red is our upper limit to how much we'll warm if we follow the SSP 4.5 scenario, and I have CO2 in the upper right. What CO2 will do is a function of time moving forward. And in this world, we're going to the lines here on the middle curve, the gold lines that go across these dotted lines, they indicate when we reach the Paris 1.5 degree warming limit, which arguably we've already reached, and most importantly, the 2 degree limit. And the circle that's under the white area is our 50% probability. But we think the scientific value of what we're doing is we're doing probabilistic forecasts of global warming. Now I'm going to cycle through the other scenarios here. So this is 4.5 watt per meter squared warming at end of century using all the AR6 formulations, which is actually leading to a little bit more than 4.5 watt per meter squared radiative forcing that you can read about in this paper that Andy led. If we tone it down to 3.4 watt per meter squared radiative forcing, we have less warming. I'll go back and forth. And in our world, we do a probabilistic forecast of this. And I should add that this trapezoid here, this green trapezoid, comes from AR5, and it's their best estimate of what actually is going to happen going out into the future, given what their words, not mine, the hot model problem of the big climate models, which I will talk about soon. Here we go to 2.6, and this looks good. And if we could somehow get CO2 to bend over to the 1.9 scenario, we'd limit the worst of what's being forecast for climate. I should just put a shout out to the GCMs. Of course, they do so much more than we do in this simple reduced complexity climate model. Of course, there's so much societal relevance in the precipitation, the wet get wetter, dry get drier, so the floods and the droughts. What we're doing is running many more scenarios than you can do in a GCM, and just saying when certain thresholds in global mean surface temperature will be reached. To find out what will happen when those thresholds are reached, you must, of course, go to the big climate models. Okay, so here are probability distribution functions of how much warming we're going to get in the end of the century based on our highly constrained energy balance model that tries to deduce natural variability, and so solar volcanoes and the human influence, but then running out to the future using only the ensembles that can actually match the observed climate record. That's our results in red. The CMIP results are in the gray area. So here's the hot model problem, if you will. Lots been written and spoken about this. This chart here is end of century CO2, and the table is the actual probability that we can limit global warming to either 1.5 degrees, which arguably we've already even passed or we're coming right up against in 2023 and 2024. AR6 is our model. I should have labeled it EMGC, but it's EMGC for the AR6 radiative forcing. And the CMIP6 is the big models. And the takeaway from this work is that if we would like half a chance to limit global warming to 2 degrees C, emissions of CO2 must be reduced such that the atmospheric abundance approaches 450 ppm by end of century. A lot of stuff on the web about 350 ppm, the great Jim Hansen, of course. If we could get 350 ppm, that would be just so amazing. But the message from our work is 450, this is peaking and turning over, could keep us below 2 degrees. And of course, endemic in all this is that climate feedbacks are what we think they're going to be. We don't really know what they are. Which is why we need continued observations. All right, so shout out to Andy. He defended his PhD just a few days ago. He is the youngest looking person in this slide, and he put his favorite images above him in the photograph. Here I am doing the mock throw the cake at the candidate, which has never yet happened at University of Maryland. And my last slide is why we do this. I have the great privilege of mentoring Abby, Maddie, Andy, Layla, and I should say I don't mentor them all. These are the atmospheric science group, so I'm not the advisor of all these people. Let's start again. Abby, Maddie, Andy, Layla, Sam, Sarah, Tiberius, and Akanksha. I was mentored by great people. It is my great privilege to turn it around and mentor these folks. They are the next generation, and they are most severely affected by the budget cuts. And of course, we talk about that. Of course, we have consternation about that. Yet, we celebrate our PhDs. We're still hopeful. And I shall end with these words. Get out, write your Congress people, raise your voice, but also young people, please note from an old man, this too shall pass. That's what I've prepared, Ricky.
Thank you, Ross. So there are a bunch of questions, and I'm going, given where you closed, I'm going to go with the one from Sage first, which is, how did you get into this research? What was the interest and the role of mentors, perhaps?
Great. Okay, so I was actually researching this. I'm going to try to make this really quick. If you Google my name and BAMS, you'll see a real whole article on this. I was researching the ozone layer when it was really boring. I switched to the global carbon cycle. My PhD advisor got in mail, hard copy, a paper announcing the discovery of the ozone hole by Joe Farman. Snail mail. Maybe was accepted for Nature or submitted. And he called me in his office and said, hey, I want you to go back to the stratosphere. And I was making such progress on the carbon cycle. I didn't know. I said, can I think about it over the weekend? All my friends said, you got to do what your advisor says. So I switched gears, did the stratosphere. I think I wrote the first PhD dissertation on the Antarctic ozone hole. Defended 87, graduated 88. Susan Solomon, who's listening, was very instrumental in all of this. Back in those days, we competed. Now we work together. And also to answer the question, I majored in applied engineering physics at Cornell University, nuclear energy, nuclear physics, all this esoteric stuff. I had a postdoc. I had a co-op assignment in Boston, Massachusetts, with a guy named Gordon Dryden. Shout out to Gordon and Dottie, doing laser mapping of Earth. I wanted to turn whatever talents I had to study Earth from my engineering co-op assignment at Cornell at AFCO Everett Research Lab. More questions?
So I'm going to combine sort of three questions to drive the backstage people a little crazy, which is, which of the satellites are you most concerned about losing? With them being removed, is this a complete data blackout, or are there other data sources? And if there are any ways with regard to citizen science that data gaps can be, say, mitigated.
Okay, I'm going to answer the last part for citizen science. I'm going to go to this slide so you can read it. Citizen science, yes. Environmental Defense Fund, methane set. PI Steve Wofsy at Harvard. That is Fred Krupp, EDF. That is citizen science at its best in space doing methane, which I haven't talked about. Super important. Which am I most concerned about? That's such a loaded question. I'm very concerned about loss of observations for the stratosphere. I've cut my teeth on the stratosphere. It seems weird to me to not let Terra, Aqua, and Aura run to the end of their natural lifetimes. They actually passed a senior review at NASA last summer. How do I know that? Oh, with stellar colors, because I was one of the reviewers. Not so happy that they called us the senior reviewers, but it was, it is what it is. So I'm very concerned about loss of Aura before the end of its natural lifetime and the turn off of SAGE on ISS Spectacular. Look, how do I answer this question? I used to work at JPL. I was very involved with the development of OCO, which Launch 1 crashed in the ocean. Horrific night for us who were there at the launch. OCO 2 up in air. OCO 3 on the space station. Shout out to OCO. It tells us aspects of the global carbon cycle we can't know otherwise. Now, there are other satellites that try to do CO2 from space. I think OCO2 is the best. Maybe we can gap fill. Look, Ricky, I don't even know what it means when a satellite's not in the FY 2006 budget. Does that mean they're going to just collect the data and not process it? I hope.
Yeah, no.
Or does that mean they deorbit? So I hope what it means, if anything, is they just bring the data down and maybe let us catch up later. I will answer this question at the end by saying there are other satellites I haven't mentioned that are supremely important, but I am also going to end on a positive note. I'm really glad to see Tempo surviving. That's geostationary air quality. Kelly Chance, Zhang Liao at Harvard Smithsonian Astrophysics. Great to see that surviving. Great to see Dave Diner's Maya, if I'm pronouncing it right, aerosols going all the way down to the surface, public health. So there have, and Landsat, Landsat is supremely useful and is surviving. So not everything's being cut, and I'm sure I've omitted important satellites. Do we have any more time for any more questions?
No, I think it's time that we must move on since we're essentially in live TV.
Thank you, Ricky.
Yeah, thank you, Ross. And we, of course, do have the European instruments and Japanese instruments and other countries' instruments as well at this point. Okay, so I'm going to move to the last talk that I'm introducing here in hour 98. We are, as I understand the spreadsheet now, moving out of the schedule we've been following in terms of the half-hour talks to what looks to me like the first of keynote talks here headed towards the end of the meeting. I'm Ricky Rude, your host. We're in hour 98. I'm an emeritus professor at University of Michigan, and I also spent 20 years at NASA. We've seen many engaging and insightful talks since our start on Wednesday, and I'm looking forward to the crescendo of the next few hours. The feedback from the audience has been amazing. We've heard talks from students, early and mid-career professionals, and elders. All of our speakers are appearing in their personal capacities and expressing their own views, which may not be those of other participants. However, we are all here with a purpose. We need excellent weather and climate forecasts. They are essential for success in a modern society. Budgets at the science agencies have been cut. The proposed budgets reduce spending by 50% or more on much of the federal research enterprise. Some weather and climate research is essentially eliminated. This endangers the country, states, and individuals. It's dangerous for the national security in living with our environment. If people want to change organizations, policies, and governments, then there are some tried and true practices. One of these is to organize, which we're doing here. Another is to be present and to speak. Presence and speaking do not assure success, but absence and quiet assures failure. Another principle of practice is to not give up on your elected representatives. Support them. Encourage them to speak. Write to them. Encourage them to be present. We encourage you all to call your representatives and governors. We need to maintain a presence and a constant vigilance of the importance of environmental predictions. There's information to help you do this in the link in the crawl at the bottom of the screen. Another principle of motivating and managing change is continuity. That is, what is next? We have many events and great first meetings, but change and success require us to keep going. Success is all about the next meeting. Now I want to introduce the final speaker that I will be introducing and then handing over to Mark Alessi and the organizers as the host. I'm introducing Dr. Jhordanne Jones, who started at the University of the West Indies, where she studied general physics and got a master's in philosophy and applied physics at the University of West Indies, and then came to the United States, where she studied at Colorado State University, focusing on tropical meteorology and tropical cyclone prediction. She has been a winner of the Fulbright Foreign Student Scholarship to attend Colorado State. After that, she was a NOAA Global Change postdoctoral fellow at Purdue, and she will be joining the faculty at Penn State in the fall semester, I believe, in 2026, as assistant professor of climate solutions for vulnerable communities. So welcome, Dr. Jones.
Thank you so much. It's great to be a part of this endeavor, and I hope that you learn a lot from my presentation. So just jumping right into it, I'm looking at seasonal tropical cyclone predictions. And I hope by now everyone already knows that we're in for an above normal 2025 Atlantic hurricane season. So the NOAA seasonal outlook calls for an above normal, or more likely an above normal hurricane activity with 13 to 19 named storms, 6 to 10 hurricanes, and then 3 to 5 major hurricanes. And they're not the only one. Colorado State has also already released their early April extended forecast. They also call for an above normal hurricane season with 17 named storms. And if you look in parentheses, that is the 1991 to 2020 average or climatology that we use as a baseline. So it's named storms 17 versus 14 for climatology. And hurricanes, 9 hurricanes to be expected, 4 major hurricanes. So all around, there are actually quite a few people and for quite a few forecasters that are looking for above normal. So do ECMWF in Europe. If you look all the way over here, the green represents the forecast mean, while the climate mean represents, basically represents climatology. And essentially they're calling for something close to climatology, but this standard deviation allows for some room to move above that climatology. So still all around above normal to be expected. And if you're interested in actually comparing all of these predictions and seasonal outlooks, there is the seasonalhurricanepredictions.org website that was done in collaboration with Colorado State University that gives you all the seasonal outlooks from different government agencies, private entities, universities, and also provides an average prediction. But the main point here is that we do expect above normal. So why is that the case? The first thing that we need to consider are actually 2 key signals to look out for, particularly in sea surface temperatures. That's 1, Atlantic sea surface temperatures, therefore the state of the Atlantic Ocean versus the state of the Pacific Ocean. And note that this is usually used as our key indicators this early on in the hurricane season or even the year, since we're doing these forecasts, or most of us are doing these forecasts for early April, May, and June. So the first thing to look at is, number 1, the state of the Atlantic, and we are particularly warm at the moment. Note that we are actually not as warm as we were for 2023 and 2024, but we're still generally warm. And this is one of the key reasons why we are expecting above normal activity. Warm Atlantic Ocean essentially means favorable conditions for tropical cyclone development, lower vertical wind shear, and also warmer oceans, which means a lot of fuel for developing hurricanes. But since we are actually not as warm as we were for 2023, 2024, a lot of that SST so far has been trending towards climatology. And you can see that pretty clearly here. In orange is 2024, and I think you can guess that that gray line that's also around 2024 is 2023, essentially. And it's great to actually see, at least for the Caribbean region, that we are well below what we saw for the last 2 years. So here we are at May 30th, which was a couple days ago, and we are just about 0.6 degrees, 0.9 degrees above climatology, relative to like almost 1.5 degrees for 2024, and then almost 1 degree above climatology for 2023. So we see a warm Atlantic, and we understand at least that a warm Atlantic does coincide with above normal or some expected hurricane activity. But the next thing to look at is the Pacific and the state of the Pacific Ocean. So here we're seeing currently cool, neutral, and so now this is actually not a video of what is happening now, but it is a representation of what usually happens when there is a significant El Nino or La Nina event developing. So this was for 1997 to 1998 El Nino event, and you can see that buildup of really warm water along the equatorial Pacific. And usually with El Nino events, you have a suppression of tropical cyclone activity over the Atlantic, versus with a La Nina, you also have you tend to have the reverse. Cool equatorial Pacific results in basically the floodgates opening, essentially, and you have a lot of upward motion, which means that you get more convection and the right conditions for tropical cyclone development and intensification. So to the right is actually the NOAA CPCs, or Climate Prediction Center's ENSO forecasts issued in May 2025. And in gray, you're seeing this neutral. Essentially, there's neither too hot or too cold within the Pacific region. It's neutral. So essentially, there's minimal forcing from ENSO, at least, on Atlantic hurricane activity. In blue, you see the likelihood of a La Nina event occurring, and then in then in red, you have the likelihood of an El Nino event occurring. So the likelihood of El Niños happening is actually pretty low going into the rest of the year, versus maybe a potential for a La Nina, but not as much as this neutral state that we're observing now. But then again, you never know before what happens, and it is always important to have consistent observations that allow us to predict ahead of time what might happen. So here again is El Niños or El Niño Southern Oscillations impact on the North Atlantic. So essentially, when you have an El Nino, you do tend to have a suppression of it, especially when you have these broad region of vertical wind shear. And then you have the reverse. So therefore you have the same or similar broad expanse of vertical wind shear, but suppressed, leading to far more hurricanes over the North Atlantic. So as you just saw, those two indicators of tropical cyclone activity are in fact ocean parameters, ocean conditions. And the ocean is in fact a key source of predictive skill for tropical cyclone activity. I have this really cool image to the left here that I got from from a website. And essentially, it shows just exactly the extent to which you can predict any number of events, or particularly climate events, with ocean predictors. So in particular, for events approximately 30 days to years, you can in fact use ocean parameters to do that, and that is because of the energy and its capacity, its heat capacity. Essentially, oceans hold a lot of heat and they slowly vary over time. And that is how we can basically say that if there is this particular state of El Nino at this particular time or season, then we can definitely, well, maybe not definitely, but likely tell you what will happen in the next 2 months, 3 months, depending on the time of year. But for less than 30 days, then you tend to move to land parameters. And then even less than that, 7 days, is atmospheric parameters. To the right is the extensive coverage of Argo flows and observations for the ocean. Like I said, the ocean condition is actually really important, an important predictor and source of predictive skill for a wide variety of climate events and climate hazards, not just for tropical cyclones. And it should be noted here that these Argo floats, of the 3,881 that are operational, the USA managed through NOAA's Atlantic Oceanographic and Meteorological Laboratory manages 2,179 of those. those. And you see that a lot of them covers the Pacific region, which again is essential because we need to understand how El Nino, how La Nina, how ENSO itself varies over time, and well ahead of our peak seasons for hurricanes and for storms in general. You can also see that it covers the North Atlantic, the South Atlantic. There are even dots also in the Indian Ocean. There are also other seasonal drivers of tropical cyclone activity. This in particular is what my work as a Fulbrighter, as a PhD student was. It was about seeking out just exactly what gaps were in forecasting for seasonal hurricane activity. And one particular gap was with Rossby wave breaking. And in particular, if you're new to Rossby wave breaking, it's essentially this irreversible overturning of different temperatures and densities of air. So essentially to the far north, you get this dry, cold air, and then to the equator, you have this moister, warmer air. And it has a sort of invisible barrier. And every now and again, when those waves that you're seeing happening basically interact with a very strong gradient, they start to overturn and essentially mixing air further equatorward and then mixing warmer air northward. And what happens is that you end up with those mixing and those these tendrils that you're seeing here, these streamers that are breaking off and mixing further down into the tropics. You actually do get increases in vertical wind shear right over the North Atlantic, the tropical North Atlantic, as well as the main development region for tropical cyclones. And that is also not the only phenomenon that affects the main development region. You also have the Saharan air layer events. We had one very recently. I think it's still undergoing, but essentially what you're seeing here in orange is air, what do they call it? Is dusty air, essentially. And essentially it's moving along with the circulation across the North Atlantic, across the Caribbean, and even it can get as far as Mexico and as the US East Coast. So this also has an impact on the circulation as well, on conditions for tropical cyclone activity. It tends to be generally to suppress tropical cyclone activity, which is good in terms of tropical cyclone damage, but may also have impacts otherwise. So for example, in poor air quality. So to go a little bit more with Rossby wave breaking, this really cool work that was done by Philippe Patin and Gan Zhang, they essentially show just exactly what Rossby wave breaking actually does for the tropical North Atlantic. It essentially, again, enhances vertical wind shear along the tropical North Atlantic, also reduces precipitable water as well. So essentially, when you have these increases in Rossby wave breaking, you have far more suppression of tropical cyclone activity. And then if you have far less anticyclonic Rossby wave breaking, then you do tend to have an increase in tropical cyclone activity over the North Atlantic. My particular contribution to that was done with Fulbright, but also done along with an ONR grant, was to look at ways in which we could incorporate the environmental impacts of Rossby wave breaking into seasonal extended forecasts, which in this case ended up being the extended early April forecast for Colorado State University. So one of the things I did find with my research was that you can in fact represent Rossby wave breaking or shear or Rossby wave breaking associated shear as a time series, and that time series could actually be tracked back in time as well. So you could in fact see that with years in which you had enhanced Rossby wave breaking and therefore its impacts on shear or vertical wind shear, you could actually see a signal further ahead in time. So around January, February, March. So much earlier on in the year, that could give us an indication of what Rossby wave breaking actually does. And then if you couple that with ENSO and shear, which is a really big driver of tropical Atlantic circulation, then it becomes a really useful tool to improve early extended seasonal forecasts. So a lot of that research was done with reanalysis tools, particularly with sea surface temperatures. A lot of those images that you saw were from NOAA, were provided by NOAA, especially those observations. But I also have looked at ways to critique the seasonal tropical cyclone activity or the role of SSTs in tropical cyclone seasons by looking at global climate models. So to the left, you are seeing observations of sea surface temperatures for the August to October Atlantic hurricane season 2023. This was done in collaboration with Bill Klotzbach and many other collaborators. I'll show you their names soon. But essentially what we wanted to know was which sea surface temperatures within this particular map was actually driving the results or the hurricane season that we experienced in the North Atlantic. And if you might remember, it wasn't as impressive as we thought it would be, especially with all of this warming in the North Atlantic. But it was also this really prominent El Nino signal within the same season. And the question was which one was actually forcing the conditions over the North Atlantic. So what we did was to break down all of these sea surface temperatures by region and then put them into the model, run a global climate model based on these sea surface temperature patterns to see whether or not they gave us back this full view of the 2023 season. And in that way, we saw that the North Atlantic, for the most part, drove tropical cyclone activity and environmental conditions, but that was also mitigated to some extent by the El Nino. So it was an extraordinary year that we were able to assess properly with sea surface temperature and a global climate model. So this is the paper. Again, these are all of the fabulous co-authors that put that paper together, that provided critique for that paper. But I would also like to point out that this is also the list of data that we used to put that paper together. So it wasn't just about global climate models that used for the analysis, but there was also data provided from NOAA. So there's HERDAT2, which is the best track for the North Atlantic tropical cyclones. Here's ERSST5. Here's ENSO. Here's more ENSO. Here's the Pacific Decadal Oscillation. So many data sets that we used, and that is based on the observations collected and then stewarded by NOAA. So it's safe to say that observations really is essential to the academic enterprise and to seasonal forecasting of tropical cyclone activity. So to take a little turn from the seasonal forecasting side of it, now we have to conclude. Now we have to engage with the fact of climate change, right? And that we do have continuing increases in atmospheric CO2. But we also have this warming trend that is very prominent, particularly for the Caribbean region, for the Gulf of Mexico, and then for the eastern coast of the US. We have a background state that now we must consider with tropical cyclone prediction, seasonal predictions. And one set of things that I would would like you to consider under climate change is that we may, in fact, see more rapid intensification events. These are some topics that are, I think, more current that academics and forecasters alike are actively working on and thinking about. So rapid intensification events is essentially when a hurricane or storm rapidly intensifies within a 24-hour period. And here's this analysis by Manikanta et al. 2023 that shows that over time there has been an increase in RI events, right? So you have single RITCs and multiple RITCs, and for all of these categories, you do see at least some level of increase, particularly for multiple RI events. So that's definitely one thing to consider. We are also likely to see intense storms outside of the peak season. So we already know that August to October are usually where we see the warmest temperatures within the Atlantic. So you tend to see also the greatest activity for the North Atlantic and as well as the most intense storms. So you might have heard of, well, you might have experienced Helene in 2024, but there was also Sandy, Maria, and Irma in 2017, Joaquin in 2015, Gilbert in 1988, and many more storms that developed within this particular time frame within the season. But with 2024, we did see the first, at least one of the first, or at least one of the first, Category 5 storm outside of this August to October timeframe, Beryl in 2024, that went on to impact many within the Caribbean and then to cause some flooding events as remnants over the continental US. So that is one thing also to consider, that as you have this increased warming and increased warmer background state, you might find that the conditions for the most intense and the most active parts of the season start to spread out into earlier in the year and maybe later on in the year, depending on how persistent the condition is. And then finally, one thing that I do think is currently ongoing are our understanding of compounding events and how that might impact us as tropical cyclone prone areas. So for example, extreme heat and storms. This is a figure that I got from the Washington Post. The Caribbean is actually heating up very quickly. And that's not a good thing, which it really isn't. One, it does point to more intense storms, but it also points to more persistent heat extremes. And the question is whether or not we can forecast and consider what those impacts might be within the hurricane season, and how do stakeholders, how do people on the ground prepare for an overall impact from these two hazards. And the last thing that I do want to mention here is Michael Lowry's A Hurricane Season Like No Other opinion piece in the New York Times. So essentially, he does a great job of summing up why this hurricane season might be especially different from the rest, especially with the budget cuts that are happening now. One thing that I got from this particular opinion piece is essentially that there are multiple institutions, multiple agencies that are always involved with preparing, with forecasting during a hurricane season, and then as well as afterwards when it comes to monitoring remnants of storms, when it comes to dealing with damage and disasters on the ground level. There are always multiple agencies that are engaged in safeguarding lives. So even these seasonal forecasts, these seasonal outlooks is just one piece of a very large endeavor by everyone to safeguard lives on the ground. So from the people who collect data, hurricane hunters, dropsons, from the people who steward that data, provide us with the platforms in order to access that data, making it publicly available to academics who use that data to make sure that we understand what it is we're going through, what it is and how it is that we should forecast for these storms. And then again, afterwards, when maybe we make a mistake or we've not accounted for anything, we go back and review what needs to be done for the next year. And then after that, after all the damage is done, there are also the people, FEMA as well, that has to engage with people on the ground with the damages that are left behind from storms and from disasters. So these are all people, the cooperative institutes that provide us satellite data. These are all people that are incredibly important to safeguarding lives because again, it is not a one agency effort, it is a multiple of people that are working towards this. So I will stop there. Thank you so much.
Thank you. I still seem to be in the show, so I will start the discussion here. So one of the things that I wanted to point out is you wrote this very nice article in the conversation.
Yeah.
And I'll point out, one, it's a very nice article, and two, for people in our field who want a presence in a place that I think is a nice, credible place to write, the conversation is a great venue. So
I agree. It's also great, not just for tropical cyclone activity, but it is actually academics that are writing those pieces, and it is made to be publicly read. It's not for just academics.
Right, and it's academics working with journalists there.
Yeah.
And I think it's I've had a few articles there, and they have been quite influential. And also more and more people, institutions are looking to the conversation as one of the places that they see public outreach for promotions and things like that. So very nice. So let me move over to the chat as well. So again, the first question: how did you get into research, and a little bit about your path?
Sure. So I was introduced to tropical cyclones in Jamaica. I've been through a few, as you can imagine. I was in high school when Hurricane Ivan in 2004 hit, or maybe, I guess, passed by Jamaica at the time. So I was interested in hurricanes from then. And I got into climate studies while I was in Jamaica. I did my master's there. And I looked at hurricane frequencies, tropical cyclone frequency, and how that changes with climate change. So yeah, I was actually doing research in Jamaica before I got to Colorado State.
And there's sort of a related question, I think, that says you have a degree in philosophy as well, and they're interested in how they overlap or influence you.
No, unfortunately, let me clarify. I have a Master of Philosophy, which is sort of the European version of a Master's of Science.
Okay.
So it's not philosophy. I did maybe one philosophy course.
Okay, so it's the classical definition of philosophy as knowledge.
Yes.
So I'm there are a couple other questions which I'm going to get to since we have a moment or two. But one thing I wanted to follow up, you were essentially starting to talk about how the sea surface temperature is changing. It's non-stationary now, and that forecasting is potentially becoming harder. I think I also saw a paper on the sea surface patterns are now statistically significant in their change.
Right.
And I view this question of non-stationarity and how it challenges both the statistical models and even the physical models, because the physical models are calibrated, they're not from first principles. How do you think about that as somebody who's a new expert in this emerging field?
Yeah, that's a great question. And it's a difficult one as well. It is always helpful, I think, to simplify the questions that we have. So I have to admit that I actually don't have a good question about how we deal with non-stationarity in terms of trends. Usually what happens in climate science is that we tend to take the chunks, take different 30-year climate chunks, and look at just exactly how these background states or means actually change, and how that might impact the variability that's varying around it. I'm actually not sure how any other scientists actually deal with non-stationarity. But what happens in research also is that we tend to isolate the trend, the global mean trend, to look at different phenomena. So for example, ENSO in particular, a lot of our data, or rather a lot of our indices for ENSO tends to be standardized, tends to remove some of that global mean. So you can look directly at the changes of ENSO itself. Separately from the background state.
Yeah. So, and I think your answer is sort of also right on. We really don't know how to deal with non-stationarity at this point, and the emerging changes in the ocean are going to really challenge predictability, I think. So. I'm again going to sort of combine two questions that I'm seeing here, which is the one by both are by Sydney, actually. Would it hypothetically get to a point where you could start getting hurricanes anywhere in the ocean, any season? And sort of a follow-up that, do you think we're getting to the point that California could be seeing hurricanes perhaps more frequently than the incredible rarity they currently have?
Yeah. So to answer the first question, this is actually a really good question. So to answer the first question, at the moment, no, we can't just yet say that we get hurricanes anywhere where it's warm enough, because for one, sea surface temperatures are not the only thing that actually changes. There's also changes and warming within the upper levels of the atmosphere, right? And what that does is that it changes stability. So, for example, with the Caribbean region, while we tend to have very strong sea surface temperature trends upwards, we also tend to have warming above as well, which means actually at a slightly higher rate than we do for sea surface temperatures. So that means that in general and within the trend, you have stability that sort of puts a cap on hurricanes. Again, this varies from year to year, from season to season within climatologies, but essentially the Caribbean is drying out, really. I'm not exactly sure what that means for hurricanes just yet. It is very early analyses on that front. Also, there is a migration of warmer sea surface temperatures further north, which allows for at least more hurricanes to occur within the subtropics and to impact the eastern coast of the U.S. That way. But again, I think for the in more recent literature, we're just now considering just exactly what happens with upper tropospheric warming, and what that actually, and how that actually varies relative to trends along the surface. So at the moment, the trends in total tropical cyclone counts remain roughly the same. We see them roughly in the same places, which is nearer to, which is within the tropics itself. But what you might see is a slight expansion of the tropics.
Okay, and potentially a little expansion of the season as well.
Right.
So, yeah, I had a student not long ago looking at the midsummer drought in Puerto Rico area and things like that, and the importance of the Rossby wave train coming out of, essentially the maritime subcontinent. So it's not just sea surface temperature. There's the Rossby wave breaking, as you were talking about,
right.
and many other things that fit into this as well. Again, here there are a couple questions here, which I'm going to go with. Who is your preferred target audience? Do you put your results before policymakers to inform their decisions, or how do you think about that policy interface?
Mm-hmm. Wow. My preferred target audience, anyone who will listen, honestly. What I will say is that I, even though you already heard my presentation, I actually don't like speaking in jargon. I do find it enjoyable to talk to the audience about science, about this type of research. When I was at Colorado State, I did get to do quite a few interviews, not just with journalists, not just with media, with meteorologists, but also with just people who were, essentially just putting together a newsletter for their own communities, right? And I think that was interesting conversations about how they interpret science when they hear it. I have spoken with policymakers before, probably not for the US or the continental US. And yes, they are aware of my research, at least. Yeah, infrastructure and public safety spending, I am not particularly sure if they know about that. But I do know that they do quite a bit in terms of reaching out to NOAA, in terms of reaching out to scientists for interviews. I have gotten quite a few of those interviews before. So I know that they are pretty proactive when it comes to the hurricane season.
Okay, and one last question that I'm going to hand it off is a question we've seen a number of times, the favorite question. Do you see a way for citizen scientists to participate in this?
Yes, I do. So again, I think, again, at Colorado State University, I did see and hear a lot about COCORAS, which is, I think, citizen scientist led, where you essentially have weather stations that you maintain and that you take readings for. That does quite a bit in terms of collecting data across the continental US, especially when you have these events such as hurricane remnants that make their way all the way up the continental US along the eastern section of the US. So I think that data like that is actually really important. It's also incredibly important to have stewards for that data, to coagulate all of that data, to put it together, to make sure it's quality controlled. So yeah, you definitely have a role to play. You also have a role to play in communicating science whenever you learn about it, whenever you hear anything in terms of hazards that needs to be communicated quickly. So yeah, I think you do have a lot to do.
and your point about that quality control of data, data is just numbers until it's quality controlled. So
Yes.
I see in the backstage that Mark is here and ready to take over from me. Thank everybody, thank the speakers, and then I think we are ready to go.
Hello, everyone. Thanks so much for joining. We have currently 830 people on, which is very exciting. Definitely go out and ask your friends to join. We are in the final 2 hours of this live stream. I mean, this is incredible. It's so emotional to look up at the top of the screen and see the number 99. So we're within the 99th hour of this live stream. 98 hours and 16 minutes have gone by. What an incredible accomplishment, honestly. And like, you got to give it up to the other organizers. Like, they have been behind the scenes this whole time, doing everything, putting it together, and it has gone so smoothly, which is really an incredible accomplishment. But yes, thank you so much all for joining today. Of course, we're here for the Weather and Climate live stream. And we know how important weather and climate forecasts are to you and to everyone in this country, whether you're looking 5 days out from now or 100 years into the future, to know how climate change will affect your community. Of course, in the United States, we developed the first computerized weather and climate prediction systems. So we have a long history of taxpayer investment in weather and climate prediction. And that's why it is so important that we continue to fund NOAA, the NOAA Research Labs, the Cooperative Research Institutes, the National Weather Service, the National Hurricane Center. All of these agencies within NOAA, within our weather and climate prediction infrastructure, need to continue to be fully funded so that we can continue protecting American lives and livelihoods. And also just want to mention NOAA's unparalleled network of observations. After the next talk, we're going to talk more in depth about some of the cuts that we're looking at. We'll bring Stella on for that, another host. And of course, as I mentioned, this miracle was made possible in weather and climate prediction by investment of the American public. And as we know, in the proposed budget being considered now by Congress, who of course controls how much funding will go to each agency, they could cut some of NSF, the National Science Foundation, and they could cut more of NOAA and its research. So we gotta put pressure on them to be sure that doesn't happen. You can go to this link right here, wclivestream.com/act. And write to your representatives. But remember, this is a nonpartisan live stream, right? It is just an opportunity for us scientists to get out there and show you what we're doing behind the scenes, how we're passionate about knowing what's going on in the atmosphere, but also passionate about protecting American lives, no matter your background, right? We're always out there trying to forecast to make sure everything goes okay. All right, so yes, we just crossed hour 100. What an incredible accomplishment. That's so crazy. It's awesome. And actually, we're going to go ahead and actually bring on Stella right now because we're going to, hello, Stella. I was thinking we should try to like high five like this way.
Wait, but I'm on the other side. Like,
yeah. Okay, go ahead. Yep. Nice.
Okay.
I hope someone screencasts that. Okay, yeah, so we are really glad to be here today. And you know, as Dr. Shepard was talking about, we really need to start engaging with the public community, and that's kind of what we're doing. You know, all these cuts are really damaging our ability to forecast and predict how we'll be affected by climate change, and that's why we're here to show the American public, you know, these agencies, National Weather Service, National Hurricane Center, NOAA, need to remain fully funded so that we can continue doing so. And so right now, we're going to take, so normally, as you guys have seen, you all are, you know, seasoned watchers at this point, we normally do a quick 3 to 5 minute mission statement about, you know, why we're here. And we're going to change that up a little bit now since we just crossed hour 100. And what we're going to do is we're going to kind of walk through the cuts, and we're gonna talk about, you know, what has already happened, what are the proposed cuts in the future that could really dismantle NOAA even further. And in response to seeing those cuts, we really want you to reach out to your representatives, start talking to people, And the link, yes, is right at the bottom, wclivestream.com/act. So, all right, so we're gonna go ahead and, well, we're actually gonna show some slides too, just to show what cuts have already occurred. So yes, okay, so first slide, these are the cuts that have already happened as of today. Let me switch over to the screen. So first of all, we've already lost technical support for the next IPCC report. IPCC stands for Intergovernmental Panel on Climate Change. They do a report every 5 or so years. This is from all countries around the world that come together and try to decide, okay, how is climate change affecting us? A lot of countries have their own climate modeling centers. They pool all of that data together. And the US, of course, is a very important piece of that climate report and that climate gathering of data, and it contributes a ton of model data. But the US has just ended technical support for that. So we're going to be flying blind into climate change if we don't have an idea for how it could look over the next few decades.
Yeah, absolutely. And we have also seen this cancellation of the $4 million NOAA cooperative agreement with Princeton, SIMS, the Cooperative Institute for Modeling the Earth System. This is a really important program for Earth system modeling, as the name suggests. It's also where I did an internship in undergrad, as well as many of my friends that I know in grad school across the country got their start in this field. And it was canceled for, quote, promoting exaggerated and implausible climate threats and climate anxiety. But I would argue that getting to engage with research in undergrad at such a world-class institution was actually just antithetical to climate anxiety for me. It helped me feel confident and like I could really do something that helped make this world a better place.
Exactly. We also just saw the canceling of the 6th National Climate Assessment. So this is an assessment that's congressionally mandated since the 1980s. And it's basically an opportunity for a bunch of climate scientists, social scientists to come together and see how climate change is kind of starting to impact the American economy, American livelihoods. And the administration just came out and basically dismissed all of those authors and canceled that assessment that we need, everyone in the United States needs to know how to respond to climate change.
Yeah, and then as you guys saw, if you've been watching since hour 1 of our 100-hour live stream, we started on May 28th when NASA GIST, the Goddard Institute for Space Studies, was evicted from their office building on the Columbia University campus, where they had been since 1966. And so, yeah, like Sil and Andrew did a really great job covering as some of our organizers were asked to leave the room where they were streaming. And right now, NASA GIST scientists are operating from home and have no workplace to meet and do collaborative science.
Yeah, I just want to follow up on Stella there. Like, we got to give it up for Andrew and Sil, if you guys were there on the first day. And Miriam behind the scenes was the one organizing all the talks, dealing with the fact that they had to move to a different room and still continue this live stream. That was truly exceptional work there. And of course, we've lost already some data sets from NOAA's National Center for Environmental Information, some data sets that are very critical for us to analyze climate change. And the most incredible part of this is that the American public owns these data sets, right? American dollars, your taxpayer money, is going to fund these data sets, and they have just taken it away and saying we can't really use it anymore. So that's another effect of these cuts.
Yeah, and then NOAA probationary employees. You guys might have seen probationary employees across the federal government. We were calling them out at NOAA specifically here because of the impacts on the National Weather Service that we've seen. And just want to highlight probationary employees doesn't necessarily mean people that just started, although many of my friends, so people that just graduated grad school, did see cuts. I know many people that were fired. But in addition to that, also probationary employees covers people that just got promoted. So just got really great news about their career development and then were fired. And as you saw in the fired employees panel at the beginning of our live stream, some people were fired, rehired, and then fired again due to pending court decisions. So a really big blow to climate science.
Exactly. And following off of that, you know, we lost a lot of the expertise at the National Weather Service, right? The United States has the best weather forecasting infrastructure in the United States. And because of probationary firings and also early retirements that were kind of pushed by DOGE, we see that the National Weather Service is significantly understaffed right now. And you can actually see that in this figure here. 30 National Weather Service offices are without a chief meteorologist. These are the people that run the office behind the scenes. They approve warnings or watches to go out. They communicate with emergency response officials, things like this. And you can see that there are 4 National Weather Service offices on the Gulf Coast without a chief meteorologist. Today is the first day of hurricane season. We need to make sure that those National Weather Service offices are continuously fully staffed. And even in the Ohio River Valley, of course, we had a tornado outbreak last week, and we're losing a lot of the expertise, and these very amazing forecasters could start to see, some burnout if they're pushed to their limits.
Yeah, and then we just want to highlight, so that's all the stuff that's already happened in our field. And we want to highlight also potential cuts that were proposed in the funding year 2025 White House congressional budget justification, as well as some specific departmental budgets that were released at the end of this past week. And then, so part of the reason, that I wanted to come talk about this is that there's been really significant cuts to opportunities for young scientists. So I would consider myself a young scientist because I'm in the second year of my PhD program right now. If Mark, you could just tap through the bullet points we have here. So the National Science Foundation is a really critical funder of research for young scientists. So at all the levels listed here, right, we have research experience for undergrads, REUs. If you've heard of REUs, right, that's founded by the National Science Foundation all over this country, not just for climate and weather, but for all science. So that's going to be, it's proposed to be cut pretty much from this new budget proposal. And so that would be a huge, huge blow to getting undergrads involved in research across this country. In addition, the Graduate Research Fellowship Program is proposed to be cut. I have many, many friends who are in graduate school because of this fellowship program. And if this program is cut, many of them will lose funding to finish their PhDs while in the middle of grad school, some of whom who have already spent 3 or 4 years working towards this degree. So this is absolutely a devastating proposal. And there's also cuts for postdoctoral fellowships. So after grad school, postdocs, that program is also being proposed to be eliminated. So just a really huge blow to the next generation of scientists. And just want to highlight that Paul Markowski, who talked at the beginning of our live stream, who's a tornado expert, highlighted that him and actually George Bryan, who are both big name scientists in the field and senior scientists, got their start at the University of Oklahoma at a NSF funded REU program in May 1995. So, if we didn't have REUs, we might not have Paul Markowski, which would be just a terrible world to be living in. And to highlight that, that means that in a few decades, many of the people that might be the next Paul Markowski are not going to have the support they need to do the science and support the American people in this way.
Exactly. And here we also just wanted to show the dismantling of the National Science Foundation. It calls for a 40% cut to the National Center for Atmospheric Research. So of course, that's a lot of atmospheric oceanic scientists who would be laid off. And you can also see here in this, we took a piece out of the budget. This is showing the number of people involved in NSF activities. And it kind of shows, what it was last year or in the current financial year of 2024 and how those will change in 2026. But you can see that, graduate students going from almost 42,000 to 12,000, and even funding for, elementary, middle school, high school teachers going from 130 students and teachers going from 130 to 40,000. So this would just be just a move that would, sabotage our scientific infrastructure here in the United States. And of course, the budget proposal also calls for the elimination of NOAA's Oceanic and Atmospheric Research Arm. So this is all of NOAA research, including Argo, which has been quite a popular topic during this live stream. And there's so many pieces of NOAA research. I'm going to go through them kind of quickly here. All 10 of NOAA research laboratories, including GFDL, which of course is where modern weather and climate prediction started in the 1950s. The first computerized weather model was developed there. We have weather and climate model development at these NOAA research labs. So just an example of that is the hurricane analysis and forecast system. This model, this hurricane forecasting model, was developed at these research laboratories, and it is maintained and developed further by them. And this model helped us last year predict days in advance that Hurricanes Helene and Milton would undergo rapid intensification when they were in the Gulf of Mexico and Caribbean Sea. So it's an incredible feat that we can predict so well in advance. And it's only because we've invested in these weather prediction models over the last few decades. And of course, we have all 16 cooperative research institutes that could be cut. These 16 cooperative research institutes partner with 33 universities, and this includes the Atlantic Oceanographic and Meteorological Laboratory. Of course, they provide the assistance to the hurricane hunters. So if we lost the cooperative institutes, we would lose some of that assistance and we need to take observations in these storms.
Yeah, and just to follow on that, I mean, cooperative research institutes are really this beautiful place where federal research scientists can interact with university academics, and these great minds from these two different areas of our field can come together and do this really powerful research. And like I mentioned, SIMS at Princeton is a really important cooperative institute that already got cut, and this is a proposal to eliminate all of them, which also includes series at Boulder, where I worked in undergrad. And, the work I did at these institutions was to improve water resource forecasting and to understand how tropical storms were changing. And, this is stuff that was really supposed to benefit the American public. So eliminating these research institutes eliminates these really powerful partnerships that serve the people here.
Exactly. And there's also, under NOAA's research arm, the regional climate centers. These regional climate centers provide climate data to farmers, to businesses, to a bunch of literally every part of the American economy uses data from the regional climate centers and all these other branches of NOAA. And we definitely need them in order to continue, predicting the weather, seeing what weather extremes are occurring, and how they will change under climate change. And of course, the research support for the National Weather Service, right? We need to continue to improve our forecast modeling systems so that we can continue to predict tornadoes or tornado outbreaks days or hours in advance, and be able to predict where those hurricanes will go and give the proper warning for them to save American lives and livelihoods.
Yeah, and this is a graphic of NASA's Earth fleet from Richard Ekman, who's a retired NASA program manager. He recently posted this on LinkedIn, and so we just want to give him credit here. But this is an example of, after his read through of the proposed NASA budget, of the satellite missions that could be and will be canceled under this proposed budget. And I just want to call out, I mean, there's obviously a lot of red X's here. This looks pretty scary. But if you look close to the Earth in the middle, there's satellites Terra, Aqua, Aura, and then also OCO2. And these are some of like the most critical, long-standing Earth observing missions that we have. They've supported a lot of the science that you've seen over this live stream, whether or not that's been explicitly called out. And the idea that these missions could end is really terrifying for what we know about the Earth system.
Yeah, that's so true. I mean, NOAA, of course, NOAA and NASA run the best observational system of our planet in terms of weather and climate, and it would just be crazy to to get rid of these satellites that the data is so critical that we use. And you can also see down here, these are all missions that are proposed in the future. and one of them here, INCUS, this is something I did my PhD at Colorado State University, and that's where INCUS kind of was developed. And it's just I watched, years of many scientists across the country work on this proposal for INCUS, and watching the satellite get built, and to know that it could suddenly be canceled would really affect our prediction and scientific research capabilities. And this graphic here is just showing 19 active science missions that would be canceled. So Stella just nicely mentioned Terra, Aqua, Aura. These have been going on for decades, since the late 90s and early 2000s, and they would suddenly be cut off. We would suddenly lose them because of this proposed cut in funding.
Yeah, and then just to kind of highlight, part of the point of this live stream was not only to share the science with the American people, but also to emphasize that this science was funded by the American people, right? And so, as this says at the top, this work has been supported by U.S. science institutions, right? And you can see here the National Science Foundation, NOAA, NASA, the EPA, the USGS, the NSF Graduate Research Fellowship Program, the Department of Energy. These are all funding agencies that have cuts being proposed that we just talked about. But they're also the funding agencies underlying all of the science that you saw on this live stream. So just want to kind of highlight that in this slide.
Yeah, no, we heard from some amazing talks, and they all, as Stella said, mentioned the support of our scientific infrastructure for that. So yeah, so that's why we're here. That's why we did this live stream. We just crossed hour 100. Amazing, Stella. I'm glad we could celebrate that together and remind folks why we're here. Great.
Yeah.
Okay.
I was going to say, if you're feeling strongly, we have the banner across the bottom. If you haven't called your representatives yet today, now is a great time to do so, or put it on your to-do list for after our next talk.
Yes, please call them. That would be incredible work. All right, so we're actually, we have one more talk for you guys as we fully complete 100 hours. Let's bring him on stage. Hello, Zach. How are you?
I'm good. How are you? And congratulations.
Thanks so much, Zach. We really appreciate having you on with us today. So for those of you who don't know, this is Dr. Zack Labe. He is currently a climate scientist at Climate Central. His research interests explore the intersection of climate risk, climate impacts, future scenarios, extreme events, early warning predictions, and data science methods like AI and machine learning. In addition to this work, he is very passionate about improving science communication through accessible data visualizations. Prior to Climate Central, he was a federal research physical scientist at NOAA's Geophysical Fluid Dynamics Laboratory until February 2025. So Zach, we're really lucky to have you on today, and we really appreciate you taking the time, and we'll go ahead and let you start your talk.
All right. And I just want to echo everyone again. Thanks so much to the organizers for such a successful last couple of days. I hope you can get some rest after this. And we'll get started. So something I like is data visualization. And whenever I'm talking about the Arctic, which I will be today, I actually always start with this graphic. And there's a lot of data here, but there's intentionally no labels, because I want you to look at the colors, look at the patterns to try to understand what's going on in the Arctic. To give you a little clue, you're looking at 40-some maps of the Arctic Ocean looking downward at the North Pole. And so I'll start adding some labels. So what you're actually looking at is you're looking at temperature data. Specifically, you're looking at Arctic temperature compared to average. And you're looking at them over the last 40-some years, which we really denote as the start of the satellite era. So older years are on the top and newer years, more recent years, are on the bottom. So this tells us a lot about what's happening across the Arctic region. It's showing that there's this long-term warming trend. So anywhere that's in red means it's warmer than average. Anywhere in blue is colder than average. So you can see there's a lot more red at the bottom in more recent years. But it also captures this variability. So not every year is necessarily the warmest year on record, despite the long-term trend. So I really like that this captures what we try to understand in climate science, and that's both climate change and climate variability. And the Arctic is a really particularly unique place for a lot of reasons, but specifically in climate science, it's a region that's experiencing some of the fastest warming of anywhere around our planet. And we often call this polar amplification. Basically means it's just an acceleration of warming in the high latitude region. And so I'm going to be talking today about what's going on in the Arctic, how it impacts you, and what are the potential important resources we need from science going forward. And so I think really the crux of all of my research, I tend to get interested in a lot of different topics, not just the Arctic, but I think what it really is summarized is my research is trying to understand the signal versus the noise. So the signal is climate change, that's human caused, that's causing this long-term warming all around the planet. But we also have this noise, that's the weather, that's day-to-day variations, year-to-year variations. And I really think we can frame it in this understanding of climate change and climate variability and weather to tell climate stories. And so I just heard from Dr. Marshall Shepard about his story. So I too have always been fascinated by the weather, even since elementary school. And I really want to make an important point here throughout my talk to say that I would not be here talking to you today without federally funded research. I also, like Dr. Marshall Shepard, had a science fair. Mine was 7th grade, trying to forecast the weather. But I'm showing examples here from my childhood of one going at Mount Washington to observe high winds. It's home of the world's worst weather in New Hampshire. And on the right is just an example of these little weather diaries that I have that I would track big storms in my area and elsewhere. And so what do we do as climate scientists? We analyze a lot of data. So we look at data from satellites, from observations, from climate models, and it looks like this. It's millions and billions and trillions of numbers. So obviously I can't look at these numbers and make sense of anything that's going on. So we have to use statistical methods, visualization methods to make sense of it, because our planet is a super complex place. And it all revolves around energy coming from the sun. So you're seeing an animation, a seasonal cycle of incoming solar radiation during each month of the year. So you can see the oscillation depending on if you're winter in which hemisphere and summer in the other hemisphere. And so all of that transfer of heat, that influences temperature. So now you're seeing another animation, another seasonal evolution of temperature change. So you can see the different patterns between the hemispheres. You see much darker colors in the northern hemisphere. Partially that's related to land. So you get cold outbreaks from the Arctic during winter that head south. You can see the warm conditions around the tropics. And if you look closely, you can even make out the signature of features around the tropical Pacific, like El Nino and La Nina. In addition to air temperature, we also have the ocean. The ocean is a huge part of the climate system. So now you're taking a look at, again, the seasonality of changes in ocean temperatures at the surface. So you can see this, to me, it almost looks like a jump rope going up and down as the seasons go on. In addition to all these other phenomena, we have moisture. Moisture is being transported poleward out of the tropics. You can see, we've heard a lot about the intertropical convergence zones. So those brighter colors right around the equator, that moisture comes out and plumes these atmospheric rivers. And so climate scientists, we have all of these interactive features going on in the Earth system, and we need to try to make sense of it. And for me, one way that I try to make sense of it and communicate this amazing planet in complex science is through data visualization. And to me, it can be a really powerful way of storytelling. And the Arctic, as I mentioned before, it's this rapidly warming place, and it's not something that's happening in the future. It's happening now. So we need to communicate what's happening in the Arctic in real time. And to me, this is an opportunity. It's an opportunity to communicate the impacts and communicate the importance of the science that's going on. As one example, Arctic sea ice has this seasonality where it grows during the winter and shrinks during the summer. That's normal. I'll talk about why it's not normal going forward and later in the talk. But for many years, the only articles that were being sort of published on Arctic sea ice were during the maximum at the end of winter and the minimum at the end of summer, and that was it. But we know that the Arctic is experiencing these extreme events all throughout the year. Here's one example of a particularly anomalous year in the Arctic in 2016, which had many periods that were quite anomalous within the region. So by monitoring changes in Arctic sea ice, not just at these 2 data points, but throughout the year, we can tell climate change stories all throughout the year. And again, it's an opportunity to share stories, not just about the science, but the impacts. People live in the Arctic. One example was during the winter of 2018. So what you're looking at on the right is a map. On the right-hand side of that map is Alaska, on the left is Russia, and in the middle is the Bering Sea and Bering Strait. So what you're looking at is actually sea ice during February of 2018 retreating, melting during the middle of winter time. That's not normal. And this had major impacts for communities that live along the Arctic. One particular example was in a town that just relies on this airstrip on sea ice for bringing in supplies during the harsh winter. But in 2018, there was no ice, no airstrip, and no way to get supplies to this community. So we're seeing impacts in the Arctic are affecting people right now. And here's an showing a picture of where that airstrip should have been if there had been sea ice like normal. So, okay, the Arctic, it's this really remote place. A lot of people were never going to get a chance to visit there. So where is it? So here's a map looking downward again at the North Pole. On the right-hand side, that's Russia and Eurasia. On the left-hand side, that's North America. And then there's many important regions of the Arctic. So what we try to do in climate science is understand these changes by place to place. And as I've been talking, Arctic is this rapidly changing place. So what we try to do is we try to understand how it's changing and how it's evolved through time. So you're looking at a graph of temperature from a variety of different data sets from 1900 all the way to present. So you can see there's a lot of squiggles in this line. That's the year-to-year variability. That's the noise, the weather. But you can see after around 1980, there's this almost, upward trend, and that's that Arctic amplification period. And so you might have noticed there's all these different lines that they don't necessarily always line up with one another. And that's because particularly prior to the satellite record, there's uncertainties in the data. And so we need to try to understand and quantify those uncertainties. You might also notice there's other features in this line graph. You might have noticed there's sort of this upward slope in the early 20th century. That's more of this natural climate variability phenomena. And then that more steeper slope, that recent amplification of trends in the Arctic. And so how do we monitor changes in the Arctic? And we've heard a lot about the importance of satellite observations. So here's taking a look at both polar regions side by side of the seasonality, looking at each month of the year. So on the left is the pulse of Arctic sea ice growing in winter, shrinking in summer. And on the right-hand side is the same sort of phenomenon, but for Antarctic sea ice. And so, this seasonality of sea ice, it's normal in the Arctic, but here's the problem. The problem is we're warming in the Arctic. So you're getting more sea ice melting in the summer than has the ability to reform during the wintertime. So it's leading to a net loss of ice. So you can see that here by the animation in the middle graph. And that's driven by air temperature increasing. That's the left graph. And on the right-hand side, that's changes in ocean temperature, which is also warming, influencing this sea ice decline. Here's another visualization if you like looking at sort of maps of this phenomena. So you're looking at changes in the thickness of ice. And on the bar graph, you're seeing the total volume of ice as it's changing over time during this last 40 some years. So again, another indication showing that sea ice, it's shrinking. It's shrinking in terms of the size and the thickness. And you might say, okay, you've only shown me like 40 some years of data, maybe 1900, but what does this really mean in the context of longer climate? So climate scientists, we've thought of this, and there's amazing work being done by people who work in paleoclimate, basically reconstructing Earth's climate in the past. So here's a graph showing of changes in sea ice during the last 1,500 years. And on the right-hand side, you can see that's that really fast decline that looks completely unprecedented compared to every other period. Yeah, that's where we are today. So currently changes are unprecedented in our historical records. And this is a wonderful example, trying to understand changes in sea ice that's contributed by citizen scientists. So one example was a project that was called Old Weather, where there were many diaries of explorers and whaling ships that went across sort of northern Pacific Ocean, northern Atlantic Ocean into the Arctic in the mid-19th century. So citizen scientists, you could volunteer and actually look through these diaries and old maps to try to attempt to reconstruct our understanding of changes in sea ice during that prior period. Again, the story is the same, that the changes now, what are happening now, again, are unprecedented in our understanding. But I think it's a really exciting example of how the public can get involved in the scientific process as well. And so the Arctic, it's really complicated. As I've been saying, it's not just as simple as the temperature goes up and the ice melts, but there's a lot going on and it's happening in real time. And I think a really amazing example of highlighting what's going on is through this annual report produced by scientists from all over the world called the Arctic Report Card. It comes out every year around the month of December that almost provides a report card, a grade on how the Arctic is doing from all of these different components. So you can go in the Arctic Report Card and see the documentation of these changes from year to year over the last several decades. And in addition to this Arctic Report Card, it's not just physical scientists, writing a report and publishing it, but the audience is geared for non-scientists and geared for decision makers and policymakers. And we also have essays as part of the Arctic Report Card from indigenous peoples who live within the Arctic to hear directly the changes that they're seeing and how it's affecting their communities and their culture. And we have amazing organizations right now that really highlight connecting the science to people, connecting the science to these communities in the Arctic. And one example of that is the Alaska Center for Climate Assessment and Policy, which does an amazing job at establishing trust in relationships with these communities over time for these really amazing relationships to communicate what's going on. Polar science community is also great in it really accelerating early career scientists and how they can become involved in the process. One of the organizations I'm involved with is called the U.S. Association of Polar Early Career Scientists, US APEX. And if you're interested as an early career scientist in the polar community and want to find out how to get more involved, I encourage you to check out some of these different organizations that really support early career researchers. So what about going into the future? So I've shown you the changes in the Arctic are already happening now. What's it going to look like going forward? So I like to say, as a climate scientist that spends all day on a computer, that I also have a laboratory and run experiments. It might not look like a chemistry laboratory, but our climate models are our way of conducting experiments. And I'm going to show you how we do that. So here's a graph. It's showing observed temperature changes during this recent period from real world observations. The graph on the x-axis, that's showing years, and on the y is showing change in temperature for the Arctic. So what I want to do now in my experiment is run a climate model simulation for this historical period to see, is our climate model able to simulate the variability in current changes in temperature in the Arctic? So that's what you're seeing in blue. And you notice it doesn't match perfectly, and that's okay because we can't quite capture exactly that year-to-year variability. But it basically, as long as that yellow line is within that sort of blue spread of the climate model simulations, then yeah, it's okay. So our climate model does a pretty good job. What if we were to run a climate model and take away humans? And in this case, there's no contributions coming from greenhouse gases. What would Arctic temperature look like at that point? So now it's coming, that's what you're seeing in the gray shading. So you can see it's flat. Clearly, the yellow line is rising above the gray line, indicating that yes, humans are, of course, influencing Arctic temperatures. So as you can see, this is one way that we can run these simulations with or without the contributions of greenhouse gases to understand climate change. Now, what about going forward into the future? What if we were to rapidly accelerate the emission of fossil fuels? What would temperature change look like? And that's what you're seeing in the red shading, going all the way to 2100, with temperature changing over 14 degrees Celsius across the Arctic, which is a massive change. Okay, so what if we run a simulation where we start to moderate the emission of fossil fuels? What might that look like? As you can see, very different future, but still a significant change. And we can run lots of these different scenarios to understand the effect of fossil fuel emissions on Arctic temperature change. And for me, again, this is our way of running experiments with our complex planet. So, okay, what does that look like if I were to show you an animation? So previously was just sort of an average. Let's take a look at these different types of scenarios from a climate model output for a world without the contribution of humans, that's in the upper left, compared to these different scenarios, sort of the amount of fossil fuels. So this animation is going to run forward into the future. Anywhere in red means it's warming. Anywhere in blue means it's cooling. I'm sure you're going to have a hard time finding any blue in these animations. So you can see, a couple features. One, the Arctic is this huge red blob. That's, Arctic amplification. But you might also notice that over land areas are much more red than over ocean. And that's because the land is warming faster than the ocean surface. And of course, we live on land, so it's going to affect us greater than, let's say, the global mean. So a question that was asked is, we have this rapid changes at the top of the planet. And in around the 2010s, there was all this extreme winter weather occurring on the East Coast. So here's a newspaper article from Snowmageddon. So at the time I lived in Pennsylvania, and I remember a series of crazy snowstorms that hit the Northeastern United States. So a question that people started asking is, one, why are we still having such extreme winter weather when we know of global climate change? And two, is this rapid change at the top of our planet influencing perhaps this extreme winter weather? And so that's what I worked on as a graduate student. So I tried to understand these connections and linkages between the two. And this was all thanks to support from the National Science Foundation. Without their support, I would not have been able to think about this really complex topic. And unfortunately, this is just one area we are starting to see cuts proposed in the budget for reductions in the amount of graduate fellowships being offered to support students to understand these really critical topics in climate science that affect us all. And this question, it continues to be an open question about linkages between the Arctic and lower latitudes. But even in the earliest and primitive of climate models, we saw evidence that this might be the case. So here's a paper from 1973 that ran a very simplified global climate model that removed all the sea ice and tried to understand what happened. And in this case, there was a rapid warming where there was no ice, that's expected. But what was a bit unexpected was that there was a cooling in response to this over the lower latitudes, even in this really primitive early climate model simulation. So that was, one indication of, maybe something's going on. We've seen this graph a lot from Suki Manabe, showing the amazing work, groundbreaking work that was done at GFDL to simulate global climate change. And here's another visualization showing that even in the earliest climate models, we saw the most warming at high latitudes. And of course, one of the proposed connections in trying to understand, the Arctic versus, lower latitudes is through the jet stream. It's this up high in the atmosphere that guides weather and temperature variations around our planet. So are these two linked through the jet stream? I'm not going to provide an answer for you today, but I wanted to show this graphic where a lot is happening, and that's intentional because this is a very complex topic with so many interactions in the climate system. So this is still one area that we need more work on in the future. And admittedly, I'm a weather nerd. I have a meteorology background, but I have to be careful and also mention that the ocean is also really important for the Arctic. So here's a visualization showing that the polar transport of heat coming from the North Pacific, coming from the North Atlantic, that deep ocean heat that comes into the Arctic also influences regional variations of Arctic climate change. And so I've spent a lot of time talking about modeling. That's what I mostly work on. But during graduate school, I had an opportunity to go to the Arctic. And I can't give an Arctic talk without highlighting some of my pictures from my journey. So this was back in 2017. We took an icebreaker from Svalbard, a little island off the coast of Greenland, and went into the Arctic. What you're looking at here is a drone image of our boats. You can now locate it there. Anywhere in white, that's sea ice. Anywhere in the really dark black color, that's open ocean water. And so you're looking downward, from high above. And, here's a picture of that drone that took those images of the Arctic Ocean. We nicknamed it the cryocopter. Cryosphere is what describes the frozen planet. So anyway, that's the type of images, and you can attach all sorts of instruments to better understand the Arctic and its changes. So here's a little bit of a closer view of our boat. So if you look really, really closely, what you essentially do is you sort of anchor the boat to one of these pieces of sea ice. It's called a sea ice floe. And you actually get off the boat, walk on the ice, and then do all sorts of different experiments. So you can see our little footprints from us walking around to do some of these experiments to understand changes in sea ice. But going to the Arctic is not without challenges. So we did get stuck in the sea ice for maybe 24 hours. Got awoken in the middle of the night by basically a giant shove and me falling out of bed as the boat finally broke free of the ice. So doing this type of work is extremely challenging, costly, and provides a lot of resource coordination. So what do we do? You get off the boat, you go down to the ice. What are some of the things you do? One of them is drilling ice cores. As I mentioned earlier, I'm on a computer most of the day, and this opportunity was basically for me to get an experience of what it's like to go out to the polar regions. So I'm not the one operating the ice drill. I'm actually in the back taking notes, and that's because I quickly learned that even though this was the best experience of my life, I am not good at field work, and I broke the ice drill many times. So I finally gave up on the sort of manual labor of this, and they gave me the notepad to take notes. But so yes, it was an amazing time, and I encourage you to try field work if you're a modeler. But yeah, I learned that I'm better suited behind a computer. So maybe this was a bit easier for me to do. So one of the things you try to understand is salinity within the sea ice. So actually we took beet juice from our lunch and we poured it onto the ice, and you can actually see brine channels within that. So here's kind of a better demonstration of that in one of those ice cores to show how salinity moves within the sea ice. You also do things like trying to understand snow on top of the ice, things like how deep the snow is, but also what's in the snow. So if you look really closely, there's a thin black layer. That's actually soot and ash that came from wildfires in Greenland that deposited within the snow layer. So you can understand different information about the snow from doing these types of assessments. The Arctic is also very alive. Here's a picture of algae in the Arctic, that green patch. So the Arctic is not just this frozen wasteland. There's lots of life within the Arctic. I, of course, have to show a picture of polar bears. Ishborn is Norwegian for polar bear. I was on a Norwegian icebreaker. So here's a picture of a polar bear and her cub sort of jumping from an ice floe. And, there's so many other amazing things like glaciers within the Arctic. And then when you do all these experiments, at the end of the day, you go back onto the boat and there's actually big laboratories within the boat to understand some of your findings. So here's a polarization of what a sea ice core actually looks like under a microscope. And, this type of science it requires, as I said, so much coordination. I think one of the most successful international scientific collaborations was this expedition called Mosaic, where they essentially froze an icebreaker within the sea ice for an entire winter time in the Arctic and did field work to understand changes throughout the year. And so again, they basically froze the boat within the middle of the Arctic and let it drift over time throughout the year. And it was an amazing amount of data in science we've learned from this. And here's another complex graphic just to, again, highlight how complex the polar regions are. And we need to try to understand this both through modeling and observational work. And to really understand the Arctic, we need everybody. We need everybody, not just scientists, but we need educators, social scientists, innovators, communicators. And I think it's really important, if you're interested in climate change, we need you as part of this solution and to move everything forward. And this was highlighted in a recent effort by the National Science Foundation in the Navigating the New Arctic project, which really thought about this holistic view of Arctic science, including transdisciplinary collaboration, working with indigenous communities, working with physical scientists to work together to understand the Arctic change. And for me, this is all about, not just that the Arctic is, changing so fast, but also just for the betterment of science. And it allows us to have trust in our science. It provides open data. And all of this encourages innovation, is when we're inclusive in thinking about all the components working together. But unfortunately, we're in a tricky situation right now. This is from a recent article highlighting the proposed cuts that have already occurred this year to the National Science Foundation. So the Office of Polar Programs sort of falls under the Geosciences division of the National Science Foundation. And there has been 88% less money awarded in grant money, particularly for the Polar Office, in addition to layoffs within that office. So we're seeing significant cuts to polar science. And as I've highlighted before, the Arctic is rapidly changing, it's impacting people, and we need to understand what's going on, especially going forward into the future. In addition, we're also seeing other organizations being impacted in the polar science community for these cuts, again, relating to lack of federal support. Another, highlight is, in addition to sort of seeing less grant money to support ongoing and new projects, but we're also seeing losses to data products that provide crucial information on changes to the Arctic. One of them is related to the Sea Ice Index from the National Snow and Ice Data Center. Really, the classic iconic data set to describe Arctic change is now losing support, particularly for service support. The data will still be available, but if something breaks, it might not be as easily addressed. And so we're seeing cuts to that occurring right now. And this information is used not just by scientists, but it's using communities, it's using for transportation, for political security, for economic security. So this data has far-reaching effects, and it's losing federal support. And the Arctic has a lot of questions that remain uncertain. Here's taking a look at projections into the future. On the right-hand side is the Arctic, on the left-hand side is North America. Basically, the takeaway here is that the wider the colors means the greater uncertainty we have in our projections. So you can see there's a huge range of possible futures within the Arctic, and improvements to scientists will help to refine them. And I don't normally show images of polar bears, but I think this is really, for me, has always been an iconic image. The Arctic, we're losing sea ice, and we're now seeing cruise ships actually go within the Arctic for tourism. And I think this image from a couple years ago of showing the cruise ship and the polar bear really highlights this is a completely new Arctic compared to even just 20 years ago. And what are the challenges that we might face with something like this happening? We need, your help in understanding it. And again, bringing it back to, we need everybody working together to understand this rapidly changing place. But I want to leave on a positive note, if I can. And I love this saying. I think it was coming from Ginger Z, had this series called "It's Not Too Late." And I wanted to show this research paper that showed the sort of probability of ice and ice-free Arctic coming forward into the future, basically saying that it's not locked in. That if we rapidly reduce fossil fuel emissions, we can perhaps prevent an ice-free Arctic. So critically, the decisions we make now will affect our future, but it's not too late to avoid the worst of the changes within the Arctic Ocean. And I'll just end by saying again, my career would not have been possible at all without, amazing colleagues, support, mentors, but also federal research. All of my entire journey from undergrad, who was a meteorologist who got into climate science, all the way from my most recent position at NOAA, all revolved around federal research support coming from a variety of different agencies across the government. And in addition to all of this scientific research, I love science communication. I love talking about it. That would not be possible, again, without open federal data. I have a website that provides visualizations of climate information that use data sets from all across the federal ecosystem for weather and climate data. And without their support, the federal research dollars to provide the infrastructure to make this data freely available from taxpayer dollars, I would not be able to do the science communication of the climate change topic. And I will end here and take away any questions. Thank you.
Zack, thanks so much. That was an excellent talk. As we know, Zack is an incredible climate communicator as well as an incredible climate scientist. Those visualizations were amazing. We really appreciate you taking the time to join us today. Okay, we've had a lot of chatter in the comments section, a lot of love for your presentation, and also a lot of questions. We won't be able to get through all of them, unfortunately, but definitely let's start diving in. I just want to show this comment. It's so great that so many scientists could come on and share their research. We're excited to do it. Okay, so let's get some questions up here. This question is from Hannah. Could you also get an estimate of how old the ice is? I'm curious if you guys did do this.
On our excursion, we did not do that, but one sort of estimate, one way we think about the age of ice is through the thickness of the ice. So essentially, the thicker the sea ice is, the older it is. And one way we actually track the age of sea ice is from satellite data. And so what we do is we actually track little pieces, there are sea ice flows. We sort of track them as they move across the Arctic. And if they don't melt during the summertime, then quote unquote, they have a birthday. At the end of the summer melt season, it's the birthday of that piece of sea ice and it becomes 1 year older. And so a couple decades ago, the majority of sea ice within the Arctic was actually several years old. It was quite thick. But unfortunately, as I mentioned before, we're seeing more and more melting during the summertime. So that sea ice is becoming thinner and it's becoming younger. So now we're moving from the old Arctic was thick, old ice. Now it's thin and young ice. And of course, that has many, implications for what's going on in the region.
Amazing. Thank you. Our next question is from Michael. Are there climate change mitigation activities specific to the Arctic, or is change there somewhat passive to removal of greenhouse gases from the atmosphere?
Yeah, so there's a lot of work trying to understand the reversibility of sea ice. So in essence, we've already experienced quite a loss of, sea ice, and going forward, it's projected to continue if we don't mitigate greenhouse gases. But let's say we do. Let's say, going forward into the future, we begin to rapidly mitigate climate change. So we can run simulations with our climate models to understand what is the behavior of sea ice. And I think another kind of positive message from that, it's not too late, saying, is that we see that there is a rapid mitigation of greenhouse gases and we do start to, lessen global warming, we actually see sea ice rebound and begin to reform. There's a lot of uncertainties, technical details with that statement, but, sea ice, it's frozen ocean water. So if you cool the ice surface enough, it will freeze. And so I think there's a lot of work going on right now to understand all sorts of mitigation activities and how it might influence changes within the Arctic, specifically on sea ice and how it could reverse and rebound.
Amazing. Thank you. I really love some of these speaker-specific questions. If you could go back to the field, would you?
Oh my, great question. Yes, somebody who's operating a fieldwork excursion, bring me along. I'll help visualize the data or something. Yes, as I said, it was the best experience of my life. I'll try not to ramble this answer because I get so excited about it. But I remember seeing sea ice for the first time. I've been studying it for a couple years now in graduate school, and I was on the top of the icebreaker, and I remember seeing the first little piece of ice go by the boat, and it was just really tiny. It was mostly open ocean water, just a little piece of ice. And I thought, oh my gosh, that's sea ice. And I tried to contain my excitement, and then all of a sudden we hit like a wall of sea ice. And it was just the most amazing experience. And the best way I can describe it is it's truly like you're on another planet. You have, sort of the whitish hue of clouds in the sky. The sea ice is white, so it's quite a little disorienting. When I was there, you have 24 hours of daylight, and you just feel like you're all around the world in a completely different planet. So yes, I would love to go back. I would love to go to Antarctica, see what it's like in the other polar regions. So yeah, the answer is yes.
Amazing. Yeah, no. It's funny because a lot of us really just sit behind computers mostly and run our climate models. Here's another good question. Starts with a lovely comment. I love your visualizations. What's the most surprising or alarming trend you've discovered while working with climate data? Have you encountered any unusual patterns we can't yet explain?
Yeah, great questions. So I admit that I think one thing for me as my takeaway for visualizing Arctic, changes every single day of the week. I run, different graphs. And for me, it's been a better appreciation for this noise, this variability in the climate system, and particularly regional change. We often in climate science talk about an average over a huge area, like the global average temperature or the Arctic average temperature. But there's so much differences from place to place and in different regions that we really need to work on understanding. Some areas, let's say I just plotted a graph today of showing changes in June temperatures across the Arctic. And so you actually don't see that much warming across North America, northern Canada, but over Siberia, you see a huge warming trend during the month of June. And so I think it's been a better appreciation for understanding climate change versus climate variability and the importance of thinking about weather and meteorology when we talk about climate change too. I think this is really useful for communicating the science as well. Oftentimes I get many questions like, okay, this year was not the warmest year on record. That doesn't make sense. The globe's warming, but it's this variations. And that's why climate scientists, we talk about the long-term trend through, in the midst of this year-to-year variability. So I think for me, looking at this data, I see that variability and the long-term trend and have a better appreciation for the regional questions I think we should be asking in science.
Amazing. Thank you, Zach. We have a few more communication type questions. How do we communicate to the non-scientists how Arctic warming affects them?
Yeah, great question. And it's a question I won't have a good answer despite I've been asked about that same wording for years, so I really should come up with something better. But it's challenging. It's really hard. How do we relate these rapid changes for, again, this place where most of us will never get a chance to visit? How do we relate this to communities? And, I'll give one example of a tangible example of how this affects people. And so I showed a visualization of the Bering Sea, this region in the northern Pacific Ocean between Alaska and Russia. And this is an area seeing less sea ice, it's seeing warming ocean temperatures. And the way I try to relate it is, if you remember, I'm not sure if it's still on the air, but there was a TV show called The Deadliest Catch, I think on the Discovery Channel. And it talked about fishing, for crabs in the Bering Sea region. And so for many of these recent years, we've seen so much warming in the Bering Sea that when they have gone crabbing in that area, the crab were not in the area that they've been for generations. And they essentially, where did they go? And we're seeing this, as that crab or that loss of them or, shift in migratory patterns, that affects you at the grocery store. If you go for seafood, it's going to increase the price of crab. So, that's one economic example of how it affects people. I think, other ways that I try to describe it is that the Arctic is also this really important place that I like to think of it as the refrigerator of our planet. And if you begin to really warm the refrigerator that maintains, Earth's temperature, then you're going to see it has global implications, enhancement for global warming. So this is it's a small but very sensitive region that impacts us. And I always try to still, as I said, working on better communicating this about why should we care about the Arctic.
I love that. The refrigerator reference, that was really cool. We've had a few questions. So you were talking about, climate change mitigation strategies to reduce fossil fuel emissions. We've had a few people ask about individual ways to reduce fossil fuel emissions in their day-to-day life. I'm curious if you have a comment on that.
Yeah, so I will preface this by saying that, I'm a physical scientist and I try to sometimes to admittedly stay in my lane. So I know the climate change variability, the meteorology, but I'm not an expert on climate change solutions. So I can't, there are amazing colleagues that I work with who can provide you amazing examples for this, that they've researched and worked on this topic. But, as some, helpful, that's a non-answer. Some ways that can do so is there are large contributions to fossil fuel emissions from things like the food supply, from transportation, from energy, electricity. So these are direct ways that you can try to reduce, the fossil fuel emissions from, driving, from leaving a light on per se. And another answer that I think is really important is voting, being an active participant, giving those calls to your congressional makers about the importance of science. And if you're passionate about the importance of climate change, to make sure you support policies that do reduce fossil fuel emissions.
Amazing. Well, thanks so much, Zach. We're at the end of the hour, the end of the segment. We really appreciate you being our last speaker of the entire live stream event. So thanks so much for preparing that amazing slideshow and spending the time with us.
Thanks, Mark.
See ya. All right, so we're now going to have a closing statement. And to do that, we're going to bring on all of the organizers. So we can only have 10 people on the screen at the same time. So a few of us might be cycling in and out. But if we want to do that, especially, of course, our fearless leader, Jonah, who will start us off on the closing statement.
Hi, everyone. Thank you everyone for being with us throughout the last 100 hours. It's been absolutely incredible to see all this amazing science and to get to share it with you all. I think you can see this, many of the organizers coming up on screen now, but thank you for being with us as we've had this event together, and thank you for working with us as we work together to save America's forecasts. All the organizers wanted to come out and say hello. Here's everyone, or at least as many of us as will fit on a screen. Say hello, everyone. But I wanted to acknowledge all these amazing volunteers. So we've got Andrew and Mark and Margaret and Nather and Nick and Henry and Miriam, Tommy and Ash, Lily, Stella, Phoebe, Paulina, Maggie, and Sil. Some of these people have been up on your screens. Some people have been behind the scenes, but every one of these volunteer meteorologists and climate scientists have been giving everything they've got to put this event on for you. We know that the last 100 hours have been a marathon, but the truth is that the organizers' marathon started long before that. These incredible volunteers have been contacting and coordinating hundreds of speakers, hosts, directors, and chat moderators to fill out these 100 hours, setting up and guiding our participants through a complex technical setup, developing a political message with a clear action and visual identity from scratch, and promoting the event tirelessly on traditional and social media. I really want to emphasize how quickly this event came together. A month and a half ago, this idea didn't exist. Less than a month ago, we sent out our first email to recruit speakers. So, as we worked, new organizers appeared like a miracle, adding new and wonderful capabilities all the way up to the final days of prep. While many of us did not know each other before, I feel over the past few weeks that we've become like a family, working quickly and collectively towards a common effort. And one of the biggest joys of this event has been joining together with these people without whom this event could not have happened. And I should say that we really benefited not just from the other organizers' ideas, but from many colleagues, our friends, our family that we've been working with and we've been sharing with over the past few weeks. Thank you for your support as we ran away and joined the live stream for this time. So although the efforts of all of our organizers have been truly unimaginable and indispensable, I did want to mention the unique and deeply fortuitous contribution of Miriam Nielsen. When the early organizers decided to put on a marathon live stream of weather and climate videos, focused in part on the closure of the NASA GIST lab, we did not have much direct experience with any of these things, and we certainly did not know there was a NASA GIST scientist who's experienced in running marathon live streams and in weather and climate video journalism. So Miriam's appearance on the scene, her deep knowledge of how to run the sort of event we had only a sketchy sense of, and her bravery in sharing the historic final moments of one of our country's great centers of earth science, not to mention her resourcefulness with additional microphones when needed, has been the sort of miraculous rare event that confounds statistical analysis. So thank you so much, Miriam. We also, round of applause. We also really want to thank our speakers. First, our fantastic keynotes. We've spoken about how much we idolize many of our keynote speakers, whether they're big names in our field or rising stars. But I think one of the first big and pleasant shocks of this event was how quickly many of these prominent scientists agreed to speak and lend their support to our effort. I do not know if this would have been possible without their leadership and their example. They then came and knocked it out of the park, giving keynotes making clear just how incredible America's weather and climate science are, the beauty and majesty of our atmosphere and ocean, and the critical importance of our infrastructure for observing and understanding these important systems for the health and well-being of all Americans. They have completely justified their hero status in our eyes, so thank you to all of our keynotes. Then there's the many, many, many speakers who volunteered their time to come before the public. We've always felt that the scientists in our community are a special group, passionate about finding out the truth of how our complex and fascinating world works. And when the word of these cuts came down, we wanted the public to know the incredible group of people out there working at their disposal, at your disposal, and we wanted you to know their incredible research. We wanted you to know the treasure that government funding has built and that belongs to you. But we had no idea whether the community would have the time and the willingness to come before the public on short notice and share their work. So speakers, you're an inspiration to all of us. We're all so, so thankful for the work that you do. I want to thank the people who participated in all our special segments, the scientists. Thank you to speakers. I want to thank the people who participated in our special segments, the scientists using their personal time to join us during the NASA GIST segment, the terminated NOAA employees, the National Weather Service and American Meteorological Society heads, the international scientists sharing their kind words about American weather and climate science. Your participation helped to bring our stream to new heights and to drive home our message of the urgent need to save America's forecasts. I want to thank the hosts, too, who helped to introduce our speakers to our audiences, helped to get our message out and get people calling the representatives. And I want to thank you for building a connection between us and our viewers and for being willing to think on your feet while on camera. I also want to thank the directors for getting us through 100 hours of scientists navigating their way through an unfamiliar tech setup. The smoothness of the stream is a real testament to their grace under pressure. And I really want to thank our chat moderators. I feel like the chat has really been the lifeblood of this event, and they've kept it full of interesting links and facts, and generally just kept the vibes really great in that chat. So thank you to our chat moderators. Finally, the real discovery for this, for all of us in this event, has been you, the incredible audience who's been with us throughout the 100 hours. The many people watching at home and the people who have been interacting and participating in the chat. At the same time that you've been watching us, we've been glued to the chat, and it's given us so much hope and joy and inspiration. You know, this is a hard moment, and specifically for the climate scientists, you know, sometimes, you know, it can be, I think someone mentioned this earlier, climate science can sometimes not always be an easy field. And it can be, it can sometimes feel hard, especially we've heard sometimes, and I've seen this in the field for senior members of our field, the weight that comes with handling this sort of research and ideas for a long time. You can start to feel a little bit out of step sometimes when you feel the urgency of the situation and to feel like the world maybe, it's unclear how much it really resonates with people beyond the science. But we've been sharing the enthusiasm and the support you've been showing to us with people in our field beyond just the organizers, beyond just the speakers. And you should know that it's changing people. It's really opening people up. It's giving them some joy and some hope that there's a public out there that cares about this. People want to understand. So, you know, it's been really wonderful to having your support. And now we actually have Lily. Do you want to share some particular highlights from our time with the chat?
Yes, absolutely. So now that the live stream is coming to an end, let's come together and celebrate some of the things that we have achieved together over these past 100 hours. So yes, some data in these 100 hours. We have heard from over 200 weather and climate scientists whose talks received over 170,000 views. And that's resulted in over 7,000 calls made to Congress. And that's just what's tracked on the 5 Calls app. So thank you so much to everyone for all of this, but also for all of the great memories that we've created together. And we've put together some of our favorite chat moments. You might recognize some names on here. So first off, I think, yeah, like we learned that science is super cool. And this is my personal favorite. I'm riveted and will be researching this Hadley circulation effect more. Some love for paleoclimate, biogeochemistry, isotopes, sediment, satellite, biometeorology, clouds. Glaciers are like dinosaurs in terms of coolness. That's a great compliment. And of course, you guys really loved all of the animations. And I think for me, like one of the most incredible things was watching how you were engaging with the information, making these connections between our talks and noticing these reoccurring characters or like common themes. So here are just some of my favorites, reoccurring characters that popped up. Yes, so MJO was back. El Nino came back many times. There was, you guys remember the cloud radiative feedback effects. Those came up during like a bunch of our talks. And yeah, overall, we're just really touched by this community that we have all cultivated together. And here I'm just sharing some love for our scientists, some very wholesome comments about how like many of you are watching the stream like between going to work or going to school and just really loving it. And also love for the Laurentide ice sheet, of course. Yeah, and most importantly, I think something you know that meant a lot to us was that many of you were so inspired by our stream that you took action. And for those of you for whom like this was your first time calling your representatives, I'm so proud of you. Yeah, and we're just so grateful that you really cared about our cause and also like put what you learned here into action. Yes, and this is my favorite meme that I saw on Tumblr about this. Yeah, so just like, it's so great how many of you called your senators for the first time and then you kept doing it and you felt more confident about it. And we hope that you keep sharing this message even after the live stream is over. Yeah, and last but not least, we have to give a shout out to our Tumblr community who really showed up for us. And here are just some highlights from everything that went on in the past 100 hours.
Thank you so much, Lily. That's really beautiful. And yeah, this has been a pretty emotional few days, and to get to meet you all, to connect with you all has been such a joy. I know you've been with us for 6,000 minutes, and I've already spoken a bit beyond that, but I just want to ask for a few final minutes. Oh, yeah. Actually, let me take a moment. Can we bring up Margaret? I would love to hear what Margaret has to say, please.
Gotta find that unmute button. Okay. Before we wrap up, And my co-organizers are going to have to forgive me for going rogue here, but I want to take a minute to talk about other scientific disciplines who are also losing their funding. So we've just spent 100 hours, which is crazy, learning about the value of weather and climate science, but there are so many scientists from so many fields out there doing valuable research, and they're also experiencing cuts. So I want to call on scientists from other fields to organize their own marathon live streams. I'm looking at you, health sciences. I know NIH cuts are really interfering with your ability to do a lot of really amazing work. And I know there are a lot of you, so I bet you could talk for even longer than 100 hours, and that is a challenge. And I would totally tune in. So, but regardless of whether or not any of our scientist friends from other disciplines are able to organize a marathon live stream, I really hope that now that you know how to call your reps, you'll call them on their behalf as well, because they really deserve it.
Thank you so much, Margaret. Is there any? Do any other organizers have thoughts they want to share with the stream? Maybe put it in chat if you do. Would love to hear from you. I just have a final few little words here I wanted to share with everyone. So, you know, this has been a really joyful event, but we also know that we're here in some hard times. And I thought about this during Dr. Jeff Masters' incredible hurricane talk. If you haven't watched it yet, you really should. We already have it up as a standalone video, so you can go and find it on YouTube. And I'm going to give some spoilers to it, but even in spite of that, it's worth watching if you haven't seen it. So while flying with the NOAA hurricane hunters, Jeff found himself in an airplane flying at low altitude, caught in the eye of a Category 5 hurricane with an exploded engine. While the people on the plane knew that they had been going to head into a storm, the terror and peril people on that plane experienced went far beyond anything they could have imagined. Reflecting on that story, it made me think of the situation that we're in here. The cuts we're facing are already causing damage and undermining your forecasts. But what is being proposed is our own Category 5, catastrophe for this country and for our community. Cutting NSF and NOAA's Earth Science in half, eliminating NOAA's research arm, eliminating the crucial opportunities for getting young scientists into the field like RAUs and graduate research fellowships, driving away international scholars who want to come and work in the US. This is our own unnatural disaster in the making. Something about big changes that they're often hard to imagine until you're in them. It's hard to imagine losing something you've had for so long, and even harder to imagine regaining something you've once had but forgotten. So let's stop and set a marker. Look at this incredible field and everything it brings you. You deserve this, and together we will make sure that we all remember it. The fascination and importance of understanding the atmosphere, ocean, land, and ice systems are not going anywhere, and neither will we. So even if our plane struggles and we find ourselves lost in the middle of a hurricane's eye, let's call on our friends to help fly in and find the soft spot in the eye wall and guide each other back to camp. Let's repair and rebuild and get flying again. If that seems impossible, if the task of rebuilding seems so much more daunting than that of maintaining, I just want to share the perspective of someone who just helped organize an event like this. When we first started brainstorming about this idea, the size of it seemed deeply impossible. To bring together 100 hours of speakers in just a few weeks seemed unimaginable, and the effort beyond anything any of us could achieve. But we quickly found that the spirit behind this event, the need for it, the desire for it, and the capacity for it was already in so many people that it felt like pushing through the soft spot in an eye wall, of undergoing some sort of critical phase transition where suddenly all the resistance gives way or even accelerates forward. It really has just been incredible to work with everyone on this. So if you're feeling hopeless, you are less alone than you think, and it's not all on you. I want to emphasize one aspect of this that we haven't spoken about much in this event, which is that as part of this event, we've also been reaching out to US-based scientists in this country who are on a visa or a green card. We want to make clear that this event, this effort, belonged to them as well. And many, many, many of them wish that they too could speak. They care about our field and about our efforts to understand the weather and the climate to come. and they also care deeply about this country too. Many of them would like it to make it their home, and they've placed an enormous trust in coming and building their professional and personal lives here. So although they cannot speak, please hear their voices too. So what now? We started with these 100 hours, and that was our initial goal, but it's clear, having done this event, that the community we've built here can't stop here. Already, we've seen some emergence of a Tumblr community. We've now linked to it, wclivestream.com/Tumblr. We'll definitely be seeing you there. The 5 calls script we've shared at wclivestream.com/act. That's going to be as relevant tomorrow as it is today. And we will keep pushing towards our goal of 10,000 calls. So please keep calling. Please promote that link throughout your throughout your networks. And though we have started with the explicit statement to our speakers that this is sort of a one-time event, we want to make it as expansive as possible to include as many people as possible. So we said, people have the option to just speak and not necessarily have those events hosted by us indefinitely, but we will be contacting as many speakers as we can to see how much of this event we can save and share so that people can come back to it. But what else? We want to know your thoughts about where this should go next. There's been so much enthusiasm, both from you, the viewers, from participants. We want to keep this connection and this communication flowing and to keep sharing science. So we have a link. We made a form that's at wclivestream.com/next. So maybe if someone can pull up that, yeah, we have a post live stream survey. Please come and share your thoughts, share your imaginings, share your dreams. We really would love to figure out where to go from here. And we have, we're going to keep our, we have our social accounts on social networks. We have our YouTube channel. Please subscribe if you haven't already. Our Instagram, and our Blue Sky accounts. So please stay in touch and keep meeting us here. I want to reiterate Margaret's point that we're not the only field that is being affected by these cuts. And just like this field belongs to you, all of these fields belong to you. And the thing I said, I think in the middle of the night the other night about streams turning into rivers, that actually fits more. It's many streams that turn into a river. It's many rivers that turn into an ocean. Let's try to get more people speaking. If you're in one of these fields, we're happy to help you. We're happy to share our experiences and to help you in that process. And now just one final thought, and thank you for your patience, but just one final thought for you all. Someone in the chat at some point asked what they could be doing right now that the 100 hours are over. And obviously, going to fill out that survey would be great, but calling your reps, maybe people have ideas in the chat. But there's one more thing I think that it would be great for people to try. And it's sort of what Dr. Shepard was talking about during his talk about being in sixth grade and just being interested in the weather. My thought for you is, I want you to go out into the world and just do a little bit of weather or climate science. So it doesn't matter if you've never been a scientist before. If you see a cloud in the sky, stop for a few minutes and just watch how it changes. Or if you live nearby some water, just check to see if it's at the same level tomorrow as it is today. Just observe that world around you, keep your eyes open, and then once you see something, once you make that observation, do what we did here, share it with someone, show them the data. I think that this science belongs to you, both because we want to share it with you, but also it's because it's a science that I think is in the world that we all live in. So that's it for me. I think that there were some other organizers who wanted to say something. Here, Mark, would you please come on?
I just want to say really quickly, I want to give the recognition to Jonah. He is our fearless leader. This was his idea. We all rallied around him. He led the whole thing. I mean, the number of mornings I would wake up to stuff from him working at 2 or 3 a.m. is absolutely crazy. So really, guys, we really want to thank all of Jonah's hard work here, and we really appreciate him in doing this.
Thank you, everyone. It's been so wonderful to build this together with all of you, and thanks you everyone for watching. I think whether you've been watching, participating, or organizing, I think we could all use some rest. So thank you again for joining us for these 100 hours. Let's keep fighting to save America's forecasts, and we'll be seeing you soon, I hope.
Bye, guys.
Bye, everyone.
See ya.